Everyone, we're back in session and we're beginning with a discussion with respect to session 2 yesterday, the satellite-based approaches of measuring AI. And we have a few seed questions to get the ball rolling, unless you have anything pressing that you want to address from your side. Also, welcome to the online people. I see Felix is here. Felix is a co-chair of the session as well. And we thought we start by talking about the sea-level budget, its closure, consistency or disagreement between the satellite-based ocean heat content estimates with in situ. A thing that we found interesting in that context is allosteric changes, which could be a point of discussion as well. One question that I have, still not super. Oh, I can see the chat today. That's good. That's good. One question that I had was, how confident are we that we achieve closure with the corrections that are already going on? Will we ever achieve closure? Is that even important? And what can we do to address this challenge?
Maybe we just could start. Anne, can you just recall us what is the level of disclosure after the corrections?
Sorry. Yeah, I think in terms of trends, I have 1 millimeter per year left over 2015, 2019. It depends on the period you look at, but which is slightly above the uncertainty.
When you mean slightly, it's about 0.1 millimeter per year above the uncertainty, right? Yeah. Okay. So so the correction for salinity. So yeah, you didn't do when you say that there is no correction for salinity. That is, you're taking the global thermospheric sea level.
Well, somehow the correction for salinity is not to include it, so it's bringing it back to zero.
Yeah. And do you consider so from the talk from James Regan, we can consider that today there is a correction for salinity, right? I mean, you don't expect a larger improvement in the correction for salinity.
I don't. I mean, Annie Wong will talk at 12:30 today, and so probably she's the one best able to discuss that question. But what James showed yesterday was that using only the adjusted salinity for Argo, we still see a change in allosteric. So I don't expect that there will be any more adjustment to the Argo since it was already adjusted.
Yeah.
There's something that's on the back of my mind on this, which is the kind of monopoly that Seabird has on the CTDs of Argo. And this partly comes from me attending a meeting last year where the RBR sensors were being tested by the European community more than the US. And they were making the point that right now, RBR is it's a Canadian company. I don't know if you're aware of it. And their CTD sensor is still kind of under calibration or testing in a way. So they are really going through the same kind of exercise of calibrating them precisely that was done for the Seabird instrument sensors like a long time ago. And one comment that somebody made along the way was that if Seabird was to try to do the same benchmarking that they do with RBR today, they would fail because they have not been kind of benchmarked extensively over the years. So I'm wondering if that's something that's how relevant it is today to this community, whether there's going to be kind of a transition in technology with at least some of the Europeans investing more into a different sensor that might change the picture. I wonder if anybody has thoughts on that.
Well, I don't think so. So Seabird has been involved in deep Argo, which I don't know if they've benchmarked, but they're definitely the precision needed for deep Argo and the conditions that the sensors are under are more difficult than core Argo, than 0 to 2,000 meters. So I know a lot of work has been done between deep Argo and Seabird to make sure that those deep sensors are accurate. As for how that benchmark, I don't know the details of what they did or how that would compare with what RBR is doing now.
Just to say, we are waiting for deep Argo to sense the deep ocean, but we are also missing all parts of the oceans at high latitudes. And all this discussion we had yesterday about whether the allosteric could be actually be decreasing, may it be because when I speak of global mean, it's actually not that as global as we would like it to be. I don't know, in terms of latitude and.
Yeah, I mean, that's a good point. There are data in the Arctic from ice tethered profilers, and there are some Argo floats that do make it up into polar latitudes. And there's cruise data, but I would say at this point, at least judging from what we've been able to aggregate in the World Ocean Database, there's not enough for recent years to answer that question.
The expectations in the future to have a better coverage of the Arctic, or?
I don't know, actually. I mean, there are, this is probably a good question for Annie as well. There has been a lot of work done on under ice floats and so high latitude floats, but I don't know where Argo stands with that.
Because at the end of the day, we're left up with quite an issue, because with the geodetic approach at global scale, if you use just a thermospheric sea level and you don't use a salinity, then you cannot be consistent with regional estimates, which will have to use salinity. And if you use salinity at regional scale, and if you take the global average, because of this salinity drift, you will never find something which is consistent when you're using just thermospheric. So I think that's a kind of an issue, because it makes something which is inconsistent in the future. If we want to have regional and global estimate from the geodetic method of the ocean heat content, then we will have some disagreement. Because then if we take salinity regionally, if we then take the global mean, we will have this drift due to this change in salinity. But maybe it's a single, I mean, so we are left with an issue.
Yes. But I mean, how much from marginal seas, continental shelves, and the Arctic? I mean, that's not a large portion of the ocean. Granted, it may be a part where freshwater and hence the salinity is changing quite a bit. But I think maybe we can get at the problem by other means. I mean, river runoff and precipitation and evaporation in these regions. You know, if we can constrain those, then we should be able to know the freshwater input to those areas and be able to use that to calculate freshwater budgets and from that salinity. I mean, actually, what we're really care about is the freshwater budget. Well, halosteric too. But I do think there are ways of getting around that. We don't have the temperature data in the Arctic either.
That's true. Yeah.
And some of the ocean heat content estimates only go from 60 north to 60 south. And that's okay, because the amount of heat out in the heat exchange in the high latitudes, or I should say heat uptake, is probably pretty low, at least relative. But that is a missing piece in temperature too. Maybe it's more of a factor for salinity. I don't know.
Yeah.
It is my understanding. Oh, are you responding?
No, I was going to follow up, so please.
Okay. I was just gonna say that in a global mean, if we compare thermosteric alone in situ to the satellite-based approach, there's still already non-closure, even without any allosteric drift, right? So do we know for sure that this is due to systematic uncertainties or errors? Or is there still a certain coverage and sampling issue? Does the in situ approach miss heat somewhere as compared to a fuller coverage by satellite, like in those regions that you mentioned? You say those regions are very small, you know, and so on. But do we have unequivocal evidence that this doesn't matter in the closure aspect, that we're not missing heat in the in situ observing system? Oh, there's a hand up. Oh, Karina.
Hey, yes, there had been, so that's an important question, and there had been some which have looked at some areas because it's very difficult because of data gaps to really study these areas. And so, for example, for the Arctic, it was from Michael, there was a kind of quantification, and on the relative contribution from the Arctic or north of 60 north, which was on this amount of equivalent to the area of global oceans, or about 4%. So that's something one takes as a kind of threshold on terms of the area, which would be then larger for the Southern Ocean. But still there is a lot of things which needs to be done, but it's challenging again, right, because of data gaps. But then with this respect is maybe coming back to the discussion on salinity, that for salinity that might be maybe different. Maybe this is much more important, and we really absolutely don't know. We had also specific extreme changes during these 2 decades in the Arctic area between the cryosphere-ocean exchange, so I don't know. That's something to explore, but I don't think that it would fully account for this unclosure or bias. But it would be another way also to maybe, and then in turn understand something about the dynamics and also the ocean, the temperature change with salinity-driven dynamics.
I think another way forward is also to use synthetic data to test the sampling. So that's an effort we will address in the sea level CCI plus the sea level budget project, which is starting next year, and we could share the data. We will do some synthetic data of, at the same time, altimetry, Argo, and GRACE over the same model, and test the sampling. I think it's a good way forward, especially for temperature, but I don't know if I agree with Karina. I don't know if the problem is the same for salinity. I'm afraid the model is not good for salinity. So I don't know to which extent we can do that for salinity as well. But the synthetic approach is very interesting to test the sampling, because sea level is not closing, even without the salinity issue. So we need to know where is it coming from. And maybe a synthetic data analysis could maybe through the community could be also a good way forward to test if we have systematic biases. But I don't know to which extent we can do that on salinity. I don't know to which extent reanalysis or models can do salinity.
I'll try and answer to that. In the eco community, we have, both a global effort that with sort of trust for the Arctic, also for salinity, We do include the ice standard profilers as constraints. We also have a little bit of data from other programs, and there is a dedicated effort to go towards somewhat higher resolution and put more emphasis on the North Atlantic and the Arctic. That's led by Anne Nguyen at UT Austin. So I think there'd be interest in our community to participate in something like this. And in terms of the quality of models in the Arctic, I was going to ask about a related problem, which is the atmospheric conditions over there. When you run models, you know, an ocean model, you provide either fluxes or some boundary condition to the sea ice, for example. And in the Arctic, there seem to be a huge amount of differences, even in the time mean on, say, the way that radiation gets to the sea ice. I've looked at this a while ago, so maybe I'm not up to date, and I'd love for somebody to correct me. But the last time I looked, you know, you sort of get the same kind of net radiation to the surface of the ice, but the split between shortwave and longwave is completely different, like almost 100% different between different products. For driving ocean models, that's a huge issue, right? For the sea ice specifically, because the impacts of putting shortwave or longwave on sea ice is completely different. Then there's the snow component, which also plays a big role for us in the way that we drive our models. And I'm kind of wondering, in the context of this community and of the processing of satellite data, for example, that sometimes uses this atmospheric reanalysis for corrections and adjustments and masking and so on, whether that's an important issue or not. The quality of the atmospheric analysis over the Arctic. Is it relevant to you? So.
Tristan is not here, but Prefire is supposed to address a bit of this aspect, isn't it? Ah, you're here, Tristan.
Oh.
Prefire is supposed to address a bit of this issue, no?
I mean, yeah, but it's a little bit of that aspect, I think. You still need to sort of address the shortwave part of the problem also. I mean, maybe between Ceres and, between Prefire and Clario Pathfinder, we'll have some answers soon, but 2 or 3 years from now.
Yeah, but it remained an open question.
Thank you. It's just a thought from some experience during this reporting activity. So, for example, we have learned a lot when we focus as a community on a specific common goal, such as, for example, an indicator. So like we have the heat content or the Earth energy imbalance, that it allows us as a community to work from different angles in order to provide different new recommendations and saying, if we want to do this, if we want to monitor global warming of the ocean or the Earth energy imbalance, we have gaps here and here and here and here and there. So well, we were trying with this Copernicus Ocean State Report to put also an indicator on board for salinity somehow. And so we started there because, I mean, it's organized like this from a regional basin approach. And so they have different, let's say, systems at regional scale. And then all the basins have different characteristics. And so we started with a kind of fresh water content indicator. And then when we was working with all these regional experts, we realized that that's not an indicator or a metric we can use as a global metric, let's say, to organize as a community around. So maybe that's just food for thought here to think about a metric which would be a relevant metric to, let's say, engage these discussions as an international community, to reply to these questions, and which would allow us to develop these kind of recommendations, to understand what is gapping, where's the problem, also to better address. If we see these kind of drifts, it could be the halosteric, it could be, for example, there's also paper from Li Jing, the salinity difference indicator, but I think this discussion would maybe merit to allow then for very fruitful discussions as international communities, just some food for thought as experience. So finally, we didn't implement an indicator because it's not ready yet. So we worked on the different basins, on the change of salinity in these different papers. but we could not yet achieve. There's a discussion needed to develop this kind of common goal, such as an indicator or another tool, to work together as a community, as we do here, regroup around this topic and talk together.
Okay, so I see maybe interest for a gap analysis from what you've said, Karina, but also maybe an interest for in synthetic data analysis, right? So maybe we could talk about this at the end and at the wrap-up. Because in the interest of time, I'd like to raise two other questions. So the first one is about the expansion efficiency of heat, which is so important for the geodetic approach. In different presentations, I see different estimates of this expansion efficiency of heat, which depends quite a bit on the Argo measurement. And I wanted to raise the question, don't we need, maybe in the interest of the GeoX assessment report in a few years, don't we need to agree on how we should estimate this expansion efficiency of heat and agree also, or maybe, I don't know if we need an intercomparison, but at least that we agree on how we compute it and what is the uncertainty associated to it. Because I don't think it's, I think it's really something that we can grab. I mean, it's a low-hanging fruit. It's not that difficult to estimate. We just have to agree, and I think we can have a good idea of the uncertainty associated to it, because it's an almost constant of the climate system. So do you have reflections about this or comments?
Did you say it's a constant of the climate system?
Almost. It's changing.
It varies over time, in space, vertically. It's a function of temperature, salinity.
Let me be clearer. At global scale, in the climate system, it depends on the circulation, which changes not that fast with climate change, and we expect changes of about 15% by 2150. So it's not a high at global scale. I'm talking about global scale. It's different at regional scale, so maybe we should have a look at this. But at global scale, it's not highly dynamic. And I think it's definitely within the reach of our observing system. I mean, at least the part of the ocean that we're observing. And I'm just wondering whether we should. I think there is room for progress here in the geodetic estimate, that we make a clear comparison and we make like best practices on how to compute it, and we can just test it over the region of the ocean where we have observations, and then we just like discard this problem, and then the problem will only be a problem of uncertainty linked to the sampling, and we can evaluate this.
I mean, I think what we did back in 21, we calculated basically the ratio between the sea level change and the ocean heat content change that comes with it, right? Using echo. And I think we did running trends over a longer time period. And I think we tested whether the time variation globally affects our heat content and storage estimates, and it didn't very much compared to everything else, the uncertainties of the data products and GIA. It wasn't a big error source, at least for the global estimate. And I also remember, is it his name, Tim Coolbrot? He was there in 2018. He did this with climate models, right?
Yeah.
So I think in the global mean, we have a pretty good idea what the magnitude of this efficiency is, right?
I agree. I mean, even ECHO is very consistent with in-situ data and quite consistent with a bunch of climate models.
Yeah. So maybe the question is, do we need to address for global estimates the time variability of it? You know, have a better idea of what its role is in the error budget. And then, as you say, we need the regional estimates. We're only just in the beginning of producing regional heat content from the satellite approach, I feel like, right?
Yeah, that's right. I wasn't arguing for an intercomparison of this aspect. I was just saying that I feel that I see very different numbers on different slides, and I'm just wondering if we all agree on how we compute this and if all of these numbers are consistent. And then some people may just wonder whether, also it shouldn't be a large part of the uncertainty. I definitely agree. We did the same kind of analysis, and we find that it's not an important source of uncertainty. But then maybe because we are not using the same, we find it's a part of the spread between the different estimates. So that's just a suggestion.
I was just going to follow up on, on a kind of echo, I guess, say that, a lot of us are very interested in the sea level problem. And if there is, like it seems to be, an agreement between already the two sort of sides of the Atlantic on kind of leveraging echo in that regard, if we can help push the notion that echo should be one of the standard products used for this coefficient, I'm pretty sure we'll find some motivations to help on our side. And yeah, no, I'm very glad that it's being used in that way, personally.
Okay, so so there is some interest. So we can talk also about this in the wrap up. Just another question, which is more difficult, I think, is something that came out from the discussions about the geodetic time series is what happens with the geodetic time series below 2 years. So it seems that we are converging towards a quite good agreement between the geodetic time series and CIRES and also Argo on long time scales, like above 2 years. But what? So we all recognize that we didn't show those time series, but we all recognize that below 2 years, there are some large variability in the geodetic estimate of the ocean heat uptake, and this large variability for most of it is probably spurious. And I think maybe in the future that's something we should address, because one particularly interesting objective in the future is to try to close the energy budget, because it provides a real independence. So this question of conservation of energy provides an independent mean to improve our different observing system, starting from satellite altimetry, GRACE, Argo, but also CIRES, if we can. And to do that, we need to go at higher frequency. But we didn't show it, but if you look at the time series of the geodetic methods below 2 years, there is a very large internal variability, which actually sums to zero when you filter at after 2 years. So one question is, where does it come from, and should we address this in the future, and what can we do about this?
I'm not an expert on any of this, but I mean, we're combining different data sets here, and each has their own, I guess, noise pattern, right? So why would we expect that they produce, a smooth, perfect?
My personal understanding of the problem is that we don't have an exact good combination between GRACE and altimetry at those time scales. Just talking about sea level, then the reasons are due to some aliasing, I think, of the annual cycle in particular, because GRACE, the annual cycle, the exact phasing is not very good, and we have also doubts in the altimetry. And then I think this problem is very much amplified by the fact that we take the derivative of the combination of altimetry minus GRACE. So if you don't have very good agreement, which happens at those time scales, and then you take the derivative, then you just exclude the noise. And so the question is, how do we combine more properly satellite altimetry and GRACE? And I think it's really about this window of time scales.
Did you filter after all the combinations, or do you filter the components separately?
We filter the components separately, I think. No, afterwards, right?
For the moment, in our Lagos Magellan geodetic products, we filter the steric component, but at regional scale. This means we filter in time at 3 years, the ocean content at regional scales, at local scale, I would say. It is grids of 1 degree by 1 degree. And after, we calculated the global ocean content. And then we derive in time the OHC to obtain the Earth energy imbalance. But as said by Benoit, if we reduce the period, if we reduce to 2 years or 1 year, we obtain quite large signals in the Earth energy imbalance, which for the moment are not explained. I say, but Benoit, we would like to investigate 2 things. The first one is if there are discrepancies between altimetry and gravimetry measurements, and we have some ideas to try to homogenize the processing of this data. And the second thing that we would like also to investigate is this signal in the Earth energy balance is coming from the internal ocean variability. And for the moment, we are not able to say what is the proportion of this between the internal ocean variability and potential discrepancies between altimetry and gravimetry errors. But we would like to address this question in the following months or maybe years.
Just a quick question or comment, or just in general, something which could be maybe of interest is this question we had very often in terms of for the global heat content from Argo or in situ in general. There's this discussion that if you go down at monthly scale, for example, that this might be spurious. Then you have messages I highlight, for example, yesterday, Argo has not been designed for globally monthly, and it had been designed for 3 monthly. Then people use annual to be sure, and there have been also papers which compare that it's very spurious if you compare the monthly means. So this kind of question would be maybe a very interesting question also for the synthetic profile approach, to see what is Argo already achieving today in terms of this temporal resolution. So to really reply to this question first. And second, which would maybe with this question, for example, or these plant analysis steps, for example, or others, to leverage this question, do we need more? So to come back to your point, Maria, do we need more in terms of sampling, or is it sufficient, or can we improve the uncertainties if we want to go down to monthly or 3 monthly or something like this? I think these are still, let's say, very qualitatively discussed questions, which could be another nice leveraging point resulting to new recommendations or even new opportunities to study, for example, the role of internal variability of the ocean and so on.
Yeah, if I can add to that, I agree very much with what was said. And it sort of relates to what you're saying on the derivatives also. I think it's sometimes overlooked how much the subjective choices made by the people who do like optimal interpolation type of products matter. And so especially when you start looking at quantities that involve derivating a couple things, you see those choices come up. So when, for example, the Rummick and Gilson product at Scripps, we tried to use it for, we did like two levels of derivatives in there, one in depth and one in time. And what came out was pure noise. We, in fact, convinced the observationists that were working with us on this problem that echo was a lot better as a smoother in that way. And I think if you compare, we might hear more about this afternoon. But if you use one of them, I'd suggest you use multiple in your analysis to test these aspects, because they're not necessarily evident in the literature, right? What are the choices made by the producers of these, temperature analysis from data? I think it's something people don't worry about enough.
So I agree with this, and I think that the key challenge, if we go to a synthetic data analysis and if we find a champion to take this over, I think the main problem is that at the end of the day, it comes down to people doing in situ data, because that's the one who will have to take the synthetic data and do their optimal interpolation to provide the interpolation, and so we can then compare with altimetry, the synthetic data from altimetry and GRACE. I mean, on the altimetry and GRACE side, we are ready to take out the output from models, the synthetic data, and provide the global mean sea level, the ocean heat content, ocean heat uptake, and I think it's quite easy for us. But then that means that every group of in situ people who are doing an interpolation, an objective interpolation, will have also to do it. That's a bit of a work. Are we ready to do that? I think it would be a great progress, but are we ready to do that? And which group are interested?
Ready to do what? The synthetic?
Yeah, so you would be provided synthetic data from a model, and then you have to do your optimal interpolation from the synthetic data and provide an estimate of the ocean heat uptake and the ocean heat content from this synthetic data.
Yeah, I think I see Matt Palmer online. That may be the, I think it's the goal of map for heat eval. Matt, did you want to say something about that? I know you have a talk later.
Yeah, you, Matt.
Folks online, Matt Palmer, for example, if you want to say something, we're not sure we can hear you. Can you? He asked something in the chat, but that's already a while ago with respect to shallow regions and the sampling we talked about earlier.
Do a mic check. Can you hear me? This is Felix.
Felix, no, we heard Felix, right? Yeah, okay.
Yeah, you could hear me. I see Matt unmuted, but I don't hear him either online, so.
Thank you. With this respect, I would like to remind on the keyword Maria put on the table yesterday, that this keyword on best practices. So, and you just ask a question, how can we collaborate? What would be the interest from the different groups? So, I mean, there's this initiative, and we will, I think, then hear more later in the talk. But so it's an interest about best practices in terms of developing these products and the evaluation of heat content. But then from, for example, the assessment you're doing, for example, under GDAP, there's another question. So that's why Maria put this on top, is on the best practices, how to evaluate, let's say, the derivative and this global scale ocean product, and how to compare with the other components of the observing system. So that would be another best practices approach that in turn could link. There's a huge initiative under GOOSE, for example, IOC, which are tackling these best practices, so that could be something which would interconnect a lot of activities and leveraging the questions in terms of community recommendations, which would go ahead alongside with this community and maybe under this keyword interlink them the discussion. So it could be maybe an opportunity, I don't know.
So that's definitely an outcome, the question of best practices. We will talk about this in the wrap-up. Just before turning this page, I wanted, Bern Webbing, you're online. I was just wondering, do you have the same, so it's very interesting to see that your group is producing now also a geodetic estimate of the ocean heat content. I was wondering, do you have this issue we find as in JPL or in Toulouse, this issue about the large spurious signal between probably spurious signal between 1 year and 3 years in your solution. Can you comment on that?
You mean in the ocean heat?
Yeah.
I think it's difficult to look at this estimate on this short timescales because of computing the derivation during the conversion. So this acts as a short pass filter and increases the noise quite a lot. So this will affect the short-term estimates. And I think what was mentioned earlier with respect to the combination of the altimetry and grace, I don't see this as much of a problem on the shorter time scales. Yeah, it's so I think what I'm trying to say is it's difficult to look at these trend. So since it's also a trend estimate in the end at short time scales, because
Yeah, that's a question. So it's trend if you look at long time scales, but if you look at short time scales, it's derivative. And so that's the whole issue.
Exactly.
So, but should I get from what you're saying that your method is not adapted to go higher frequency in the estimator of the ocean heat uptake?
So theoretically, we get ocean heat uptake estimates for each month.
Okay.
And what I showed yesterday with the conversion, where we use the scaling, we can even theoretically do the scaling on a monthly basis. But that would then potentially lead to some issues regarding numerical problems, because since we are doing the ratio between two values, it becomes an issue when these values are very small, because then we get a huge scaling factor for that month, which doesn't make sense. So, which is why we resorted to the RMS for our method. And I think with respect to what was mentioned a few minutes ago, that, for example, Echo is smoother than the product from Scripps, I think this isn't too much surprising, because it's a model, and the other product depends on observations, and of course you will get a more noisier estimate from the observation result. I'm not sure if I answered your question.
Yeah, it does. Thank you.
I was gonna ask something, but first checking in with the online audience to give a chance. Okay. So we're talking about models. I know there's a session coming up, but would you agree that the models kind of represent physically consistent smoothers? I don't know. Am I simplifying? I feel like we should look at them a little more. I mean, that was the plan all along, right? So I'm looking forward to the session in terms of the closure. For example, Anne showed when she used Horace, the latest discrepancy or non-closure isn't even evident. I would like to see that with Echo. I'm not sure I've seen it. Ian might show something, right? And then, but also the derivative, I wonder how it looks in models. And if different models are all over the place, or also if there's an amplitude issue, maybe it's gone when you use the models, which like fill all the time steps up, right?
Can I just, sorry, I'm talking a lot, but I feel rather strongly about this terminology of, observations with those models. I'd like to point out, like you said, that the Argo data is in both the Rummick and Gilson type products, and as well as in ECHO, both of them have, in fact, models. It just so happens that the model that Remick and Gilson uses is purely statistical, and that ECHO has a lot of dynamics to complement that. And so ECHO tends to be smoother because of the way we do it, but you will find pretty large contrast in noise and signal levels when you compare different products that are purely statistical on one hand. And similarly, if I compare ECHO to other data assimilative products, you will also see a very different behavior. So it's a little more subtle than saying, you know, optimal interpolation is observation and ECHO is models. I think that's a bit misleading.
Yeah, I don't know, want to get into that now, but I mean, a model, it's a set of equations, if you will, physical equations that that are run and then altered or relaxed, or I don't know the right word, towards the observations. So, but it's the model that's relaxed towards the observations, where in the statistical, like an optimal interpolation, is using just the information from the observations to interpolate or extrapolate to areas without data. So I do think there's a big difference, and I wouldn't refer to the optimally interpolated as modeling. I mean, it's a point of view, so I don't know that.
I'm not sure we have to enter this discussion now.
Yeah.
Do you really want to do?
It's fair enough. Yeah.
What about talking about this afterwards, or within the discussion after the reanalysis session? Is that fine? I think it's a deep discussion. It's very interesting, but we won't get out of it like in a few minutes. And there is a last question I like to address the audience before we move to the talks. Do we think we have overlooked a source of uncertainty in the geodetic approach? And if yes, which one? And do you think there is one that we should look into more details?
I'm not sure if it's fair to call it a source of uncertainty, but I'm thinking about the wind-driven modes of variability of the ocean's sea surface, right, and of bottom pressure as well. In a way, you know, there is a lot, when you look at the record of spatially varying sea level, you see a lot of fingerprints of that, right? And so is the obvious example. There's a lot more. And I wrote a paper once where I suggested that ECHO, for example, could be used as a correction term to subtract that from both grace and altimetry as a way to sort of clean up the problem to get to, you know, the Earth energy imbalance problem.
So that's a good point. Yeah. So that's something we're looking into, because there is one point where you're definitely right, is that what we call the barotropic correction, which is not, the barotropic correction is not the same in grace and in altimetry. And so we've been knowing that for a while, and we suspect this could be one of the sources of the noise between after 1 year, because we suspect it could alias at longer timescales. For now, in altimetry, what we remove is the inverse barometer and the barotropic response to winds under 20 days. That is something we're not doing in grace. And there's some evidence, especially from JPL, from Joanna in sea level. So she presented this a long time ago, I think 3 years ago, that if you do that in grace, it changes your signal even after 1 year. So that's definitely true. We do not do this properly. Now, that's a good question. What should we remove exactly? It's it's one of our priority in the Toulouse group for the coming 2 years. And the first question would be, what should we remove? So for the time being, when we do this in altimetry, we do this with a barotropic model like TUGO and MOG2D. I know that ECHO can do that, but because this is done in altimetry with this one, I think we will take this one to do in grace. So that's definitely something which is overlooked, but it's as a target.
There are also additional uncertainties from the solid Earth component, the corrections that go in. The GIA correction is just a linear trend, but you will find groups that will present papers with updated GIA models that can seemingly, close the budget residual a little bit better. I mean, you can make 15 years just a little bit slightly worse and get the last 5 years a lot better, right? So you'll find that, and then it's hard to discriminate between GIA models in general. And additionally, there might be time variable solid Earth corrections that we're not doing quite right. Famously, we had a C21 sort of issue a while back, and that was sort of a definition, but there's some geophysical processes that map into time variables, large scale patterns that I suspect in the next few years will, as we have more data, that will also shift again. And that's one reason why I always do not want to tune processing choices, post-processing in either altimetry or grace, just purely on minimizing the residual. There ought to be some sort of more first principle traceable correction that you can independently verify, such as the wet troposphere correction, right? Like you look for other models, you look for data that corroborates that. Just closing the residual is and have nothing else is dangerous.
Yeah, I agree for GIA, but just Felix, just a point about the wet tropospheric correction. We are not trying to reduce the residual. We just trust the FCDR from the SSMI, which is better than the radiometers, the altimeter radiometers
I know.
for simple
I was
reasons.
I was mentioning the wet tropospheric correction as an example of a good way of going about it, because it's
okay.
traceable to
Yeah,
something else.
I definitely agree with
evidence.
Yeah.
It's not just about closing the budget. Yes.
I definitely agree with you with this. We shouldn't make a change if we don't have physical and rationally behind that tells us that it should be better. And even I would go
you and
for.
We've been in this. We've been around the block a couple times. I've seen this in the past where these subjective choices, and sometimes it's really subjective, get that were mentioned before. They get made, and once they're in the literature, it's really hard to get them out.
And so, just about your point about GIA, do you think that? So I understand you say the GIA correction is probably not the right one. That's true, but do you think that would change also the uncertainties that we are affecting to GIA? Should we increase the uncertainty that we affect to GIA currently in our estimate of the uncertainty on EI?
I'm not sure. I don't even know. I mean, in Alejandro's presentation, that was the GI correction was sort of the main one that clustered it in 4 groups, right? Or whatever the number was. Was that driven by the GIA or the Geocenter? I don't remember.
Yeah, there's a combination of both, but yeah, it's one of the major sources of uncertainty, which is already quite large.
I mean, the good thing about the GA correction is that it's kind of you don't need to go through the whole motion of doing the sea level budget. You can kind of keep it separate and just estimate the impact on sea level, and well, you come back to the expansion efficiency again because you do need to multiply it with that. But so I'm not sure how we're tracking it right now in the uncertainty budget. I think in our paper, in Maria's paper, we used an uncertainty estimate from Lambert's GA model, right? A large sort of ensemble of 4,000 realizations of his GIA model to span that uncertainty.
Yeah, okay. Okay, thank you all. We should move on to the next session now for the talks. Thank you for the discussion. So I noted your different points, and we will propose something at the end to summarize all of this. Thank you. So who is, I think, leading and you, Tim, you're leading the, and who is the other co-chair? And Michael, yeah. And Michael. Yeah, I will.
Could I just check my mic quickly? Can you hear me now?
Matt, is that you? Yeah.
Yeah. Great. I just wanted to check it was working. Thanks. Brilliant.
Good to hear you.
It's nice to see you. Nice to see you all.
Could you please check the audio in the room? We cannot hear you online.
Can you hear now?
Yes, thank you.
All right. Thank you. I cannot move the, I do not. Oh, this? I don't seem to have control. Gotcha. Okay, sorry for the delay. So I'm just going to shut down everything. Can you help me one more?
No, this is something that you already see. And then you go. Okay.
Gotcha. Okay, one more time. I'm Tim Boyer from NOAA's National Centers for Environmental Information, and I'm going to talk about a comparison of Earth's energy imbalance in situ ocean heat content calculations. And this is part of the GWEX Earth's energy imbalance assessment that's been introduced before, and the data and assessments panel perspective and support for selection process of suitable EEI products for production of globally consistent water and energy cycle products. And the specific focus here is understanding and quantifying uncertainties in situ calculations of ocean heat content and ocean heat uptake. And the same basic data set of ocean subsurface observing system data underlies all of the in situ ocean heat uptake calculations that I'm going to show. And so I will argue that the analysis method, while it does have some impact, the main dependency is quality control and usage of available data, what I think, Gail, you were alluding to before. So this is all based on data which has been in situ data which has been posted to the GWEX EEI website, which you can see here. There are also satellite data and reanalyses, but there are eight analyses of in situ data that will be discussed today. But before getting into that, I want to talk about some of the methods. There are documented uncertainties in ocean heat content or ocean heat uptake, but a lot of these are not large factors in the Argo global era, the era that we're talking about here, from about 2005 to present, when Argo became sparse global. So on the left here, we right now are going through the process of calculating new climatological mean fields, the World Ocean Atlas 2023. And there has been some discussion that the use of different climatologies does have an effect on the ocean heat content time series. So on the left there, you see 3 time series separated by ocean heat content. Ocean heat content is the x-axis year on the y-axis. Excuse me, flip that. Y-axis is heat content. Year is on the x-axis. And you can see right now the NCI product, I call it LEV here for short for Levitas. I still call it that. Uses the World Ocean Atlas 2009, 1955 through 2006 baseline reference, and that's the black line. And there's the red line, that is the new calculation of the World Ocean Atlas 2023 climatology with an updated Levitas XBT correction. That's from 1955 to 2023. And what we are planning to use for our updated ocean heat content is a climate normal 1991 through 2020 calculation. And you see on the left there, they are spaced when you do these are 5-year running ocean heat content years time series from 1955 to present. And you see they're spaced in time, which you would expect because there's a different amount of heat contained in each of those climatologies. But on the right there, when you reference them, or re-reference them, I should say, to, in this case, the 1991-2020 period, you see from about 2000 on, there is really no difference. In earlier years, yes, there are some differences, and that does need to be taken into account. But for the time period we're talking about here, this really shouldn't be a factor. Likewise, XBT corrections. The XBT was the main expendable bathythermograph, the main observing system from about 1970 until the advent of Argo. And there is a bias in the XBT that needs correction. So on the left, this is calculation of the NCEI ocean heat content using that method, but using a climatological mean field and data with two different corrections. One, the Levitas correction, that's WA23X, and WA23C is the recommended now correction, the Cheng et al. Correction. And you see on the left there, there's a little bit of difference, and that's because we calculated the climatology with the XBT correction as well. So you're basically looking at two slightly different oceans with the different corrections, even when you're using just the 1991 through 2020 period, because the 90s were dominated by the XBT. But again, when you re-reference them, so they're using basically the same baseline, you see very little difference at all to 2000 and back. You see some differences before then, but basically in the time period that we're looking at, this is not a factor. And so now looking at the 8 different time series, and I'll go into each one in a little more detail. So looking at it in 2 ways. On the right is ocean heat content anomaly, so the accumulated heat in the ocean, and this is the way that we in the ocean community usually look at this, because that's what we're interested in, is the accumulated heat in the ocean. And so this is referenced when I showed this in Bern or something very similar in the last EEI workshop, and the discussion point came up: is this really a valid way to look at the data? You see in there the series. This is referenced, if you will, or compared to the series net flux in black there, and 90% in gray on the right, and then all the other heat contents. And to make it so, we know that series is looking at the change. The absolute value of series is not the important point, but the change, the year-to-year change, which we look at on the left. But to compare it to the heat content, at least for myself, it's better if we start and reference all the different ocean heat contents to one point, and that's basically the point of series in 2005, and then let them run freely there. I do think it does give us some good information to look at this as ocean heat content anomaly or accumulated net flux from series, and it will tell us some information. For me, it's much more difficult to look at it on the left, and that's in ocean heat uptake in watts per meter squared, which for the ocean heat content time series is the derivative. And as we talked about in the discussion, that makes for that amplifies noise. So, but I still think it's valid, and it is important to look at it in this manner. And you can see some things that jump out, and one is one that we've been discussing here, which is 2016. You can see almost all of the ocean heat content or ocean heat uptake from the ocean heat content calculations are negative or close to zero, whereas the series does not see this big drop in 2016. So I'll look a little bit more into that later. I'd also like to show, even with all of this, almost call it noise, on the left, the heat content on the right are pretty similar, but only one actually is as large as or matches the series, if you will, and that's the ISAS. In yellow, you see on the right, it follows along with the series pretty well, at least the 90% line. On the right, you see the correlation with series is not so good. So looking at these a little bit closer, one by one, and I'll try to do this quickly. So on the right, this is the NCI ocean heat content, and on the left is the ocean heat uptake. And you see it doesn't match very well. The R squared there in the bottom is 0.29. It's pretty noisy compared to series, and you see the big drop in 2016. And this is what we calculate at the National Centers for Environmental Information, objective analysis, 26 ocean layers, using all data, Argo and other from the World Ocean Database, baseline climatology. So this is new. This actually isn't up on the site yet. I got this from John Lyman and Greg Johnson. This is the RFROM, Random Forest Regression Ocean Mapping. And their paper just came out in March, I believe it was. And so they show a very high correlation with ocean heat uptake with series. And you see that here. But you still see, in this one, you still see the big drop in 2016. And on the right, you can see how that plays out in the accumulated ocean heat content. And you see it starts out pretty much the same as series and then drops off and loses that accumulated heat, especially in 2016. And so the R squared that I calculated here is 0.42. The R squared that's calculated in John and Greg's paper is 0.61 for the yearly. And so they do a little bit of smoothing, and there are some other reasons why the R squared is going to be a little bit different. I just used a very simple, I took the data they provided and just subtracted 1 year from the next. Well, after taking a mean from the 7-week averages. Anyway, there are some reasons for the difference, and I'm not going to talk about R squared anymore because this is the highest R squared of any that I calculated. Then there's the JMA, the ESA objective analysis, 1 month grid, 26 levels, 0 to 2,000 meters. And you see, again, pretty good agreement, except the big dips in 2008 in heat uptake and, of course, in 2016. And you see how that plays out on the heat content on the right. And this is the PMEL. This is actually the data that was used in the Loeb et al. Series paper from 2021. So this, you see on the right, it follows along very well with series, which is what you would expect, because this is actually the data that was used for the 10-year average to peg the series data too. But this also has, in 2016, the big drop, and that accumulated heat never recovers, if you will, back to the series. So there's really something going on here in 2016. There's other things that you can see, other differences on the left, and different actually than what was shown in the paper. And so the data that I got from John and Greg is yearly. The data used in the paper is also yearly, but every 6 months. So a year's worth of data every 6 months. And there's some other differences here, but it does show up very differently on the year than it does from the paper. And this is the Institute of Atmospheric Physics. This is Li-Jing Cheng's work, Ensemble Optimal Interpolation, 1-degree gridded fields. Li-Jing provided it in monthly, and I just averaged it to the year, and based on the papers listed there. And you see a lot of variability, not just in 2016, but the drop in 2019. And this is Cusello and Giglio. And this, for the first few years here, up till 2010, it matches exactly series EBAF. And you can see that in the accumulated ocean heat. Then the big drop in 2016, and again, the accumulated heat does not recover in the Cusello and Giglio as with the others. And note there are some differences here. This is 0 to 1,850 meters, not to 2,000 meters. So there are some differences in this field, and mapped using locally stationary Gaussian process. And there'll be a talk on this one, as with a few others. And then the Hadley Center, the EN4, yearly ocean heat uptake and ocean heat content. And you see a lot of variability in the EN4 in the ocean heat uptake, and that plays out in the accumulated ocean heat as this is the lowest accumulated heat time series from all of them that are looked at, and this is objectively analyzed fields using persistence. So persistence is a first guess using the previous month's anomaly, and then I received the monthly fields here were averaged before they were sent to me. And this is the ISAS. And you see on the right, this matches quite closely with the series in the heat accumulation. But if you look on the left, you see big differences in the ocean heat uptake year to year. And you see that big jump, the big drop in 2016, and then large increases in heat uptake, larger than what would be expected using series in subsequent years. So there's a lot of differences between the different methods in ocean heat uptake. There's also difference in accumulated heat, but less so. And so the next step, I wanted to look at this geographically or regionally. What is going on? And you want to look at year 2016. What is going on? And maybe we can discern something. Why is the big drop in heat in the ocean that is not seen by series, or the opposite of what the energy entering the Earth system? And so looking year by year, this is 2014 on the top, and red is positive heat versus the baseline and accumulated heat, and green and blue is negative. And so you see 2014 a pretty average year, and then 2015 is an El Nino year, and you see big changes in the Pacific there that you would expect from an El Nino. You also see a lot of change in the around the Antarctic circumpolar current and in the North Atlantic, a big cooling in the subpolar North Atlantic, and then the difference field on the right. So that's just stepping through 2014 to 2015, and then 2015 to 2016. So there's 2015 again on the top. On the bottom is 2016, and this 2016 started out in La Nina conditions and ended in a big, El Nino conditions and ended in a big La Nina. So you see that there in the pattern in the equatorial Pacific. You also see continued big changes in the circumpolar current and in larger changes in the subpolar North Atlantic. And then you see the difference. And so a lot of the difference, which is basically the heat uptake, and I have the wrong heat uptake there. It's 2016 should be -1, plus or minus 0.2 watts. But you see the difference between 2015 and 2016 is concentrated in the La Nina area, although there are other regions where it's cooler than 2015. And then going from 2015 or 16 to 17, and you can see that the warming again in the area around the El Nino pattern. So I wanted to look at this in ISAS as well. A few of the other data sets on the GWEX had provided the geographic distributions, and I wanted to look at ISAS as well because I wanted to also look at the big jump in 2019 and where that might be happening geographically. So here, this is again stepping through 2014 to 2015. You see very similar patterns to what we saw in the NCEI. And again, maybe even enhanced the difference between well, actually it's more concentrated, is what I should say, around the equatorial Pacific, the difference, as you see in the top right there, between 2015 and 16, and then 2016 to 2017. So this, I think, really to get at the differences between the methods and to understand the ocean heat uptake patterns, we're going to have to break this down and start to look geographically like this. And also to understand the differences between the resultant fields from the methods. We'll have to do this as well. And this, to some extent, we're looking at two different time periods here, because the NCI, the baseline used here is 1955 to 2006, where ISAS is using 2005 to 2020. So this is somewhat nonsense. What I'm showing here, you can't really tell what's going on with the difference. I need to, and I just haven't graphed it, normalized to the same baseline. But you can see, and that some of the big differences that will show up when I do this right, that are around the Antarctic circumpolar current and around boundary current, the Gulf Stream. So this is actually looking at the differences in 2019, where ISAS jumped up quite a bit compared to the other heat content. And so just about 2016, I don't want to get into monthly. We're still working through years, and maybe we'll get to the shorter time periods. We need to, of course, but what happened in 2016, a La Nina year, was a peak, or a trough, I should say, in the ocean heat content in August 2016, and 2019, a similar thing happened in August. There are specific months where this negative uptake occurred here. So, although it's a question unto itself if we have enough data for a good signal-to-noise ratio for monthly, there is something going on here that maybe is. We do need to look at time periods less than a year to understand what's going on. 1 minute, okay. So I did look at a few other things. Does the mixed layer or upper layer ocean heat uptake correlate better with series than the deeper layers? The short answer, at least for the NCI, is no. And as Maria brought up yesterday, some of the methods that use Argo only correlate better, or at least have better R² compared to series than the methods with all in situ. And I think that's probably more coincidental, maybe based on the methods. So I did look at NCI using Argo only versus all data, and those are the red and blue lines, and they're almost identical, although you can, in ocean heat content, although you can see some differences in the ocean heat uptake. Now, when you use Argo only with the Argo QC only, you get the green line, and that, and this I've talked about before, this is does show a much larger heat uptake, and this gets into, which I won't because I've taken too much time, but the mesoscale eddies. So Argo's QC is basically to make sure the data is good data, that there's no problems with the sensors and so on. It's not, more needs to be done, I believe, to look at Argo floats or data that's in mesoscale eddies and how that affects the overall ocean heat content calculation. And this is just a picture I've shown before of an Argo float that was deployed into a massive mesoscale eddy that had warmth, 12-degree heat down below 500 meters. And this Argo float actually followed it for more than a year. Because there is sparsity of data, this mesoscale eddy that the Argo float was in aliased that heat into a larger area around it and had an undue influence, if you will, on the integral of ocean heat content. So there does need to be more looking at or filtering of Argo data for mesoscale eddies like this. And we're starting to look into doing that using some eddy tracking. This is work by Heather Roman Stork to verify that these Argo profiles are in mesoscale eddies so that they are good data, and then how to handle them. Use the altimeter data to constrain the limits of the mesoscale eddy so it's not alien heat into a larger area of the ocean. So I'll just leave the summary up. Thank you.
All right, thank you very much, Tim. So we are running a bit late, so I suggest that we leave the questions for the coffee break, which right after this, and let's move on to the next talk by Li Ching.
No? What should I do? Okay.
Yeah.
Okay, thanks. So, hi, it's good. Today I'm going to introduce the update for the RAP ocean heat content data and give some implications for EEI. So, have some colleagues here, Victor, Yuyin Pan, Zhetao Tan, and Yuehui Fer. And now who we are. So we are providing the IAP Global Ocean Heat Content time series in up to 2,000 meters. So this is our time series, and I'll skip this. And we are direct approaches. We're based on, actually we based on World Ocean Database. So now we incorporate more data, GTSPP and our Chinese data. But today my talk is mainly based on World Ocean Database, and we have do core QC and do bias corrections and do mapping, and then to give graded data and ocean heat content estimate. So this kind of processes are really important to understand the uncertainties of ocean heat content. So there are some indirect approaches that talked yesterday, so I'm going to skip this. So basically, we relied on the integrated observation system with various instruments to observe the ocean heat content, bottle, MBT, XBT, CDT, Argo, Glider, APP. With so basically, we use all the available data. And so we're not Argo only product, because other data have some complement in a lot of areas, Arctic, polar regions, and coastal regions, and ITF regions. So we find it very useful to integrate all the data we have to provide OHC. So what is the new here for this year's release of IP? So we improve our data quality system. So we, in the previous version, we use World Ocean Database QC, but now we developed a new QC system to have 14 QC modules to remove some spurious or erroneous data. The key module is the local climatology check, because previously people used maybe 3 times standard the deviation range to filter out the bad data, but we know that the temperature distribution in the ocean is not normal or not a Gaussian. So we use the percentile, 0.5% percentile, 99.5 percentile threshold to account for the anisotrophic feature of the local temperature distribution. And we also account for the topographical barriers in some complicated channels, for example, ITF. Because the channels, the land, they separate different ocean masses. And also we do the account for the ocean warming, because we know the ocean is warming, so the threshold should change. So now we have more positive extremes than the past decades. So the range actually changed in our system, and we have a linear rate for this kind of threshold to account for the impact of ocean warming. So we also optimized this system with the diagnostic tool and eventually and evaluated manually. So all this work are done in the framework of IQOT. So this is an illustration of how we remove the spurious state here, as you say in red. So what is the impact on the ocean heat content? So we just do a simple test. We use all the other methods are the same, but we use World Ocean Database QC in orange and the CODC, the new QC system, in blue. So we find that the impact QC on ocean heat content up to 1,000 meters, up to 8%. It's really a huge difference during the Argo period from 2005 to 2021. So the new QC system provide higher rate of ocean warming in the recent decade. Why is that? So we take the difference of the two ocean heat content calculation between WOD-QC and the CODC-QC. So the difference is mainly in the eddy regions, the boundary currents regions, the Gulf here, and Crucial and ACC regions, and so it's really interesting. So we try to find the why is that. So we compare the our temperature profile. We calculate the steric sea level. We compare with altimetry data. So you see they are quite. This is in the Northwestern Pacific, the crucial regions, and I think it's 2020. It's just 1 year date. So you can find that the correlation is really high. But the green lines are all the data we have for temperature profile, mainly from Argo, but also have some CDT, XBT stuff. And all data is in green, but if we QC it after, based on World Ocean Database, so the black light shows the data that has been removed by World Ocean Database QC. So you can see that a lot of positive anomalies that looks really good because they are highly correlated with altimetry data, but got removed by the WOD-QC. So that is before QC, the distribution temperature anomaly before QC and after QC. So a lot of positive anomalies being removed. So we argue that probably the statistic, because World Ocean Database QC also based on the local climatology range to filter out the bad data. But this range has to be changed because this statistics based on the old data does not represent the current state of climate with some real extreme values over here. So that is our guess for why QC can have so much impact on the ocean heat content in the recent decade. And actually, even for our new QC system, CODC QC, we did remove some of the positive anomalies. So I just talked with the team that we need to have some post-QC exercises to compare with altimetry data to bring back a lot of good extremes to improve the estimate of ocean heat content. So this is the QC stuff. And then the bias. So if you use the institute data, you have to deal with the biases. So this is a XBT bias from late 1940s to 2000, and the MBT is more or less a positive biases. The sources of biases is not really well understood, but it's likely a combination of a lot of factors: the data recording systems, the depth measurements, a lot of issues. And before we use the ESA method to correct the MBT bias, now we shifted to a new correction schemes proposed by Victor and myself in 2020. So the difference is mainly in 1980s and 1990s. The maximum difference is 25 zetajoules. So the MBT bias does not have any impact in the recent decades in Argo periods, mainly in 1980s and 90s. So bottle bias. So this is the new finding. So we find that bottle data also have some biases from 1970s to 1990s, much larger in 1970s. So if we apply this kind of bias corrections, this provide a huge differences in the heat content time series before 1960s, 70s, until 80s. So the maximum difference can be 40 joules. So it's quite a big change. But this is we're going to revise this because this application assume that all the bottle data has biases, but it's not true because some of the bottle data has a reversed thermometer, so they have a pressure control on the instrument, so they are less biased. So we're going to revise this, and you know, many of the bottle data are also biased. So this is bottle. XBT, we know that we are going to have this is well-known biases in the instrument, and the one much larger in the 1970s and reduced after 1980s. And now we're going to update the SAGE-14 method in this year because we find that QC also have some impact on the bias detection, because you know, if you have a lot of bad data, a lot of outliers, so you can change the statistic of the biases. So we are going to revise this scheme this year to account for the recent development of QC stuff. So mapping, we also try to resolve the conservative biases. As you say, in the ESA approach, I just take the difference between 1994 and 1971. So the colors show you the difference of 2 years. So you can see that a lot of white areas. So that is a conservative biases because the Southern Ocean drifted to the climatology fields. So the difference of 2 years are actually close to zero. And also we try to provide a more realistic covariance than the traditional Gaussian covariances, because you see a lot of contours are circle-like, like a circle, but it's not realistic. So we use the model data to provide a covariance, and that is the traditional IP method. And we also have some improvement. For example, we use the kilometers distance instead of the degree distance to improve some reconstructions in the polar regions. And also we do some optimizations on the inflation radars this year. So a little bit of tuning for the IP method this year. So it leads to, and also the climatology, we have make a big change to our climatology, because first of all, we have recommended to use the short period climatology because it has a consistent baseline at different places. Otherwise, because the baseline is different in different regions, so the dynamics is not dynamic consistent for different regions. So we recommend you to use the short period climatology to do the ocean heat content calculations. So this year we shift our climatology from 1990 to 2007 to 2005 to 2020 ago periods. And so, and also we use the kilometer distance instead of a degree distance. So you can see a lot of improvement. So the old climatology is a global up to 2,000 meters annual cycle. So you can see a lot of not really good wiggles in the annual cycle, but now the red one is new climatology, seems more physically plausible and closer to the other climatologies, as you see in the dashed lines. And also the key issue is Arctic. So we don't have many data in Arctic, but we do have data in Arctic. So in Arctic, the old climatology is it's mostly, I think, it's spurious as not correct. But the new climatology seems quite good and consistent with ESA, EM4, and ORS4 data. So that is the improvement on the climatology. And the vertical interpolation. So I just introduced this figure is by Barker and McDougall. So the black lines is observational data, black dots. So they apply different kind of vertical interpolation to the data. So you can find some differences if you use different vertical interpolations. And for some method, for example, the linear interpolation, it definitely create some biases. So this is example. So if the profile is in black, you have only 4 points in rates. So you use linear interpolation. So you can have a negative biases in the upper ocean because the shape of the profile, and then a negative biases and positive biases below 2,000 meters. So this kind of a linear biases bilinear. So previously we applied the Rennig-Ross method to temperature profiles, but now we try to use the most up-to-date P-chip method, and also we try to apply Rennig-Ross to the anomaly profiles after subtracting climatology, because temperature change is more vertically homogeneous than the profiles, so that leads to less uncertainty in the calculation. So we tried the three and uncertainty. So now I finally go back to the uncertainty calculation. So we try to use an ensemble approach to account for all the no error sources statistically. So the key idea is that the errors can never be formulated mathematically. So we have to do it statistically. And we don't use all the available methods. For example, XPT, we have more than 10 correction schemes, but we don't use all of them. We know some of them are not good and incomplete. So we only take the best 2 or 3 methods. For example, the QC, we have 3, and XPT, we have 3, MBT, about climatology, we use Verdosh and Atlas, and this is from Germany, Victus, and also vertical interpolation mapping. So this is a big framework to do. So we do different kind of combinations to account for different errors. So so because they are correlated, so it can account for the dependence of the error sources to the final estimate. But for now, we only managed to run some of the experiments. So now we use 2 QC system, WOD, CODC, 3 XBT correction schemes, 3 climatology, 3 vertical interpolation method, and use our IP mapping method to have members. And now only 29 finished. So I'm going to show the results for the 29 combinations of the runs. So the 29 members actually represent the uncertainty due to QC, due to XBT, due to climatology, and due to vertical interpolation. So that is the 4 main error sources. So this is the results. So exactly the same data processing, but 3 different climatology, 3 different XBT correction scheme, 3 different vertical interpolation method, and 2 QC method. So it is reduced to it is annual mean. So because I want to illustrate the key differences. So you can see that the climatology more or less vertical offset, and the standard deviation for the 3 different choices is 6.7 zetajoules, and the maximum difference is 35 zetajoules. So, but it's also a vertical shift. Okay. And for XBT correction schemes, as also filed by team, the main impact is on the 1980s to 1990s. So during the Argo periods, almost no impact, and before 1980s, almost no impact. And for vertical interpolation method, it's really surprised to me that the impact the long-term trend. So the trend difference for after 1960 can be 0.6 zetajoules per year. So if you use the P-chip, the new vertical interpolation, it results in about a little bit less than 10% of trend, larger trend than if you use the Rennig-Ross traditional method. So it's quite a big differences. And the standard deviation is 14 zetajoules. And for QC, as expected, we have a large differences in the Argo periods, and that is 10% difference after 2005. And before that, no big differences. So you see that different data processing and different choices do impact the heat content estimate, but their impact are different for different periods, and this is critical to say. And also the I just said that the impact of different data processing are not independent. For example, if you just use the 3 different climatology, but applied to COD-CQC and WD-QC separately, so you find that the standard deviation is 6.7 zetajoules for COD-CQC and 8.5 zetajoules for WD-QC. That means the choice of climatology, the impact of climatology on OHC is more sensitive in world ocean database QC than COD-CQC. So there are some they are not independent, they are correlated. So you have to take account of all this kind of dependency to estimate the biases, estimate the uncertainty. So that's why I think our approach is the only tenable approach to estimate the overall uncertainty for all the error sources. So this is an example. We have 29 members representing different choices of climatology, QC, XBT, vertical interpolations, but not including mapping for now. So you can see the spread of the different members, and the spread gets to less in the recent decade. It's 7 to 10 zetajoules. And before 2000, it's 15 to 2025 zetajoules. It's only for the 4 error sources. And if you compare our estimate with Boyle et al. 2016, so the climatology is more or less similar to the Boyle team's estimate, and XBT is a little bit smaller than team's estimate, and vertical interpolation QC is really important, more important than climatology and XBT biases. And so we have an OI approach. So we naturally have an estimate on the mapping approach. So we combine them together. We have 22.9 total uncertainty. If you consider the these 5 error sources, but it depends on time, right? So before 2005, it's 28. After 2005, it's 10. Zetajoules. So this number are still preliminary. So you can start to put them together to have a perspective on what happens on the different kind of data processing stuff. So finally, EEI. So this figure is up to 2,000 meters time derivative of ocean heat content versus series state. So black is series and month-to-month variation. I did not do any smoothing. So you can find that the 4 error sources that I account for does not account for the mismatch between OHC and the EEI. So OHC, the variability is too high. The 1 sigma is 6.2 to 7.4, but the series is only 0.7 watt per square meters. So it's a big mismatch. And the reason behind it, I think, is lies to both OHC and the series. And the ensemble mean actually reduce a little bit the variability, but not that much. So still have a 1 order larger variability than series. So this is month to month. So I try to calculate the annual. So this is the annual estimate of time derivative of ocean heat content compared with series. So the variation becomes very small if you just calculate the annual rate. It's closer to the series, but still a little bit larger than the series. And the uncertainty due to the 4 error sources is about 0.15 watt per square meters. So eventually, I expect that if I finally add the mapping uncertainty, add some other uncertainty source, I expect the 1 sigma error will be more or less 0.3 watt per square meters. And the heating rate, the variability, you can see that it's we still find the big dip in 2016. And nevertheless, the correlation is 0.47 after 2005. And if we don't account for this big wiggle here, 2016, 2017, the correlation goes up to 0.58. So that is quite promising to us that the new development really improve the correlation between OHC and EEI. But it's not fully resolve the mismatch between OHC and EEI. So that's why we are trying to aid the mapping and other error sources, and to incorporate all these errors to this ensemble framework. Okay, so trend. We have a little bit of trend in the new estimate. So serious trend is here. We have a more or less consistent trend increase of our hitting rate, but you say the variability is high. So I don't know the trend is reliable or not, at least for OHC record. But anyway, we now have a trend here. So summary. So I highlight the importance of QC and also biases, spot of MBT, XBT, and sampling mapping to also to resolve the conservative errors and uncertainty estimate. So a QC mapping and a vertical interpolation larger than climatology and XBT. So we are to be added uncertainty due to MBT bottle and mapping, and still a big difference between series and OHC. But I guess it should be related to the sampling and the mapping, but we need to quantify that. And I'm going to analyze the regional uncertainty. And also now the OHC estimate is monthly, but we combine 3 months together. So it is a 3 months estimate. But I'm going to try 6 months and 12 months OHC estimate, and to check what happens if I combine more data. But there is a trade-off. So if you combine more data from different months, we have better sampling. But we are going to have uneven signal distribution of data. So there are trade-offs. So to be tested if positive effect is it is positive effect or negative effect, but to be tested. So next step, I'm going to implement this super assemble approach. So I'm going to, I'm going to have around more than 2,000 experiments. So it's a matter of time. So I'm going to finish this year. Okay, good. I'm stop here. Thank you.
Okay, thank you very much. Okay, let's take the question again for the break. And we're running quite late, but let's move on to the next speaker, who is Nicola. I believe he's virtual.
Okay.
Figure out how we stop here.
Okay.
So Nicola, can you share your screen?
Yes. Can you see my screen?
Yes, this looks good. Do you want to put it on full screen?
Okay. It's okay?
Yeah, this looks perfect.
Okay, perfect.
Please go ahead.
So, hello everybody. I'm glad to present you some preliminary results on the estimate of uncertainty on global ocean state, and also with ESA-ESRIN, which is a mapping method based on optimal interpolation to map in situ data, and especially Argo data. So I will acknowledge my contributors. This is a work principally led with William Lovell from LOPS, and also with contribution from Anaïk Prigent, Jean-Marc Molines, and Thierry Pendieu from Grenoble. So basically, mapping in situ data for monitoring climate indices. Mapping method is mainly used to map data with sparse sampling. So it's basically designed to fill the gap between the data. And so since 2000 Argo data have considerably increased the sampling for each season and in every region of the global ocean. So it provides a better way to assess the global heat content, steric sea level, budget, etc. And so we have a pending uncertainty on global and regional budget, which prevent us to to close properly ocean, Earth energy imbalance, sea level budget, etc. So basically, if we gather a lot of estimate of heat content trend, global heat content trend, and steric sea level trend. Alors this is works presented earlier by Karina, which gathers estimate from different products and different groups that show many different trends. So we have a spread among the different products. For example, here we have the heat content between 0 and 2000 meter depth from over the Argo period from 2006, and we have a very large spread, which is about more than 0.5 watt per meter squares. And all the products present a different heat content trend over this period. Now, these products are from a different group that use different method, different data set, not exactly the same data set, and different approach and tuning for their methods. So the exercise could be done also for the sea level trend, so which is basically the same problem, and we also get some very large spread among the different products in the sea level. So in this talk, I will present some preliminary result on trying to explain, to understanding the cause of this uncertainty. So we have basically 4 causes, which is separated by the error due to the sampling, error due to the data quality, error due to the a priori statistics and the OI tuning, which is which be very sensitive, and also the impact of intrinsic, which basically a chaotic eddy ocean variability, which due to the sampling of the Argo over the Argo period is not well resolved by the Argo sampling. So we will illustrate some error, some mapping error due to this aliasing to the eddies. So basically the method is a ISAS tool, so it has been already presented some result earlier. So we have an optimal interpolation, which is basically described in the Gaillard et al. 2016 paper, so which is a global temperature salinity field, which is now on full depth because we progressively integrate deep Argo and in situ data. The in situ data for the ISAS 20 configuration is Argo only, but ISAS 17 there is other configuration that integrate marine mammals, Tiao, Triton, Pirata, Rama mooring, ITP, CTD, etc. So basically, the statistic and the covariance scale and weights are Gaussian function. There is 2 scale of distance of space scale, which is basically a scale, a large scale on 300 kilometers, and a second medium scale. Mesoscale, which is basically 4 times the Rossby radius. We have also a temporal scale, which is 45 days to encompass 3 months of data. There is on this map we have the climatology of temperature and salinity from ISAS 16, the previous release of ISAS, and we have the covariance scale. Now for the zonal scale, we have an increase, an anisotropic covariance scale at the equator and along the bathymetry. And we have all these scale are weighed by different part of the variance, which is for the ISAS-20, which is basically the partition of the variance for the different scale. So this is very basic optimal interpolation. And to assess this the tuning of this optimal interpolation, we have used a synthetic and ensemble approach using a model with synthetic data taken from the model at the location and the time of the historical data over the period since 1959. And this approach allows to compare the mapping of the synthetic data and the truth, which is basically the model. And this exercise was repeated 50 times for 50 members of the model, which have been ranged with the same forcing but different initial perturbations that leads to a chaotic trajectory and behavior of the model different among the 25 members. So we have 25 members of model, 25 members of synthetic data, and 25 members of ISAS. So if we compare the results as a short example on this figure, we can show the ensemble mean of the model in red, with the spread of the 50 member in pink. And we have the ISAS reconstruction for the thermospheric sea level, the ensemble mean in black, and the spread in gray. So for the mapping of the regional sea level and heat content of the ocean and the impact of the intrinsic variability, you can refer to the Williams paper in 2022. So basically, the first error which is provided along with ISAS and any optimal interpolation is basically the error that is computed from the equation of analysis, which is analyzed error, which is basically a percentage of the total a priori error of the model. And basically, this mainly depends on the coverage of the data. On this graph, we have the number of profile for the ISAS, for the Argo networks, and we have the average global percentage of variance for the temperature analysis, which is decreasing as the sampling, the number of profile increase. And if we look at the latitudinal average of the PCT var, we can see the differential decrease of PCT var, which is basically the differential time of coverage among the latitude, with the northern hemisphere earlier covered and the southern hemisphere later covered. And we have a decrease of the PCT var that is ongoing with coverage of Argo. And you can see that at higher latitude you have still uncovered region and large PCT var. So this is propagated in the heat content, for example, and using correlation scales from the ISAS model, and we can get this envelope, which is basically diminishing with the time and with the coverage of the data. So this a priori error is mainly dependent on the coverage and of the sampling of the data set. A second source of error is basically the quality of the data, which is very important for the optimal interpolation. And I can illustrate this with the issue that has been that has occurred in the salinity Argo data with the seabird problem with the seabird conductivity cells. So we have detected this spurious salinity drift due to problem in the conductivity cells. And if we translate this using the optimal interpolation. This has a big impact on the optimal interpolation. Here we have the global mean anomaly of the salinity average over the global ocean. And here we have the rate of delay mode quality control profile. So the delay mode quality control is in a solid line, and real-time plus automatically adjusted profile are in dotted line. And at the end of the period of the Argo, we have increasing of real-time profile and decreasing of delay mode profile. That is normal because we need time to properly, for the DMQC operator, properly QC all the database. And if we look at the salinity during this period, as the delay mode quality controlled profile diminish, we have an increase of the drift. We have clearly a drift in the salinity, the average salinity over the global ocean in the optimal interpolation. That is stress the fact that we need to have delay mode quality control data in the optimal interpolation, and especially for the Argo database, the operator on the optimal interpolation should regularly update their database to get the as much as possible the quality control, the delay mode quality control data to get rid of this spurious salinity drift, as is illustrated there. A third source of uncertainty, this is the most subjective one, which is basically the tuning of the optimal interpolation. So in the optimal interpolation, we can change the a priori statistic, we can change the correlation scales, and we can change the weight over the different correlation scales. So playing with these parameters, and using one member of the synthetic approach using occiput the model, we can compare different tuning of the global heat content from ISAS, occiput, and comparing to the in a black to the model trajectory. So we can see that we have a lot of difference between the model and the ISAS optimal interpolation, especially at a small at a monthly time scale. We have a lot of variability which is not seen in the model, which is probably due to aliasing to the ADs and maybe some too high sensitivity to the individual data. And if we look at the trends, the heat content trend, we have basically, we will integrate in the period 2008 and 2015, without the period with low data coverage of Argo network, and we can play with different tuning of and different correlation scale to adjust the trajectory of the ISAS model to get the best trajectory. So this is a comparison that show we can have a large spread only due to the tuning of the optimal interpolation. And to finish with the third source of uncertainty, which is the most which is important in the framework of the Argo, because Argo is not designed to resolve ADs, the mesoscale ADs. So we have around the different member for different the 50 member for ISAS using the 50 member of the synthetic profiles, and we get this this evolution of global heat content and thermospheric sea level with the associated trend over 2 periods, and that we can see that the first is that the spread provided by ESA by the optimal interpolation is much larger than the spread among the different models. This is mainly due to the chaotic, to the eddy, mesoscale eddies hill mapping. And there is also difference in the trend that could be due to both the eddies and the small scales, the mesoscales and the short time scales that could alias the variability. And so if we compare the trend among the model in red and the ISAS in blue, we have a slight underestimate of the trend in the ISAS with the ISAS mapping. And here is the spread among the different members, and we can see we have a large spread, which is explained by the mesoscale. So to conclude, we compute a global budget from in situ measurement necessitate analysis tool with a priori hypothesis and caveats. The source of error are identified, method, data quality, a priori statistic, and intrinsic variability. So a synthetic approach helps to better constrain analysis parameter and also to get consistency among the different state variable, which with the same analysis of temperature salinity, we should provide a consistent sea level rise and also heat content change. So the perspective for this work are the ESA CCI sea level closure budget project, which we led this improvement using using the synthetic approach for the two next year in the framework of this project. So thank you very much. This is all I have. And I can answer question.
Thank you very much, and thank you also for staying on time. So we are very late for the coffee break, so we should break now, I think, and you can probably virtually address any questions that you might have for Nicola. But I think we'll have the break now. What are we going to do with the duration of the break? Like, when are we coming back? Who is the boss? How long of a break are we going to have? Right. So here we are going back at 35. So yeah, we'll all be back here at 35.
The techniques to measure the EEI. The first talk is from Matt Palmer from UK. So can you share the screen and study?
Yeah.
Okay,
Can
we
you
see the.
see everything?
Can you make it full screen?
Yeah, I tried to do. Is that working? Maybe like that. Is that good?
Okay, that's okay.
Perfect. Okay, thanks.
Done.
Great. So thanks for the opportunity to talk to you all today. Thanks to the workshop organizers. Sorry I'm not there in person. It would have been great to have been there in person to talk to you and have some discussions in the margins of the meeting. But anyway, so I'm here to talk today about a new initiative that we're just kicking off. So we've only really started the planning for this in the last few months. So this is an initiative led by myself, Kachi Dominguez, Donato Giglio, and Didier Monsalison. So really, this is about trying to come up with a coordinated effort to assess the mapping methods that we use to reconstruct ocean heat content changes. And actually, the first three speakers of this session have done a brilliant job in kind of setting the scene for me and kind of mentioned many of the things that I'll go on to talk about in this presentation. So these images on the front here are just to remind us that really the focus of this is really on the in situ OBS and the in situ based reconstructions, but the use of synthetic OBS is, of course, a wider concept and can be applied to different things too, and that's something we'll probably come back to in the discussion, I expect. Let's see if I can advance the slide. Okay, so very briefly, that I'm going to give a bit of motivation and background. I'm then going to show a couple of results from a paper that was published in 2019, led by Leslie Allison, which kind of showed, was a kind of a very first pilot study where we tried to use this synthetic profile approach. And then I'm going to talk about the project that we're talking about here. So I'm going to refer to that as ME40H, just as a shorthand. So we're going to talk about a kind of initial proof of concept study and then talk about the future plans. And I think that's somewhere where it would be good to think about how this effort can link into and complement kind of existing activities that are already kind of ongoing within this general area. Okay, so this is a nice figure from Li Jing's review paper that was published quite recently. Here's my kind of view on why I'm interested in kind of ocean heat uptake, and it's clearly, both the heat uptake and the variability is fundamental to our knowledge of past and future climate change. I think there's obviously the Earth's energy imbalance is what we're here to focus on today, but there are many other applications for why we care about this kind of information. So that includes detection and attribution. I think an interesting one is the forecast initialization for either seasonal or to decadal forecasting. We talked a lot about the sea level budget earlier today in the first discussion session. There's things like constraints on projections. So in the latest IPCC report, there was a much bigger kind of emphasis on using these emulator type kind of projections, which really rely on having observational constraints to help with that process. So it kind of emphasizes the importance of the observations in projections. And I think a really key one for me is really going back in time to try and understand a little bit better what the past radiative forcing is. And that's kind of something I was quite involved with in IPCC. So, when we take these observational estimates, as previous speakers have shown, there are lots of differences in terms of the trends. There's differences in terms of the variability, and there's differences in terms of the estimated uncertainties. Okay, so I mean, this is a plot that I like to show. I think it's good to remind ourselves that ocean heat content's really got this very strong kind of relationship with EEI. So it's one of the most powerful kind of observations that we can make. Whereas we find that when we look at global surface temperature alone, it tends to be a weak constraint on the EEI on kind of decadal timescales, and so the kind of benefit of ocean heat content is that it's a more direct link to what the radiative forcing is doing. And so it's potentially very helpful to kind of understand past changes in radiative forcing. And then you've seen this figure several times before. So this is from Karina's most recent paper, but the key point being that even during the well-observed kind of Argo era, we see substantial spread in the rates of ocean heat content change. And so we want to understand why that happens. Okay, so I kind of just listed my sources of uncertainty, but other speakers have actually done a really great job of talking about this in more depth. So essentially, I mean, I just wanted to note that while we're going to focus on the mapping methods here, there are other sources of uncertainty. I probably won't dwell on this. I think some of the other speakers have gone into much more detail and provided more comprehensive information on that. And then I just wanted to note, really, I just wanted a bit of motivation. So from Tim's paper in 2016, really, we know that the mapping method is one of the important sources of this uncertainty. And for the periods that they looked at, it was generally the largest individual kind of source. And when you look at what the observing kind of kind of sampling was back through time, it kind of becomes fairly obvious why that is the case. Certainly pre-Argo. So this is a paper, a figure that was published. I published in a kind of review paper a few years ago. It's actually based on the EM4 data set. So thanks to Simon Good for the figure, but it just shows how much work has to be done to translate. So this is the 0 to 700 meter kind of layer, how much work has to be done by the infilling kind of methods in order to construct a globally complete field of, global ocean heat content. So they obviously got to do quite a lot of work in these early years. That has changed a lot over time. And of course, during the Argo era, it's a very different picture where there's much better spatiotemporal kind of sampling characteristics. So I wanted to kind of flag up some of the other recent papers that have kind of looked into this. These are useful things, I think, to go and have a bit of a closer look at. This is a recent paper by Savita et al. So this was published in the Journal of Climate. I know many in the room will have been involved in this paper. But as well as the integrated quantities, it is interesting to think about the spatial patterns and how they manifest and where that, where that spread is largest. And so we kind of know that it's really these energetic kind of frontal regions where we get the largest kind of discrepancies in the mapping methods. I think this relates to some of the comments that have been, or other speakers have kind of referred to the presence of eddies and how they can introduce noise. And I think this is kind of giving us a similar kind of message that, it's kind of critical what you do in these areas of strong kind of horizontal gradients where the eddies can really make a big difference, or the exact placement of an Argo float can make a big difference on what the, on the sampled ocean that's kind of taken to be representative of the larger body of water. So then I just wanted to, highlight a few questions that we're kind of interested in. So, how can we evaluate which mapping approaches are most suitable for a given kind of application, kind of noting that there are different things we might want to do with this. How can we determine whether there are systematic biases in our observational ensemble of opportunities? So while there's systematic biases, I think one of the really interesting things is looking at the series kind of OBS, and I think comparing that to the ocean heat content is giving us some kind of indication that there might be systematic biases within the whole set. So that's something we're interested in exploring more. And can we independently evaluate the uncertainties provided on integrated ocean heat content time series? So really, I think many of you will be familiar with the concept of synthetic OBS, and Nicola's presentation obviously kind of showed a very nice application of this, just before the coffee break. Essentially, this is about, using climate or model ocean kind of simulations as a test bed for mapping methods. And this is, essentially all we have to do is kind of sample those modeling systems, those closed modeling systems like the observations, and then we can map them in a similar way as we would the observations. But the critical thing is that we have a known model truth, so we can compute a perfect kind of integral of global ocean heat content or some other quantity. And that's the thing that's been missing in some of the evaluation and the kind of intercomparison projects to date, is it's very hard to be objective about whether some mapping methods are, have particular strengths compared to others, and whether we can kind of, try and benefit from their different capabilities kind of collectively by learning how well they're doing for particular kind of applications. One of the things I'm illustrating here, oh, sorry, I've skipped on one. One of the things I'm trying to illustrate here as well is the importance of the underlying model resolution for this kind of exercise. So we know that the 1 degree kind of oceans are probably not much good for this kind of thing, because they don't really have any kind of representation of the turbulent ocean. At a 1/4 degree, we kind of get some of these turbulent features, but it's really, if we increase the resolution again, then we get an even more realistic looking kind of patterns. And that might be quite important when it comes to evaluating what the spatial kind of uncertainty, or the mapping uncertainty in the kind of is, and the amount of noise that gets introduced by this limited sampling that we have of the real world, of course. Okay, so just very quickly, some initial results. So this is, I mean, this is a paper where we tried to make the case for this kind of approach, and I'd encourage you to go and have a look at this. It's not a very long paper. So the things to note is this is an idealized, very much an idealized model setup. We have a quarter degree ocean, but we're only using monthly mean data, so we're not really doing the temporal characteristics quite right. And we're also kind of using perfect climatologies, and we're getting model covariances computed from the full field model information. So that means we're giving our mapping methods, those that use the global covariances, the best possible chance of kind of reconstructing the observed signals. I think one of the nice things that this paper kind of illustrates is if you look at the model truth in black, you can see that both of our mapping methods, so one's a more traditional kind of local covariances method, and one is a more sophisticated kind of global covariance method, which is initially based on model covariances, but then it kind of it ingests the available OBS and tries to recompute those covariances in a kind of iterative process. And you can find out more. I don't have time really to get into the details in this presentation, but the point is that both of these kind of on-the-shelf mapping methods we had available to us, you can see that the sampling itself of a turbulent ocean really does kind of introduce quite a lot of spurious variability into the reconstructed time series. And I think this is one of the challenges, you know, of comparing these the derivative of you know, ocean heat content and comparing that to series. I think it's this turbulent ocean which introduces a lot of noise, and so some type of smoothing is clearly going to be beneficial, and other commentators in the workshop have kind of mentioned that. We can see that in this paper we don't capture the long-term trends kind of either. It's kind of very difficult to get at the below 2,000 meters trends. You can see that actually the model truth evolves pretty smoothly, actually much more like the series kind of data than the ocean heat content OBS. So I think there's, you know, some interesting scientific insights into this approach. Another kind of, I think, almost incredible thing is when we start to look at the spatial patterns. Like, some of these methods are really very good at kind of getting at some of the spatial patterns, even with a very small amount of data. And so it's intriguing that, you know, there may be potential to go further back in time. So, you know, the whole question of how many observations do we need to really constrain some properties, the large scale patterns. I think this is really important when we think about the development and evaluation of decadal forecast systems. It's critical that we can initialize those systems and carry out some kind of evaluation of them. Okay, I'm just having a quick look at my time here. Okay, so essentially this showed, I think this initial study showed some great kind of, or some very promising results. And essentially what we really wanted to do is take this kind of approach, but apply it to a much wider group of mapping methods. And that's what this, really what this ME4OH initiative is all about. So, as I say, we've only really been doing this for a few months now, and we've really been trying to get together a first kind of test data set. So this is Didier who's done a lot of the work for this. But essentially what we're proposing to do is use a 1/10 of a degree model that was run at CSIRO. So this is an ocean model, an ocean only model, but forced by the JRI 55 reanalysis surface forcings. So it's superior to the Allison et al. Study in a couple of ways. It has a high resolution model, so that'll be interesting to see what difference that makes. But the other thing is that the temporal resolution is much better. So the synthetic profiles are based at daily resolution now, so much closer to what the actual observing kind of temporal sampling is like. The simulation period is 79 to 2014. So yes, and this is just kind of an image to show you roughly what some of the variabilities kind of look, well, some of the sea level trend. It's really just to show you that we are doing a reasonable job within this simulation of getting some of the mesoscale kind of characteristics and kind of spatial patterns. So this is some diagnostic plots just to show that, you know, Didier's been through the process of kind of extracting for various you know time periods. So this happens to be August 2008. He's got these various kind of diagnostics plots, but there is a synthetic profile data set ready to go. There's a bit more kind of information there again, I'm kind of glossing over this a bit. I kind of want to get on to what we're kind of doing and what we plan to do next and how people can get involved if they're interested to. So we've begun, as I said at the start, we've begun to reach out to potential contributors, and some of you in the room would have been contacted by us, I'm sure. We're interested in both the mapping, people who run mapping methods, but also people who generate synthetic OBS. So it'd be great to have the kind of occupant data as a synthetic profile data set in kind of due course. Our initial focus is on off-the-shelf kind of in situ mapping methods, such as those reported in BAM State of the Climate and the most recent von Schuckmann et al. Paper. That doesn't say that other things aren't kind of in scope. So you could imagine expanding that to ocean reanalyses, or some of these are kind of data assimilative approaches. But I think in this very first tranche, we're just going to do the kind of lowest hanging fruit and the easiest thing that we can do to show benefit of this kind of approach. There will be a consultation process to refine experimental protocols. So that is expected to take place on Monday, the 10th of July. So if you're in Berlin for IUGG and you want to come to that, please let us know. Then we expect to have a much more comprehensive workshop later this year or next year. And then a kind of initial aim is really thinking about the mapping uncertainties. So yes, please contact us if you'd like to get involved. In the longer term, I think it's important that we throw a number of synthetic observation data sets to ensure robust results. We'd also like to develop more comprehensive experiments. So, and there's almost, there's a very large number of things that you could look at, but here's a few kind of examples that I kind of am particularly interested in. This approach of, can be expanded to other variables. Could even, I think, use the same framework to look at kind of the biases and the data QC aspects that several people have talked about. And then a big one for me in the long term is really to think about how we can try to evolve or use this information to help inform the development of the global observing system. And then, of course, at a meeting like this, it's, I can't resist thinking about how we could combine multiple, so not just the in situ, but think about all of the observational kind of elements that we have. And Benoit's kind of mentioned this a couple of times. But are there ways of combining a wider range of Earth system kind of observations to get the best kind of estimate? And the rise of machine learning type approaches is particularly attractive for this kind of problem. And I think I will leave it there. I guess the last thing I should say as well is that we're obviously interested in seeking funding kind of opportunities. As Benoit mentioned, this is no small task. We can do a proof of concept based on best efforts, but really for the longer term, we'll be looking for funding, kind of dedicated funding sources to fund this type of work. So thanks for listening. Please reach out to us. There's a few more details in these papers if you're interested. Thanks.
Okay, thanks, Matt. Questions? Okay, Benoit.
Great. Thanks, everyone.
Thank you, Matt. Very, very interesting. Benoit speaking. I was just wondering, will you use just one model, or would you accept some other synthetic data? Because I was just thinking we may develop also synthetic data from another model on our side, which will have a special ensemble with the intrinsic ocean variability, and the synthetic data we intend to develop will be developed for Argo, of course, but also for sea level and GRACE, so we can compare with the sea level budget. So we would be very interested if you could look at this data to have an idea of the mapping, because we will work with ISAS. It's just one mapping, and I'm just wondering the effect of mapping. So do you open the possibility to use other synthetic data that we could provide to you?
Yeah, I think really we just wanted an initial data set to kind of have a first walk through. I think that if there's another synthetic observation data set that's kind of ready to go that we could immediately use or use with relatively little effort, then I think we could talk about doing that. We should talk more about doing that. I think in the longer term, it would be really good to talk about how we can coordinate these things and do more comprehensive type studies. But yeah, I mean, I guess yes is the short answer, and we should talk more specifically about how that might work.
Yeah, that's a good idea. We probably have to make all the different efforts consistent with each other. Will you be at the end of the workshop for the discussion, so we can try to set up a first idea on how we can bring the different efforts consistent with each other?
I can do my best to be there. Yeah, I will do my best to be there. I've got quite a busy week because I've kind of just moved into more of an observational role from the sea level projection work that I was doing previously. So I'm not quite in my full observation mode, but I'm hoping to engage much more with this community, in the next month, in the months and years. But yeah, so if you give me a slot, I'll do my best to kind of be there. Yeah.
Okay, thank you. In any case, we can catch up with you afterwards.
Great, thank you, Benoit.
Okay, probably we need to move to the next talk. It's Michael Cosella. Okay.
Let's see if I can get my slides here. I forgot to put them during the break. I was still focused on coffee, but I think we'll manage. Maybe not. How do I get to the USB stick? Here. Yes. Okay. What do I do now? All right, so thank you very much. So I'll be talking about work we've been doing on mapping Argo data, especially ocean heat content. So the first thing I should point out, this is all joint work with Donata Ciclio and one of my students, Tia Sukianto. The second thing I should point out, I'm actually a statistician, not an oceanographer, but I've been working on Argo data for many years now, so I know some of these things already. But you're the experts on oceanography, and I might know something about statistics. So, all right. So we will actually have 3 talks on the work we've been doing. So we split this into 3 different contributions. So I'll be outlining here the general mapping approach that we are using and presenting our results for global ocean heat content. You've actually seen some of our curves in the previous talks already. So it's been the Kuusla and Ciclio curve that is done using these methods that I will describe. Then in the next talk, Tia will talk about an extension of this approach to better handle the vertical structure of ocean. And then in the last talk of the session, Donata will talk about regional estimates we get out of this new product that we have. And one of the taglines or the key points here is that we can provide uncertainty. So, I don't know what that other cursor is, but anyway, so one of the key points we have is that we provide kind of statistically rigorous uncertainties on these maps. And in the program, Donata's name was wrong in the printed program. So the last talk of the session actually is by Donata. So that will be also part of this set of 3 talks. Okay, so we all know that in order to do science with Argo, we need to produce discrete data products. And basically this means that there's statistical modeling involved. We are statistically trying to map the sparsely observed data to a regular grid. How do you do that? There's many ways of doing that. And the approach that I personally like, and many others also have found very useful, is to approach this problem through local mapping methods. So already for a long time, there has been local methods for the mean field, going back to these papers by Ridgway et al. And Remick and Gilson, where you use basically local regression to estimate the mean field, meaning the climatological field. And then what I proposed back in 2018, it would be to do the mapping of the anomalies using also local models, and especially locally stationary Gaussian processes, which basically just means that you do what you call objective mapping or optimal interpolation, but you do it using these local moving windows, and you do it in a way where we use the data to estimate the decorrelation scales. So these local models have a lot of benefits. Specifically, it's easier to define local models than global models, and so they basically allow you to account for the non-stationarities of these fields, and they make the computations fast as well because you can fully parallelize. So we map many things using these methods. Here we are especially going to focus on the ocean heat content. So we want to get this time series of ocean heat content, which basically means a 3-dimensional integral of the temperature field with some scaling. So the first thing you notice is that out of these 3 integrals, you can actually compute the vertical integral very easily because you have the vertical profile. So this first integral we actually get for free. We basically do a PGP interpolation of the vertical profile, then we integrate that. And then at this point, we have this kind of vertically integrated heat contents from the profiles. And then we need to do spatial mapping to infill the gaps over space and time. So that's where the mapping part comes in. So especially what we do, we kind of, I have here kind of 5 steps of what we do. So the first thing we do is that since we do these vertical integrals, so it's a problem for us if the profiles stop before they reach to the bottom of the section you consider. So because of this, we divide the ocean into 2 sections. We can do more, but for this talk, we'll have 2. So we have sort of the upper ocean section, which goes basically until 975 meters, and then from 975 more or less to the bottom of the Argo sample depth, the range of depths. And that division is done based on data availability. So there's actually much fewer profiles in this mid-ocean section than in the upper ocean section. So that's why we divide it in 2. And then we do the vertical integral first. Then we need to do horizontal mapping to infill the gaps. We do the mapping using these locally stationary Gaussian processes and local regression for the mean field. One difference between us and some other products, including, for example, the Scripps product, is that we add a climatological time trend to the local regression. I'll show you that in just a second. And I'll show you that makes a difference. And then we map the anomalies using locally stationary Gaussian processes, where the kind of the key point is that that we use the data to estimate the decorrelation scales. And this is something that's entirely standard in spatial statistics. In the oceanographic community, this has been less standard, but this can be done. It actually provides kind of very nice estimates of those decorrelation scales, as I have shown in some of the previous work I've done. And then we finally one of the novelties in here is that we can quantify the answering of these fields using local conditional simulations. I'll talk about that more also in a second. So that's the outline. So let's talk about the details. I'll probably need to skip a lot of details here, so I'll just give you very rough kind of pointers here. I hope the slides can hopefully be shared afterwards, or we can also discuss later. But anyway, so for the mean field, meaning the climatological field, we use the same approach as Remick and Gilson, so basically this kind of local regression model, where the only difference really is, well, there's some other technical difference, but the main difference is that we allow for a climatological time trend in these local regressions. And I will show you in a second that this actually makes a difference. And then for the anomalies, we use locally stationary Gaussian processes, which basically means that we use this kind of moving windows for doing the mapping. So we basically, let's say if you want to get a mapping at this location here, let's say this is my grid point, I want to get the mapping there. We look at a local window both over space and time. Then we assume that at this point we have already removed the climatological mean field, so we look at the residuals that are supposed to be mean centered at this point, and we assume that they follow a stationary Gaussian process within that local window. And from that assumption, it's an assumption about the statistical model. From that assumption, we can estimate the covariance parameters, which you call the decorrelation scales, using maximum likelihood estimation. This is what I proposed in this 2018 paper. We showed very clearly that this leads to better mapping, including the actual maps and the uncertainties that you get from the maps. And many others have since found this to be a very nice approach for doing the mapping of the anomalies. So that's the approach we are using here. No major changes with respect to this earlier work in this part of the mapping. And then, so we estimate the local decorrelation scales using maximum likelihood. And then when we move to the next window, so let's say here's my next grid point, we re-estimate the decorrelation scales. Oh, my mouse is moving around. Oh my God. Okay, let's put this away. So when I move the next window, we re-estimate the covariance parameters. They're going to be slightly different because some of the data is shared, but some of the data is new. So we get kind of this locally estimated, locally most relevant data-driven decorrelation scales, basically according to what kind of dependencies you seem to see in the actual observations. So we don't need any ad hoc choice. We don't need any choice from a model. It's entirely from the Argo observations using basically standard spatial statistical techniques. And then we do these local moving windows. We do allow the windows to overlap. This gives you kind of smoothness both in the decorrelation scales and in the final maps that we get out of this. just quickly about the covariance that we are using. So we are using an anisotropic spatiotemporal covariance. So we have time in here, which is also different from some of the other techniques. And we have these different decorrelation scales for latitude, longitude, and time, and which we estimate from the data. And again, for each grid point, we have a different moving window. So basically, for each grid point, we re-estimate the parameters. So altogether, in a 1-by-1 grid over the ocean, we have some like 30,000 estimates of these parameters. This is one visualization of what that looks like. So I'm showing the estimated correlations at a fixed spatial lag for the upper ocean heat content fields. And what you can see here, which probably makes a lot of sense oceanographically, is that you see longer range dependencies in the equatorial regions and shorter ranges towards the poles, with also some other variations in the spatial structure of these decorrelation scales. We have similar plots for the other parameters. I'm just showing one here. And in this 2018 paper, I showed that this kind of an approach really helps in terms of the mapping. So here's just some examples of what these maps look like. So if you stare at this for a second, you'll see that these are clearly anisotropic. They are clearly non-stationary, meaning that you get different dependence structures in different locations, and hopefully also kind of make sense oceanographically in terms of what we expect. All right, so how do we then move on to the ocean heat content? So in order to do that, we of course now need to integrate these spatial maps. And if you just want to get the actual value, that's very easy. You just take the map and integrate that. So that's easy. But then the thing that is more difficult is what if we want to get uncertainties on these ocean heat content values. So the issue here is that now we need to integrate over this spatial field and get the uncertainty on this integral. The problem is that uncertainty depends on the correlation in the mapped fields between two different locations, and also over time, if you want to get the correlation over time. So in principle, if you want to get the rigorous uncertainty on this quantity, we would need to have access to basically the really high dimensional covariance matrix that you have between different map locations and also over time, which is completely intractable. In fact, something we cannot even get out of the local model very easily. So that approach is not doable. However, what we can do instead is that we have this new approach that basically enables us to sample from that conditional distribution of those fields. So basically the idea is that if we go back here, for each of these maps, there's an underlying high dimensional distribution. Here we are assuming things are Gaussian. So there's some high dimensional Gaussian distribution over these pixels. These maps are the mean of that Gaussian distribution. So whenever we produce these maps, we are really just mapping or showing the mean. But that distribution, of course, has a spread around that mean and correlations. So what we do in these local conditional simulations is to simulate from that high dimensional distribution in such a way that those simulations have the appropriate correlations over both space and time. I have the algorithm here. I will not describe that in the interest of time, but I'm happy to talk about this, and hopefully we can also share the slides. But I'll just show you what it looks like. So here's one of our anomalies. So this is the conditional mean. This is the mean of that high dimensional Gaussian distribution. That's what we usually do when we plot maps. So now what we can do is we can simulate from the distribution around that mean. So here's one of our conditional simulations. And when you look at this for a long enough time, this actually is dependent over space, and we also do this in a way that is dependent over time. So here's one ensemble member from this ensemble of these conditional simulations. Here's another one, and here is a third one. So we can keep doing this, and these are all sampling from the distribution, the conditional distribution of these fields given your data, and it's these ensembles that really reflect the answer, the allowed range of these maps. Like normally when we do the mapping, let's go back here, we just look at the mean. But if we really want to understand what is really the allowed range of these maps, you really need to look at that ensemble. And that's what we do. So that's the approach for answering quantification. One other thing I want to briefly mention is validation. So this is also something I haven't heard in this meeting so far. But there has been a lot of discussion about validation with models, and that's also all fine and good. But there's also a way to do the validation just using the data. And this is a statistical technique called cross-validation. This also actually goes back to a 2018 paper where I did this for the first time. So basically, so what you do in cross-validation is that you basically leave out floats one at a time. Then you remap to that left out location. You get your kind of mapped value there, and then you compare against the left out data. And the idea is that, you know, if you're mapping well, or if there's some systematic biases, you should see those in those cross-validated errors, basically. You can do it actually in two different ways. You can either leave out one observation at a time, or you can leave out the full float at a time, and we are doing both. Usually we find very similar results for both. And then, of course, none of this would be very useful if you don't have software. So another thing we are developing right now, and this is really something that Tia, my student, is leading, is to produce kind of a reproducible software pipeline that is modular and extensible for basically mapping purposes. Not just mapping for ocean heat content, but generally kind of mapping of in situ data. This is work in progress. You see here some of our code and some of the diagrams we have used to kind of sketch out like all the different parts and you know what goes there and the kind of the interfaces between the different parts of the pipeline. So this is something in progress, and hopefully we'll have this. We'll basically launch this at the same time once we also have the paper ready on this. So in the rest of this talk, what I want to show you are basically the ocean heat content results globally. So Donata will be showing the regional results we get out of this, but I will just here focus on the global results. So I will focus on three questions. So the first question is what difference it makes to have that trend in the local mean field. The second question is what difference it makes to add time to the covariance structure. And then the last question is what do the answers to this look like? So the first question, what difference makes to add the trend to the mean field? So here's the first plot for that. So what I'm showing here are the different estimated ocean heat content time series for the mid-ocean section. So this is the deeper section. This is where we expect the most trouble because this is the more sparsely sampled section. And what you see here is basically the different curves, the kind of the red and the green are the ones where we either add the linear or quadratic time trend. We usually don't really see much of a difference between linear and quadratic. And you see that, you know, we get estimates for those. And then you see that if we don't add those, so those are the blue lines or the no trend estimates where we don't add those extra terms, you see that you get this kind of much slower, a much smaller trend. And why is that potentially happening? Well, kind of what is happening, and what also has been described in the previous talks, when there's gaps in your array, you get your maps revert back to a mean field. And if you have a time constant mean field, basically what ends up happening is that kind of here at the later years, you get like a bias downwards, and in the early years, you get a bias upwards, and as a result, you get a smaller trend. And we see this is a major impact in the deeper section of the Argo sampled ocean. And we also, I have here the RG is my reproduction of Remick and Gilson. So this is not the actual Remick and Gilson, but it's something that's basically trying to take their paper and reproduce what they did. And you see that it has the same problem because it doesn't have the trend in the mean field. So then, of course, the question is that, well, okay, so we see this difference, but can we somehow say that, you know, which of this is more correct? And that's where the cross-validation comes in. So on the next slide, I have our cross-validation results. And I probably won't have time to describe this in great detail. I'll just tell you how to read these plots. So the way you read this is that if you see a trend in these plots, that would indicate that there is an actual bias in the mapped fields as shown by the cross-validation. So basically the cross-validations would show that I'm either downward or upward biased, then I leave out data if I do the mapping in a certain way. And what you can see is that the no trend lines always have a bias in every way we do the cross-validation. So this gives very strong and I think clear evidence that these curves here where you don't have the trend in the mean field are actually downward biased. And this was entirely from the data, like not from a model. This is entirely from the Argo data. And I think it shows very clearly that there is a kind of a underestimation of the trends in potentially some of these products. And I think this kind of a spread would potentially explain some fraction of the spread we have seen in many of these plots where you see the spreads between products, because there are differences in terms of do you do this or not. This effect is a little bit less pronounced if you go to upper ocean because it's better sampled. We do see still an effect, there's still an effect, but it's less pronounced. The cross-validations look similar. It's similar conclusions from the cross-validation. So next question, what difference it makes to add time to the covariance? So Here are two time series. On the left, we have our ocean heat content anomalies without the time in the covariance, so just space-only mapping, similar to what Fromig and Gilson, for example, are doing. And on the right, we have our maps, which have the time in the covariance, where the decorrelation scales, again, estimate from the data. And the first thing you see is that the right plot is much smoother. You see it seem to have like less of this kind of potentially spurious fluctuations in there. So you get this kind of additional smoothness in the time series. So then the question again is that, is the right plot really better? Is it really a more realistic kind of estimate of the actual true heat content or not? So how can we potentially quantify that? So that's again where the cross-validation comes in. So here's again our cross-validated errors as a function of the different methods and as a function of time. And what you can see is that consistently you have higher errors as shown by the cross-validation for the models that don't have time in the covariance versus the models that have the time in the covariance. So again, this shows, I think, very clearly that this time series on the right is not just kind of smooth, it actually is a better reconstruction of the underlying truth. And we can do similar things for other depths and so forth, but they kind of consistently show the same result that yes, adding the time there actually gives you better maps. And then the final question is about the uncertainties. And I think this is sort of in some sense the most novel part of this work. So again, we do it using these local conditional simulations, and what we do, we produce those fields. We do a few hundred ensemble members, and then what we do is that we basically integrate those each of the ensemble members to get like a kind of an ensemble of ocean heat content values, and then we look at that spread, and that gives us the uncertainty. So the first plot I'm showing here, I'm showing the ocean heat content anomalies, where I show in edits for the upper ocean. In black, I'm showing the conditional mean. So this would be just, if you just take the mapped fields and integrate those, you get the black curve. And then around that, you see these gray curves. So those are the conditional simulation ensembles. And really, the way you use this is exactly the same way you use climate model ensembles. They reflect basically the distribution around the mean as implied by the model and the data. And if you look at this very carefully, you actually see these are done in a way that they're temporally dependent. So they actually are correlated in terms of these ensembles. So what we can do is that, we do this many, many times. We do a few hundred of these simulations. And then from that, we get error bars. So this figure is now showing our 68% and 95% error bars around the monthly ocean heat content anomalies in the upper ocean from Argo. And what you can see, I mean, for example, one thing, there has been a lot of discussion about the 2015-16 El Nino and what's going on in there. So if you look at this, you see very clearly what is going on. So what is happening here is that there was a positive anomaly during the El Nino phase of that oscillation. And we can see from here, this is statistically significant. Now that we have the error bars, we know that this is statistically significantly positive. And then what happened when the ocean moved to the La Nina state, there was a big loss of heat, and you get a statistically significant negative anomaly. And it's very clear in this time series, and to the extent that we trust this answer, it's a very kind of clear signal of basically an accumulation of heat during this time within the Argo sample part of the ocean, and then a huge loss of heat during this time. Of course, then there's a separate question, where did the heat go? But that's maybe for your community to think about. And then finally, we can get out of this also answers on the trend of the ocean heat content. So basically what we do, so here I'm showing the full time series, including the seasonal cycle and the trend now. There you see we have these error bars around the actual ocean heat content values. So you see that there's a sizable amount of uncertainty around these actual values. And then again, we have underlying all of this, we have the ensemble of conditional simulations. So what we can do is that we simply fit a line to each ensemble. We look at the spread of those lines, and that gives us an answer on that trend line. And the final answer we get is down here. It's about the 5% uncertainty. And in case someone is wondering, this is normalized to the ocean mask we have. So that's why the number is a bit different from the EEI numbers we have seen. But this is right now for the normalized to the Argo sampled ocean, the estimate of the trend and its uncertainty for the ocean heat content. And that brings us to the end. So just to maybe quickly summarize, so as many people have said, these Argo mapped estimates are sensitive to the choices you have made, but those choices don't need to be arbitrary. I've shown some of the ways you can reduce that arbitrariness. Of course, there are still choices you need to make, but you can try to be less arbitrary about some of those. We described our approach. Maybe I shouldn't kind of summarize it here, but you have the summary there. We have 2 more talks coming up on this. So we have done a talk about what we see regionally, and then there are many ways we can improve on this. For example, we have this recent paper where we did this kind of mapping for ocean circulation. We have a few novelties there which we have not yet implemented for ocean heat content. So there are actually things we already know we can do better. Then Tia will talk about the multivariate extension of this, and everything here is Gaussian, so there's a big question of how do you do the non-Gaussian version of these things, but it's all very interesting and there's a lot of things to be done. So I'll finish here and happy to take questions if there's time. Thank you.
Okay, so questions? Okay.
Thank you. Very nice presentation. I'm wondering if you were trying to go back to the historical period where there is no Argo and the sampling is a lot sparser and concentrated over some lines. Given how data-driven your method is, I'm wondering if that will work out well, or if you want to comment on that.
Yeah, so I wouldn't, well, I mean, one needs to be careful with the historical estimates, but in principle, the concern you're raising, I think is not an issue because basically the modeling assumption is that the anomalies for each year are replicates from the underlying Gaussian process. So what would most likely happen in that case is that basically it would just use the, like when you do the maximum likelihood estimate, it would mostly use the recent data to estimate the decorrelation scales. We are assuming that decorrelation scales don't change over time. That's of course another thing that one could maybe consider relaxing. But within the assumption we are making right now, I think there shouldn't be a problem because it would basically just use the modern data, and it might get some extra benefits from the historical data, but it's so sparse. But that really the information is in the modern data.
Okay, Benoit.
So my question is related. So I didn't get exactly. So you didn't show how the correlation is changing with time. I was curious if it's changing a bit. And my question was, if you're using recent data, and if it shows you like decorrelation scales which are small in space, how do you do when you get at the beginning of Argo and maybe in the past where you don't have data within this distance? And so how do you just go back to the trend?
Yeah. So one thing to notice is that so those decorrelation scales should not be adjusted to your data dense. Like the decorrelation scales, at least the way I see it, or a statistician would see it, they reflect the underlying physical process. So they should reflect the underlying scales of the physical process, which if we assume that the correlation structure doesn't change in the physical process, then you would have basically time constant decorrelation scales, which is our assumption right now. So yeah, exactly. That what would happen is that if you go to early times when it's very sparse, you would basically just revert to the climatological mean because simply, I mean, if your realistic decorrelation scales are short, then putting an observation here doesn't give you information here. So really, the right thing to do is to go to a climatological field. And then, of course, it's a question about the uncertainties. I mean, basically, your best map is the mean, but then you have a big uncertainty around that mean, and really it's really a question of uncertainty quantification and understanding that really that mean is having a huge uncertainty around it in terms of what the true value of the field was. Yeah, I mean, hopefully does that answer your question?
Yeah. But that means that now in your mean, because you add the trend, your best estimate is the trend.
Yes, that is true.
Okay.
Yeah, I mean, so exactly for that reason, I would be very cautious about going to the historical data. I mean, yeah, at the end of the day, if it's sparse, if there's no information, then there's no information. You cannot like kind of make up information. So I mean, I guess we are maybe considering at some point looking at the historical data, but we need to be very careful in doing that because yeah, that's exactly what would happen. That trend would just be extrapolated to the past, basically.
Any more questions? So I do have one quick one. So you separated the layer by 2 around 1,000 meters. So what happens if a profile just goes down to 1,500 meters? How do you deal with the deeper layer?
Yeah, so right now what we do is that so if you have a profile which is, let's say, from the surface to 1,500, it would only enter in the map for the upper layer for us right now. Because the problem is that when we do this integration, we cannot really handle profiles that only sample half the layer. So the solution will be to do more layers. I mean, you don't need to add too many, at which point you kind of end up in a situation where, you're not kind of throwing out too many observations because of this. But yeah, I mean, so there, a lot of Argo profiles stop before 2,000, like way before 2,000. Actually, around 1,000, there's a big cutoff. So that's why the choice we have right now is about 1,000. In the, when we provided this for the GVX comparison, we actually did, I think, 3 layers. Donata would remember better which layers we actually used, but we did the layers that were requested by GVX. So we have done this for, like, let's say 3 or 4 layers. And of course, it's interesting to figure out how you do it, even from more layers than that.
Okay, thanks. So Tim, would you take over?
Thank you.
So our next talk will be by Thea Sukianto. Hi, Thea. Share your screen.
Looks like I have to come back into the meeting.
Do we have your talk here? Yeah, I think she's logging off and back on. There.
Sorry about that, I think. Seems to be working. All right, can you see my screen?
Thea, I'm having a hard time hearing you.
Can you hear me?
We can hear you, but not very well.
All right, is this better? Or is that about the same? This is the only microphone I have.
That's a bit better, thanks.
Okay.
But you.
Sorry. All right, can you see my screen okay?
Yes.
All right. So hello, my name is Tia Sukianto, and today I want to talk about my joint work of my co-advisors Donata Giglio and Mikhail Kusala on toward improved OHC mapping and uncertainty quantification by modeling the vertical spatiotemporal dependence. So we know from the IPCC that most of the excess heat in the climate system has been stored in the ocean, which means that changes in the OHC contribute to extreme climate events such as intensified tropical storms and rising sea levels. So if we want to track the rate of climate change, it would be a good idea to look at the ocean. In our case, we consider the Argo data from 2004 through 2021 to estimate the OHC from 15 to 1850 dbar. On the left, we have maps of the number of Argo profiles from 15 to 975 dbar, which I'll call the top layer, and 975 to 1850 dbar, which I'll call the bottom layer. We can see that in the bottom plot, there are a lot of regions which are blue, which means that it's more sparsely sampled. So due to having fewer observations deeper in the water column, we will model the OHC in the top and bottom layers separately. So now how do we model the OHC from sparse observations? The first step is to model the vertical dimension, where we consider the two layers and we integrate the Argo profiles in each layer. And the next step is to model the horizontal and the temporal dimension, which I'll start talking about in the next slide. And then finally, we estimate the uncertainties based on the results of 1 and 2, which is kind of the main focus of this talk. So for the horizontal and temporal dimension, we need to estimate an evenly spaced grid across the global ocean. One of the established ways of doing this in the literature is what my advisor Mikhail just talked about in the last talk, where the first step is to model the temperature mean field using local least squares regression. This follows the classical method that was proposed by Romick and Gilson in 2009, where we also add an extra step where we add the linear climatological time trend. The second step would be to model the residuals or the anomalies using this local moving window stationary Gaussian process regression. So now that we have a model, how do we get the uncertainties for the total OHC? So the top plus the bottom. We need an estimate for the conditional variance of the total OHC given the data, which incorporates the conditional variance of the OHC for each layer. Now, if the layers were independent, we would be done here. But realistically, the temperature in the top layer is correlated with the temperature in the bottom layer. So if we simply summed the conditional variances for each layer, this would underestimate the uncertainty of the total OHC. So we also need to add this conditional covariance term. But if we model the layers separately, then we don't actually have access to this term. So all we can get is this conservative upper bound, which would overestimate the uncertainty of the total OHC. This all suggests that we can improve the uncertainty estimates by also modeling the correlation between the layers. We can do this by extending the Gaussian process model to a bivariate case. So let's call the temperature residuals at year I and observation J, Y top and Y bottom for each layer. We say that this is equal to a function fi of the latitude, the longitude, and the date, which we say is IID Gaussian process with mean 0 and covariance function k. This captures the variability at larger scales, but for the variability for smaller scales, like such as those from eddies, we say that we also add this nugget effect epsilon, which we say is IID normal with mean 0 and covariance sigma epsilon. So on the next slide, I'll talk about how we actually get the cross correlation from this covariance function. Now, if we were considering the residuals on each layer separately on their own, then we could use a marginal covariance from the established univariate method in Kusela and Stein in 2018, where Z is the vector that is composed of the latitude, longitude, and the time. Say that this covariance function is equal to this factor, which turns out to be the Gaussian process variance, times the negative exponential of the distance in space and time between 2 points, scaled by these length scale parameters or the decorrelation scales. So for the bivariate extension, we also consider this cross covariance function, which is based on the work by Kleiber and Nitschke in 2012. And we can see that this definition looks very similar to the marginal covariance, but the main difference is that conveniently, we now have access to this beta, which is the cross correlation that we're interested in. Okay, so now that we have the cross correlation, how do we get the uncertainties? So recall that we're interested in the conditional variance. So what's the distribution of the anomaly given the data? Conveniently, since we're considering a Gaussian process, then the result follows from the multivariate normal distribution, where the conditional covariance is the sigma for a particular grid point I that we're interested in. This conditional covariance is parameterized by our estimated Gaussian process variance, length scales, and the cross correlation from the previous slide. So now how do we sample from this distribution? We can do this using local conditional simulations, which is an extension of a work by Nitschke et al. In 2018. The way this works is that we first simulate the Gaussian white noise over the grid for both the top and the bottom layers. We next compute the local conditional covariance matrix for the grid point using the parameters that we estimated. Then we take the symmetric square root and multiply it by the white noise. Then we keep the center point and we repeat for all grid points and for the top and the bottom layers. We repeat for the desired number of ensemble members. And then finally, since we model the correlation, the sample variance of the top plus the bottom layer integrated ensemble members is then the estimate of the conditional variance of the total OHC given the data that we're interested in. So now I'll go over the results. This plot is of the estimated beta, so the cross correlation. Looking at this plot, we can see that most regions are red. So that means that they are strongly positively correlated, except for a few regions in the Indian Ocean and the equatorial Atlantic Ocean, which are negatively correlated. Another observation we made is that in the Kunoshio region, we seem to estimate that the correlation is exactly 1, which would be unrealistic because this would imply that if we knew the temperature in the top layer, then we could perfectly predict the temperature in the bottom layer. We think that this could be due to some strong non-Gaussianity in this region, but to know for sure, we will need to do some further investigation. Next, we also have plots of the relative difference of the predictive variance or the Kriging variance. And we can see that for both the top layer and the bottom layer, most regions are blue, which would imply that the bivariate model tends to produce lower predictive variances. This also matches up with the previous plot, where the regions are positively correlated. But to really make the statement that the bivariate model produces better predictions, we would have to do a cross-validation study. So the next is to discuss the uncertainties. Here we have plots of the global OHC anomaly estimates in black from 2004 through 2021, where for now we just have the uncertainties for February of each year due to the computational cost. The orange is the 95% interval and the red is the 68% interval. But just by looking at the plots for these two models, it's difficult to compare the lengths of the confidence intervals. So instead, we plot the standard error directly. We can see that the black dots, which are the uncertainties that we obtain with the bivariate model when we consider the correlation, is approximately 15% smaller than the original univariate method and the conservative upper bound. We can also see that the uncertainties with the correlations are smaller than the conservative for both methods and larger than those without the correlation, which matches up with our discussion of the conditional variance from earlier in the talk. Another observation we make is that the trend in the uncertainties follows the number of profiles. So if we look at the number of profiles in 2004, we have the least amount of profiles, and this also corresponds with the greatest uncertainty. Conversely, in 2016, we have the greatest number of profiles, and we also have the lowest uncertainty. But just by looking at the global uncertainty, it can be difficult to tell if there's anything interesting going on at a regional level. So we also plot the proportion of significant grid points over time at the 95% level. And just to be clear, this is not a stacked bar plot, but it's the univariate proportion plotted on top of the bivariate proportion. So this is saying that we consistently have a greater proportion of significant grid points for the bivariate model. And on the right, as an example, we also have a map of the significant regions for February of 2010. And we see that the dipole pattern emerges in the equatorial Pacific Ocean. But just taking a first glance at these two plots, I think the first thing that we really notice is that in February of 2016, there is a huge spike. We think that this corresponds to the 2015 to 16 El Nino, and that this appears in the equatorial OHC anomalies. So if we look at the map again for February of 2016, we see that this dipole pattern is much more pronounced, and that there's a particularly large negative significant anomaly in the western equatorial Pacific Ocean. So for future work, we still need to validate the Kriging variances and the uncertainties. One way we could do this is using cross-validation, which is what Mikhail talked about in his talk. We could also map the synthetic profiles and comparing this to the model truth, which is what Matt Palmer talked about. We also need to investigate the Kunoshio region and see if we can account for this non-Gaussianity in the future. And notice that we also only discuss the uncertainties for the Gaussian process model. So we also need to discuss the uncertainties for the mean field and the climatological time trend. I think a natural extension of this work is to generalize the multivariate GP regression model to more than 2 layers. And we could also apply this model to other fields, such as SSH and OHD and oxygen and TS, which is part of an effort that is led by Alison Gray. So in conclusion, due to having fewer observations deeper in the water column, we model the OHD in the top and bottom layers separately. But we can improve the uncertainties of the total OHD in the water column, so the top plus the bottom, by estimating the spatially varying cross-layer correlation. And empirically, we found that using the bivariate Gaussian process model to estimate the correlation reduces the OHD anomaly uncertainties, both for each layer separately and by around 15% for the entire water column. So thanks. I'll be happy to take questions if there's time.
Thank you, Thea. Are there questions? I did have a question, a very basic one.
Yeah.
You talk about bivariate as and the univariate, and I'm sorry I missed this, but What is the bivariate?
So bivariate is this model where we consider the temperature residuals in the top layer and the bottom layer together, and then we also model the cross correlation using this additional cross covariance function.
So univariate would just be, you just add the heat content from the top and bottom layer, where the bivariate uses a correlation between the two?
Yeah, so we still add the top and the bottom layer, but we also consider the correlation. So in the first, like a univariate method, we're effectively assuming that the two layers are independent. So we don't have any information at all about the correlation.
Okay. And why do they need to be dependent? Why do you need the covariance?
It's in this definition of the conditional covariance of, the conditional variance of the total OHC given the data, which is how we get the uncertainties. So if we assume that the temperatures in the top layer are like correlated with the temperatures in the bottom layer, which I think is realistic, then we also need to consider the covariance function. And then if we don't consider this, then it will underestimate the uncertainty.
Okay, but so basically the heat's entering the ocean from surface flux, right? In the top layer. But there's, so it's coming down from the top to the bottom layer at some time scale, but not at a short time scale. Your bottom layers was from 980 to 85 to 1850. Was that it?
Yeah, it's like a 975 to 1850.
So there would be a correlation, but on longer time scales, on what time scale are you looking at?
So the time scale in the model is we're considering that it's like independent across the years. So I think it's on like a yearly time scale.
Okay, thank you for the explanation. Are there any further questions? Okay, thanks, Thea. So our next talk is from Annie Wong. Hi, Annie.
Hi, Tim. How are you?
I'm good. How are you? I know it's very late or early there.
I assume you can hear me. I'm having some problems with the video, so if you don't mind, I'd like to keep the video off.
Okay.
And then I'll see if I can share my screen. Can you see this?
Yes.
Okay, view, slideshow. Okay, shall I start then?
Yes, please do.
Hi everyone, my name is Annie Wong. My talk today is all about Argo salinity. Several talks from yesterday have already touched on this topic, so I hope I can give enough of an overview to at least answer some of the questions about Argo data. A very brief overview. You all know Argo's aim is to provide global sampling of the subsurface ocean variables by using autonomous profiling floats. Unfortunately, the raw data can contain bias from various instrument problems. And one of the more significant instrument problems we have is sensor calibration drift. This is a fact of life for most instruments, but is particularly prevalent in conductivity cells used on profiling floats. I mean, naturally, if you leave the instruments in the ocean for long enough, the various components of the cell will deteriorate over time, and so will the salinity measurements. Having said that, Argo salinity measurements have on average remained fairly stable over time. This plot here shows that on average, about 25% of floats will require salinity correction of only about 0.01 after 6 years in the ocean. I think that's a pretty good long-term performance for an instrument that's pretty much left unattended for the, its entire life. So how does Argo adjust its salinity data for sensor drift? We do a simple additive correction for each profile, but in order to come up with that additive correction factor, we look at a long float time series against background historical reference data. The time series is put through a piecewise linear fit to filter out the variability in both the float data and the reference data. In most cases, we need a time series to be at least about 12 months long in order to extract a robust trend, sometimes longer depending on the trend. If the trend is more complex or if there's a lot of variability around, we need a longer time series. So in the lower left-hand panel here, it's an example of a typical sensor drift trend that we see is slow and steady over many years. In this example, the drift rate is about 0.02 in salinity unit over 3 years, and the trend is slow and steady. That's typically what we see. But in recent years, we have many CTDs showing what we internally refer to as abrupt salty drift. On the right-hand panel, in green, is an example of such an abrupt salty drift. We use this term to describe the kind of drift where the salinity measurement starts drifting early on in the float's life, earlier than expected, and then the drift proceeds to being drastically bad and the data become erratic and uncorrectable very early on in a float's life, to a point where we cannot correct the data anymore. It represents a net data loss for Argo because the data are so bad we cannot correct them. And many speakers yesterday have already talked about the increase in salty bias in Argo starting around 2015. That increase was the result of the manufacturing problem that manifested as abrupt salty drift. And so what are the impacts of this particular manufacture problem? It increases the number of CTDs we have above average that have this salty issue. Seabird Scientific, the manufacturer, implemented a manufacturing change in 2018 to fix this issue. We think it's mostly fixed, but the Argo array still contains many affected CTDs. We have many data teams around who are actively searching and monitoring the floats with this problem. When the drift is detected, the salinity data are flagged in real time and adjusted in delay mode. But the true impact is that many data products that included raw Argo salinity data from that period are out there and people are using them, and their scientific results have reported significant anomalies after 2015. Here's one of the studies that demonstrated the effects by Bernard et al. I think Anne has presented this in details yesterday, so I will skip it because I can't do a better job than Anne. Here's another similar study that used several data products that included raw, unadjusted Argo data and demonstrated the same anomalies in global mean salinity after 2015 when compared to GRACE-derived values. So as far as scientific impacts go, I'm sure there are many experts in this workshop who are more knowledgeable about this topic than I am. So I think I will move on to describe some of the best ways to use Argo data. Argo published 3 kinds of data: raw, real-time adjusted, and delay mode adjusted. What are the differences? The raw data are data as delimited from the floats. They will contain instrument bias. If you use them, you have to evaluate or adjust them post-deployment. We supply QC flags only. But they are available readily. They're available between 12 to 24 hours after data telemetry. And then there are real-time adjusted data. These are data that have been adjusted by an automatic procedure. The factor used by these automatic procedures are derived from the delay mode decision or from climatology. If the derivation is feasible, they will be available at the same time as the raw data. And they bridge the time. They're not perfect because it's done automatically, but they bridge the time gap between the raw and the delay mode data. So they serve their purpose. The delay mode data are data that have been adjusted or evaluated post-deployment by oceanographic experts. They are the highest quality data. They're improvement over the raw data because of the reduced bias. We also supply detailed quality control flags and uncertainty estimates. The downside is because, as I described in previous slides, it takes time to do this process. They're available about 12 to 18 months after data telemetry. And where may you find all these data? The raw data and the adjusted data, whether they are real-time adjusted or delay mode adjusted, can be found in the same data file. The raw data are stored in variables called press, temp, pcell. The adjusted data, whether they're real-time adjusted or delay mode adjusted, are stored in the variables press adjusted, temp adjusted, pcell adjusted. To know whether they're real-time adjusted or delay mode adjusted, you can look at the variable called data mode, or you can just look at the file name. Real-time files have file names that are preceded by the letter R. Delay mode files have file names that are preceded by the letter D. As I said before, the delay mode data are the highest quality data we can produce. Scientific applications that are sensitive to salinity error should use the delay mode data. Obviously, the higher quality the data, the longer time it takes to process them. So if you can wait 12 to 18 months, best to use the delay mode adjusted data. Another thing I want to mention is in Argo, we put all our data out there, the good, the bad, the ugly, all of them. Obviously, you can't use all of them for your scientific studies. So to decide what you need to use, you've got to read in the QC flags. This is especially important if you are getting data from the GTS and you are still using old code from the TSAC days. I mention it because before 2018, we put data on the GTS via the TSAC format. The TSAC format did not accommodate QC flags. So back in those days, we selectively only put the good data on the GTS and withheld all the bad data. But now we are using the buffer format to put data on the GTS, and the buffer format accommodates QC flags. And so now we're putting all our data on the GTS, the good, the bad, the ugly, with the QC flags. So we're going around to reminding all the operational centers who rely on downloading their data from the GTS to please update the code to read in the QC flags. in the buffer format. Last thing I want to mention is, well, a reminder that users should refresh their Argo database periodically. There is a reluctance in the user community to maintain multiple versions of the Argo dataset. I mean, not just the Argo dataset, but it's something we all hate to do, you know, maintaining multiple versions of any kind of dataset. But this is necessary to not spawn anomalies in scientific results, because, as I mentioned, in every Argo data file, there are two kinds of data. The raw data are preserved as originally received. They never change. So by nature, they're static data. But in the same data file, there are the delay mode data, and the delay mode data are being reevaluated periodically and updated when necessary. So by nature, they're always changing their dynamic data. So raw Argo data harvested from the GTS need to be replaced with delay mode data from the Argo GDAX. And Argo data holdings that are downloaded from the Argo GDAX should be refreshed about once a year to capture the most recent delay mode analysis. Here are the main points in my conclusions. I don't think I need to repeat them, but I think many speakers yesterday have already touched on these conclusions. But this is just a last plea to data product producers to, if you're including Argo data in your data product, to please refresh your data holding and update your data product periodically. Preferably use delay mode data. And that's all for me. If people are interested to read more about uncertainty evaluation of this delay mode salinity, here's a paper you're welcome to peruse. If there are any questions, please feel free to email me, or I think there's time for me to take a few questions.
Thank you, Annie. We have questions?
Okay, thanks for the nice talks. So I have a lot of questions, but just two for now. The first one is you have a real-time adjustment and delayed adjustment. So have you ever assessed the difference between the two kind of adjustment? Is the first question. The second one is because you make an adjustment, you compare the Argo data with climatology. So they might be 10 years or 20 years long distance. So there are a lot of variabilities or trend. So how to assure that the adjustment is correct or does not biased? Thanks.
Okay, to answer your first question about the real-time adjustment, the correction factor that are used in the real-time adjustment are derived from the delay mode adjustment. So basically the real-time data centers extract the very last available delay mode adjustment, which, as I mentioned, is just an additive factor, and they propagate that forward. I haven't done an analysis how the real-time salinity adjustment performs, but James Reagan's presentation yesterday had a slide up where Jim has done this comparison where he showed that the real-time salinity adjustment tracks the delay mode adjustment fairly well. But as I said, it is not a perfect procedure. It's done automatically. It reduces the bias somewhat, but not perfectly. So if you can wait, it's best to use the delay mode adjusted data. To your second question, you know, the CTD data set is not perfect, as you know. There are many spatial gaps and temporal gaps in there, but they are independent, and we use only the highest quality CTD data. So that part is important. we do supplement that reference database, which is all CTD based, with a secondary database that we come up with internally, which is composed of Argo profiles that have been determined in delay mode to be good and that did not need any adjustment. So in areas that do not have sufficient CTD reference data, either spatially or temporally, we supplement our evaluation with that Argo reference database. And then we also sporadically do basin-wide analysis where we look at all the delay mode data in the same basin collectively. So when we do delay mode analysis, we look at each float time series individually. But we also do basin-wide regional analysis where we look at data from all floats in the same basin collectively. And that tends to bring out anomalies in our evaluations. And when we see them, we go back and correct them. Does that answer your question?
Yeah. Thanks, Annie.
There's time. Yeah, very nice presentation. Thank you for the information. I got my copy of the data set updated from a month ago from the GDAC. My question to you is there in the QC right now an information to identify which profiles might have this dramatic problem in salinity being identified?
No, we don't do that because, as I said, sensor drift is a fact of life for profiling floats for any instruments. We internally refer to these special cases for our internal discussions, for tracking, for monitoring, for conversing with the manufacturer, but we don't tag them with this tag. So we in the data files, we treat them the same as any other sensor drift, which is we either correct them if we can correct them, or we mark them as bad. So in the data file, you just get the corrected data or the evaluated data. Is there a need for you to know that that's the case that we're referring to? Because it's a subjective description.
Yes.
Different people looking at different drift trends will say, well, this is it, that's not it. It's just a terminology we use internally. It's not a definitive problem.
Right. I will probably follow up with you over email, but essentially what I'm thinking about is we have argued that ECHO, this ocean analysis we produce, is a good way to reject data like this because it would be very hard to fit it based on physical principles. And so I'm going to try and do a quick comparison between the two and see if I can identify them. I was wondering whether the data would be marked as bad or if I had a hint of how to find them. But I will follow up with you on email. I think it would take too much time.
I think it's best if we discuss this offline.
Any more questions? Okay. Thank you very much, Annie.
No problem.
So I think now we break for lunch. I'm getting ahead of myself. Sorry. We have one more talk. Brian Sodden? Oh, Donato's giving the talk. Okay.
Yeah, I think the name is wrong on the program. The online one is updated.
Okay.
Can you see my screen? Can you see my screen?
Yes.
Okay. And I was trying to start the video, but it doesn't seem to let me do that. Not sure why. Okay, maybe it will come up at some point during the talk. Hi, everyone. Today, I'm Donata Giglio, and I will be presenting today on regional changes in oceanid content. And this is a work in collaboration with Mikael Kusala and Tia Sukianto and Jacopo Sala. So we looked at observation-based regional oceanid content estimates with uncertainties because these help to evaluate models and understand driving mechanisms for these changes. Also, they help understand impacts on coastal communities. If we think about regional sea level changes, intensification of tropical cyclones. And finally, they also help us understand impacts on ecosystems. If, for instance, we can think about coral bleaching. Here on the right, we actually have an example for what I mentioned on regional changes in sea level, where we see from the recent IPCC report how the thermal expansion contribution to the sea level, shown here in the map on the right, is important when we want to understand impacts of sea level rise for coastal communities. In the following, I will be talking about this estimate of oceanid content fields in the layer 15 to 9075 decibel as one example to see what we can look at if we have reliable uncertainties. I will not be describing in detail the method as Mikael has already presented. So this is the mapping done, the univariate mapping Mikael discussed, where the climatology includes a seasonal cycle and the linear trend in time. The residuals from these climatologies are mapped using locally stationary Gaussian process regression. And finally, the uncertainties are represented by these ensemble members that are created via local conditional simulation. And this is an extension, as Mikael mentioned, and also Tia mentioned, of Nishka et al. 2018. We use Argo data, as you may remember from the previous talks, and we focus for this example on the period 2004-2022, with some exceptions. In some of the slides I'll mention that the period is a subset of this, as we want to compare with other products, and we restrict to the period those products are available. We'll briefly talk about Gloris and Echo as comparisons, for comparison. As you know, during the 2004 to 2022 period, we have a lot of Argo profiles. Argo provides this unprecedented resolution in space and time. And this map shows just that in terms of Argo profiles in 1 by 1 degree bins. So the first thing we could look at when with this product is, for instance, the trend, the regional trends with uncertainties for the full period I mentioned, and the zonal average of these trends. So here on the left, we have the zonal average of the trend. The horizontal axis is oceanid content trend in watt per meter square. The vertical axis is latitude. And then, as you can see, there is a dark, thick black line, solid line, representing basically the ensemble mean, and then the uncertainties around it at the 95% level are based on the ensemble members. So at most latitudes, there is a warming, as we know, except for the higher latitudes in this panel. And this is associated with a warming hole that has been described by different studies. Basically, when we look at the map, these are the blue anomalies we see in the North Atlantic. Now we can also look at the spatial distribution of these trends, not just in latitude, but in longitude and latitude. And the regions that are masked gray are those that are not significant at the 95% level. And we see patterns that we recognize from other estimates, but we may want to compare more directly these patterns of warming and cooling in different places with other products, both in terms of this trend and the other variability that is there. So for purpose of showing some examples, we look at this Northeast Pacific region where we had a prominent marine heat wave and during the Argo period. And then we look at the Southwest Pacific down here. The other box represents the Niño 3.4 region and will be used later in this talk. So the first comparison we do is with the GLORIS reanalysis. This is an high resolution reanalysis. And for both Argo and GLORIS, we remove the trend and the seasonal cycle, and then we look at the time series and the trend in those regions that I highlighted in my previous slide. So on the left, we have the region in the Northeast Pacific, on the right, the Southwest Pacific, and the legend shows the trend with uncertainty in the case of Argo for Argo versus GLORIS, and then the time series shows the variability, other variability in the region. So for both panels, the horizontal axis is time, the vertical axis is the anomaly in ocean heat content, and as I said, for the purpose of this talk, we take the example of the 15 to 9075 decibel ocean heat content. So for the Argo, as we saw earlier, for the zonal average of the trend, we always have a thick solid black line that is basically the ensemble mean, and then the uncertainty at the 95% level are shown as dashed black lines. And what we can see from this comparison with GLORI is that there is an overall good agreement between the gridded Argo and GLORIS. If we want to look at the mechanisms for some of this variability, we may want to do so using an ocean state estimate, dynamically consistent reconstruction of the ocean. We can do that, for instance, using ECHO. So the ECHO version 4, release 4, is available during the period 2004 to 2016. So now we look at the Argo ocean heat content in this period and the trend, the regional trends during that. Given the shortness of the Argo period, we see some differences from the map before, but overall consistent. So the only difference really is the different duration of the data that are considered to compute the trend. And again, the gray area are those that are masked because not significant at the 95% level. Still, we see this warming in the Northeast Pacific on a warming trend, and Southwest Pacific, the cooling in the North Atlantic. And if we compare the trend from Argo with ECHO, we see a lot of those patterns. So if we compare, if we focus on, I'm going back and forth, so this was Argo, and if we focus on the regions that are significant in the Argo estimate and compare with ECHO, we see good agreement. This is great. ECHO obviously assimilates Argo, and for this layer, there is a very good agreement in the trend. We can also compare the time series, the other variability in addition to the trend in the two regions that I mentioned earlier. And we can do so in this plot. And if we think about, for instance, the Northeast Pacific region, and we have in mind that we want to look at the marine heat wave event, it makes sense to restrict to a shallower layer. So here we look for this comparison at the 15 to 300 decibel layer. And the time series shows on the horizontal axis time, the vertical axis is the anomaly. And the three products here are in red as before. We have GLORIS, not the focus of the current comparison, but the blue is the ECHO product and the black is the Argo product. So the ECHO trend and the Argo trend, as we expect after seeing the previous map, are in good agreement in this region. And also the variability is in overall good agreement between Argo, ECHO, and GLORIS. So we can hope that we can gather some insights on the mechanisms for these changes in heat content from the budgets that we can do with ECHO. So here we look for the Northeast Pacific region at the temperature and salinity budget terms at different levels in the water column. And here I'll be very brief and just point out that if we look at the relative importance of the contribution of the different terms, the relative importance of the different terms in the budget, what we see, for instance, if we look first on the left, that the dominant terms near the surface for a temperature budget are the forcing, surface forcing, so RC fluxes, and in magenta, the diffusive convergence. And as we go deeper, the advective convergence as a larger and larger plays a larger and larger role. And this is the case also for the region in the Southwest Pacific and many other regions of the ocean. I'm not showing that now. And also for the Southwest Pacific, this relative importance is the same for the salinity budget. Instead, for the region in Northeast Pacific, as we can see here on the right, the relative importance is a bit different for different terms. For the salinity budget, if we look at the top panel on the right, we see that the advective convergence, so this yellow dotted line here, plays a role in the budget already near the surface. And the larger, I'll not go into the details of this project led by Sala here at CU, but the larger idea here is to look at how the different contributions to changes in stratification play a role in the formation and demise of marine heat waves in different regions of the ocean. Another thing, and I'll probably skip a couple of slides here, but another example of how we can use, in the interest of time, probably I'll skip, and I'm happy to go back if there are questions. But there are another example of what we can do when we have uncertainties that are correlated in time, like we do for this product, is to look at correlation of our ocean heat content with climate indices. Here we bring the example of the Niño 3.4 index. So we look at ocean heat content in the Niño 3.4 region, which is highly correlated with the climate index Niño 3.4, and ocean heat content in the rest of the ocean. And what we can see, a lag 0 is unsurprising. Basically, we see that in the Niño 3.4 region, there is high correlation. This is expected. And then we can look at other lags, again, masking out the regions in gray if they are not significant at the 95% level. So if we look at a lag of 6 months, where basically we have the ocean heat content at any point in time and the Niño, and we correlate that with the Niño 3.4 6 months later, what we see is also what we expect, that the Western Pacific and Central Pacific are warming up. And so we see this high correlation west of the box. Then we can instead look at a lag of minus 12 months. So basically we correlate the ocean heat content everywhere with the Niño 3.4 region 12 months before. And we see some of the patterns that we recognize based on how we know the heats evolve, the heat evolves in the tropic during El Nino. We also see some positive correlation here in the Southeast Pacific. And we can, again, try and see if this is captured in ocean state estimate like ECHO, which it is. So this is the same exact map, but from ECHO, and we see again this positive correlation here. And then we can think of looking at how the tendency evolves in this region and what are the contribution to that tendency, which we can do in ECHO. So if we do that, then this is again a time series of the temperature budget terms from ECHO. Now the advective convergence is in red, the total tendency is in black. And if you notice in the background, there is the Niño 3.4 index that uses the right axis on this panel. We can see, for instance, here that during the strong El Nino in 1516, we have that the orange line is indicating a prominent role of the meridional advection, the advective convergence, for how the tendency of ocean heat content changes in the box down here in the Southeast Pacific. So to summarize, observation-based regional ocean heat content estimates with uncertainty help us evaluate models and, most importantly, to understand driving mechanisms of ocean heat content changes. So ocean heat uptake, how and when this heat may be released back to the atmosphere, There is, as we saw, an overall agreement between Argo and ECHO before R4 in regional trends and variability. We looked at some examples of how we can investigate the mechanisms using the budget in temperature and salinity from ECHO. We saw that the relative importance, for instance, of near-surface advective convergence is larger in the Northeast Pacific salinity budget compared to the temperature budget and to other regions of the ocean like the Southwest Pacific. Also, we saw that the advective convergence is a dominant term in the Southeast Pacific heat budget during 2015 to 2016 and so. And I'll stop here and I'm happy to take questions. Thank you.
Thank you, Donata. Are there questions? I did have a question, Donata. So you have here in the summary, you showed overall agreement between Argo and ECHO, and you showed specifically kind of a what's the word? A correlation between Nino 3.4 and an area in the South Pacific. I mean, wouldn't you expect that, given ECHO is assimilating Argo data, right?
Yes, yes. So we do expect that there will be consistency. Now, this consistency may look different and be more or less if we were to look at the vertical distribution of heat in the water column, which we are not doing here. But what I see sometimes is that even if the specific layer that we discussed here and that is consistent with what Michael discussed is consistent with other data simulating products, not always we get the same good agreement when we look at the vertical distribution, basically the vertical stratification in the models. So this is one thing I want to look at now that we have uncertainties and we can compute more layers and use the uncertainties to evaluate how the stratification basically and changes in stratifications are represented in these models. It's not always the case that all the layers basically, I guess that would be my comment on that, agree as well as when you look at this layer.
Okay, thanks. And I have a question from chat. But before I get to the question in chat, do you have an explanation for that kind of that correlation with the South Pacific and Nino 3.4?
So the next step I want to investigate here will be to look at changes in winds. We haven't done it yet, but this is obviously a region where, especially for the role of the advection, that seems to be the dominant term for specifically the case of the strong El Nino, and so in 2015 and 16. I would like to look at that more carefully and understand better if changes in winds are what caused that, basically. And this is this correlation is found on this short period during the Argo period, and may be driven by what happened specifically during the strong Nino event there. So it would be interesting also to go back in time and see what are the conditions, like doing a composite basically over several different ENSO cases and see if this happens also other times. Because we clearly see the role of vacuum convergence during this specific strong ENSO, but we still have to investigate this more carefully.
Okay, thank you. And the question from chat, from page 11, any idea what is causing the small but strongly negative trend in OHC just south of Japan versus the positive trend farther north?
Oh, we haven't looked at that yet.
Okay.
And
Thanks.
again, yeah, I would look at changes in circulation.
Okay. Any more questions for Donata? Okay, thank you very much.
Thank you.
And now it's time for lunch. It's a pretty big question.
I may take a few ones for the others. Just a comment about that. I think the ensemble approach that proposed Li Jing was quite promising, wasn't it? I mean, although the different uncertainty, the different errors may be correlated, this ensemble, which is taking into account, which is using all the different sources of uncertainties, isn't it a kind of thing we want to do to try to aggregate all the uncertainties and get a full vision of the level of the uncertainties we may have at the end? Probably it has to be populated with more mapping methods, for example, probably more other elements. But is it something that could give a comprehensive, or at least a start of comprehensive estimate of the uncertainties?
Yeah. Okay, so just some thoughts on that. So first of all, I very much like the ensemble approach. I mean, that's also kind of what we are proposing. We just start doing an ensemble at a different level. We are actually not accounting for the sources that you are accounting for, and I think you're not accounting for the ones we are accounting for. So I think, you know, we can maybe combine. So I think the ensemble approach is very attractive. But the comment I want to make is that I think you just need to be a little bit careful, like what are all the sources of uncertainty, in the sense that some of the things that have been like called uncertainty here, I think are not really actually uncertainty, in the sense that for example, we've seen a lot of these like spreads between different methods and ways of doing things. The issue is that like some of these methods are actually biased, and we can show that they're biased using the kind of techniques we have studied. So the question is that like if there is a bad product and it causes a spread in, you know, with respect to in some sense good products, is that an uncertainty? I would say that that is not an uncertainty. So one needs to be very careful in terms of what goes into the ensemble. I think things are like you know, bias corrections and there is XPT corrections and things like that. I think those are all valid things to put to the ensemble, but one just needs to be a little bit careful about all the things that form the ensemble.
Well, I mean, I'm sorry, Li Jing, go ahead.
No.
Oh. I do think the ensemble approach is a good approach, but you say we don't want to have bad products in the ensemble, but how do you identify a bad product? I mean, what I showed, you know, the comparison with series and the at least the ocean heat uptake, it was all over the place. It was, I mean, it wasn't random, but from that, it was impossible for me to tell what was a good product or a bad. I mean, you need to go, I think, to the next step, which I was starting to do, and start to look at it geographically and see. I mean, you've really got to look into it to see if the product is creating realistic patterns, or why those patterns of ocean heat uptake. Because over the long term, all of the ocean heat content products that I looked at were pretty similar. Maybe one was a little bit low, but otherwise, none of them looked bad. How without looking for regional patterns or what exactly is going on, I don't think we can really judge a particular product to be good or bad, and without that, I mean, the ensemble is a good way to go about things to get an uncertainty, but that really doesn't get to the heart of the matter about what makes a product good or bad, and can it be, is it the method then, or is it the data itself, or what would make that product better? No.
Yeah,
so
can I just tell you a point? There is maybe a way around this, which is your community. Can't you agree on the list of minimum things that has to be done, because it has been proven that we shouldn't do the other way? For example, I think it has been proven in many papers that relaxing towards zero or relaxing towards the climatology is an issue if your climatology doesn't include a trend, for example. And so you could make a list of practices that are minimum to enter an ensemble study, saying, well, we know that a product which is using a climatology without a trend and which is relaxing to the climatology, we know it is biased low. And so we can say, well, we want people to have to address this question by way or another, or either the way Michael is doing, or the way Li Jing is doing, or others. But you have to address this question if you want to enter the ensemble. Or it doesn't mean we could do then a study with all the studies, and then just identify a sub ensemble which are agreeing a list of minimum best practices that you can agree in your community, because it has been shown that in this case it is biased.
Well, I don't think that's true, actually. I mean, what I showed in my talk, the first few slides, that maybe, and our ocean heat content does relax to climatology. But what I tried to show in those first few slides, that at the very least in the Argo period, that is not an issue. I mean, that's a mapping issue, and if we have enough data, which we do, or we think we do, in the Argo period, then that issue goes away. I mean, we certainly, for before that time, we need to look at it. But the years that we're interested in for comparison with series at least are those for which that is not an issue, as well as the XBT correction. I mean, it's good to look at the different XBT corrections and see which ones are as part of the ensemble, but that's really not that relevant for the Argo period, the period that we are interested in.
Okay, fine. I was wrong on this example, but you could take...
Can I comment on that, because I have a slightly different view on that. So it's probably true that for your product, there's not much of a difference, but it does depend on how the product is created, and some products might be more sensitive to this issue than others, and especially it depends on the decorrelation scales. So if you use relatively long scales, then you're less sensitive to the climatology. If you use shorter scales, then you are more sensitive to the climatology. So it's actually confounded with the way the product is done. So one needs to be a little bit careful in terms of drawing conclusions just based on one product. So the other products might have this issue. And I mean, that's what we showed in our work, is that like the way we do it, it is very sensitive to whether you include the trend there or not. And I think the Römig and Gilson product is used a lot. I think even they themselves admit that it's biased. If you look at their, you go to their website and look at their ocean heat current time series, it's very clearly biased both in the early period and the late period. And then there are users who are not aware of this, and they just pull the data and they use it. There are no big warnings about this. So there are for sure products that are sensitive to this issue. Maybe probably not your product, but there are other products that are. And so then that brings the question: how do we know if this is an issue? So it goes back to validation. I think there's two validation techniques that have been proposed. So one is to use models and synthetic data from models, and I think that's fine and good and should be done, and hopefully will be done. We've heard about efforts for that. But then there's also the cross validation that I talked about. So so if you do that, it's a fully data-based, data-driven validation that is not relying on synthetic data from a model. It's really asking, like, can I even reproduce the actual Argo data that went into the product in some sense? And I showed you that, I know it was pretty quick in the talk, but I showed you that there, from that you see a very clear unmodeled, or a very clear bias if you don't include the trend, at least the way we do the mapping. So things like that, like cross-validation, can be used to like rule out bad models. And if things like that show that there is a very clear bias or big errors or underestimation of answers and so forth, then that would hopefully help kind of figure out what products should go to the ensemble and what should maybe be left out or maybe downweighted one way or the other.
So just to finish, just coming back to the general question, do you think your community can agree on a list of best practices to start and to put those models in an ensemble? Or do you think it's a wrong idea?
Do we have to? I mean, just from the little discussion here, I think.
So okay, maybe we don't have to. So it goes back to the previous question. What is your option to get a comprehensive, so knowing all the sources of uncertainties we have today, not talking about new ones, how can we get a comprehensive estimate of all the uncertainties if it's not an ensemble approach? So if you say we don't have to, so it means we have to do something else than the ensemble, because we would agree in doing an ensemble if we have a list of best practice to enter the ensemble. So if you don't want to do that, what's the option?
I mean, the way that I see if we can, I mean, we don't have to agree even, but if mapping method is not as important a factor in the Argo period, well, even if it is, but I think the input data set is the important part. Let's just assume that we have enough data that whatever the mapping method, you're going to get pretty close to the right answer, as good an answer as you can get, as long as the input data is optimal. And so if we concentrate on making sure that the input data is optimal for ocean heat content calculations, then anybody can grab that data set and use not any mapping method, but a variety of mapping methods to come to get to the same conclusion.
Yeah, I think. Somebody online wants to say something?
Yeah, sure. I mean, I'm interested in the discussion. So this is Matt Palmer here. So it's a shame I can't see you guys. I can see the lectern. Yeah, I mean, I guess I have some sympathy with what Benoit's saying, is that I think there would be some value in kind of working towards an ensemble estimate that reflects the diversity of estimates that are out there. I think one of the purposes that would fulfill is the communication around ocean heat content change and its rate. And I think there are some advantages to the ensemble approaches. So I put a link in the chat. But for IPCC Sixth Assessment Report of Working Group 1, I mean, we basically had to go through this process, or that's the process that we went through with a limited subset of ocean heat content estimates. But I think there is value in the different methods because they have different structural kind of assumptions in that. That's one of the things that's come up again and again in the discussions, is people saying, well, there are certain subjective choices. It doesn't really matter which data set or variable you're talking about. There's always these subjective steps that we don't really know how they influence the end product. But one of the ways, using an ensemble approach does allow you to factor in those structural choices, which I think is good. So to me, it seems like to work towards some kind of ensemble method in the shortish term would be an achievable goal. I think to really answer the question that's been asked here, we need to employ a wide range of techniques, including the synthetic sort of profiles, but also using the data that's available to us and kind of cross-validation and all these things. So I think it's hard at this stage to be really confident that we've captured all of the uncertainties and really understand what they should be. But I think in the short term, one of the best things we can do is throw an ensemble approach, a multi-center ensemble approach at the problem. And I think there would be a bunch of advantages of doing that. One of them could be that as part of generating that ensemble method, we actually get all of the time series in a single data format, so that it's convenient for people to pick out whatever kind of members of that ensemble that they might want to use and kind of facilitate science that way. So I think there are advantages, but as I say, I don't think it's going to necessarily give us It doesn't solve the problem exactly, but I think it would be a useful exercise. So I'm quite supportive of trying to pursue that.
Maybe I'll jump in now. I was going to just ask a quick one. So I agree with what Matt said in many ways. Be inclusive. There is no reason to start from, trying to reduce the spread. But the other point is I agree with what Tim said at the beginning. I think that, it should be, the statistics are important for sure. But to many of us, the more important criteria to evaluate what these products are and how valuable they are is how much physical sense they make. There are tests that can be done on that are pretty straightforward. We know a few things about how the ocean and the climate system work. A simple one that I would offer as a starting point maybe is you can take consecutive months or consecutive years of your ocean heat content, right? Differentiate. You're going to then get an estimate of the amount of heat flux from the surface you would need to explain that. And if that's 300 watt per meter square per year, that is not a good product, right? Because that's just not true. So there are things like that that we can bring to bear on which products are more useful than others for certain purposes, and which ones make more physical sense, I think, to me, is ultimately the more important criteria.
So there are many directional discussions here, so for which I agree, and there are important aspects which we have heard all on the talks. These approaches, like the work from Nijing, which is tackling the whole envelope of the uncertainties. Then there are other talks which have, for example, highlighted, and what you also just said, Tim, in terms of the input data and going to delayed mode data, fast, and so on. So the many aspects all you have listed. But I think what is important is to take these opportunities and put all this information together, this lesson learned, in order to optimize the way how we use the data and optimize the way how we add the uncertainties for the interpretation of the different data. Then there's another aspect Matt was just mentioning in terms of availability. So to create a framework where those are available, but and also with this idea of providing as a community best practices and guidances and some further recommendations, which can also help, like also services, for example. So there's, I think one needs to, however, consider as well that there are different proposals of the development of the different time series. So I would really make a distance of trying as a community to democratize the different estimates. So they have all their proposed and all their big expertise behind. So I think it's more of taking those information, and there are all different lessons we have learned from today and from other studies. And I think that would be important to put that together to learn this and do the tests, as, for example, suggested with the synthetic profiles, and further really understand, and so that everybody could be equipped to use this information to provide readable uncertainty estimates and improve their estimates if needed, etc., rather than going ahead and providing one ensemble standard, which will also suffer from something, right? Because also and yes, and provide more a framework where best available information and guidance, and also state of the art, and also to learn how to improve would be an outcome. I would further support that one.
Okay, probably I'm going to defense this method, because the key idea is really, so we identified in the past 20 years, I think a lot of people working on that, and we identified more than 7 sources of errors in the ocean heat content estimate. We know that, and I say it's really no comprehensive estimate on the uncertainty. If I say no single estimate actually account for all these error sources. So that's why the ensemble method come out. And why I pick 3, because we have more than 10 XBT correction scheme, but not all of them are good. I mean, good seems subjective, but we have a objective evaluation. For example, some corrections only correct depths, they don't correct temperature. So that is kind of knowledge we have. After communities knowledge for so many years, we really have this knowledge that we can really identify which ones are good, which ones are not really good. So that is the key message I want to convey. And another message I want to say is, because there is a dependency, right? So, for example, my ensemble, if you follow the same method, same mapping method by IEP and the same ensemble method by NOVA, the results will be very different because they're dependent on the mapping method. So this is some kind of dependency. So even if I finish more than 2,000 runs for the ensemble members, it only represents IEP. It does not represent the other community. So that is the key point I want to say. At least if the team agree, you can also run this kind of 2,000 assemble in NOVA's method. So you can have another assemble and for your time series. So that is the meaningful estimate for your time series. So now what I propose is only meaningful for my time series. But that is the key point. So as a community, what we should do? I think first we should really take account of the best knowledge we have right now. For example, the conservative biases. So that is well identified by a lot of studies. And maybe sometimes it's not really important because it's covered by other error sources. But it is there. It is there. It is a bias. So that is the knowledge we have in the past years. So we need to take account of this kind of knowledge we accumulated in the past decades, including the XBT, MBT, this kind of biases, the knowledge. So I think for us as a community to move forward, we need to take advantages of these knowledges and then have a kind of a community consensus on how to do that. And maybe sometimes we don't know more than conservative biases for mapping method. That's why synthetic approach is also useful, because it can also identify other error sources in the mapping method besides of the conservative biases. So that might explain why the NOVA's mapping method is not the conservative bias does not impact too much the NOVA's method in Argo periods. So that is my point.
Can I make a comment on dependence, since you mentioned dependence? So one thing I want to comment already for some time now is that so we've seen this figure with the big spread in the different Argo estimates, and one thing to note is that, like, by and large, these different products, they more or less take the same input data. I know there are differences in the quality control and so forth, but like by and large, most of the data is effectively the same. So this means that really that spread there, it's not really statistical fluctuation. These are not statistical. This is not like statistical noise. These are basically statistically like 100% correlated. These different products, because the actual input data is more or less the same. So really that spread we see in those figures really has to be about kind of systematic uncertainties and biases and method choices and modeling choices and so forth. So really that spread is reflecting all those choices that go into products and the differences that causes. And also one other place where one needs to be very careful about dependencies is when you look at the error bars. So there was at least a few different talks where you see these different products, and now we have error bars for some of the products. Again, one needs to keep in mind that these products are very highly correlated. So those error bars, like they sort of should be consistent because these products are correlated. So one needs to be kind of careful interpreting those error bars. Like the fact that these error bars kind of match doesn't really validate the error bars in any way, because they're supposed to match when they are correlated. So we need to keep in mind that a lot of these things are dependent, because there's only one Argo. There's not like 10 different independent Argos data sets that 10 different groups use. They basically more or less use the same input data, which makes these products highly correlated in a statistical sense.
I mean, they're highly correlated. Oh, sorry.
Yeah, Yes, I would like to make two comments. One on the ensemble. I think, I mean, the way why we want to have an ensemble is because we believe that each member is a possible realization of that representation of the climate, and this is obviously a basic assumption, but which means we should consider, as long as they are reliable, then the reliability means they are consistent with our knowledge. They are all potential representation of the climate. There is no way, I mean, even though there is no bias in the XBT and BDT, if we change the correlation length scale, we will get different result in objective analysis, in reanalysis. So my suggestion is to keep the ensemble as large, as inclusive as possible. The second point is that if we change the perspective, we have seen a very large consensus on the drop of oceanic content in 2016, and this should be regarded possible as a signal, not as a mistake. So we do, in principle, there is more than half of the ocean that is not sampled below 2,000 meters. So if we want to reconcile series data with the statistical mapping reconstruction, it is easy because we have the ensemble, for instance, the GCOS reconstruction led by Karina. We have an estimate of data with an estimate of uncertainty. With that uncertainty, we can really fit the data set, the time series with series, saying that is the deep ocean responsible, or at least the first candidate is not a problem in the objective analysis, but it's the missing part of the measurements. I mean, they are not measuring the same physics. They measure a different region of the ocean with a different time scale, and this is obviously very basic, but I don't think there is a contrast between the two estimates. It just matters to understand why this estimate exists.
Yeah, I agree, Andrea, that we do need to treat these like the 2016 as real physical. I mean, we looked at it. It fits the pattern of, at least in part, of a La Nina. And so this is probably something real and physical, and all the different methods see it. Then we can get past, this doesn't match series because there must be a problem with all of the methods or one of the methods or two, and start looking physically. Okay, we're seeing this, but where did the energy go? Then we can get to the question that is really of interest. And I guess, I mean, I do think the ensemble is a good idea, but we're just going to get statistics and numbers out of that. When we start to look at the data, like we look at 2016, then we can start to look at the relation of those, the physically what's going on in the ocean with the rest of the components of the energy system.
Agree with this discussion. In particular, it's a good example, this 2016 signal. So maybe also for thought for discussing, instead of moving together to a super ensemble, to maybe think about a super ensemble on terms of the uncertainties. Because then it would allow someone, if you have your time series and you are faced, for example, to such a budget difference like this 2060 signal, it would allow you to judge whether this, if you have an internationally agreed uncertainty and this guidance, and also this availability, so that you could have access quickly to similar data sets and check, and this could be, for example, helpful. I don't know, just for discussion. It's a good example. And then to, as you say, to go then to the physical questions.
I'm not yet quite convinced that this anomaly in 2016 is fully true, and if so, I agree. We need to look into where else would the heat go, right? It's a big anomaly. Is it in the ice, the atmosphere, the land? I don't know. It must be somewhere to meet the series estimate. But in our study, we didn't see such a big dip in 2016, neither in our in situ ensemble nor in the satellite-based steric sea level changes. And we broke it up into basins. We did indeed see a huge dip in 2016 for the Northwest Pacific, but an opposite anomaly in the East Pacific, which seemed then to cancel out in the global mean. And I'm wondering if there's other folks who have, had similar findings.
I was just going to check to see if that's actually what we see in the maps I was showing earlier today. But I think it is from memory. But I didn't look yet to see if those. I mean, that's what you're going to see in a La Nina year, right? You're going to see an increase in one side of the Pacific and a decrease in the other. But the question is, do they balance each other out? I can't answer that yet. I haven't looked. But that's the point. Yet maybe it isn't. Maybe what we're seeing it is not real necessarily. But then why? And getting at that. And Benoit had talked about this a little bit yesterday. I mean, all of the mapping methods that we have, all of the in situ ocean heat are on isobaric levels. And maybe it's missing a component of the La Nina pattern, the heave of density levels. So maybe it's better to look at isopycnals, the heat going on isopycnals. So that's a suggestion. But by looking at looking at the physics of it, we can get at that. Maybe all of these methods are not wrong necessarily, but missing the signal because of the way they're all situated on isobarics. So by pursuing that, by looking at the patterns and seeing how the different methods handle them is an important aspect of this. A separate path from doing the ensemble, which is important too. And as Karina said, then gives you some type of uncertainty on the patterns you see.
Can I just want to give you an hypothesis? Kind of like when you said, there's heat moving when you have ENSO, a lot of it goes west and it ends up in the Indonesian archipelago where there is no in situ data, right? And a lot of it can also be in the coastal ocean. So you don't have necessarily to look very far to find it, is my guess. But it might have to do with the sampling and the lack of data in shallow places. See what? I don't have the plot right now. There is at 200 meter depth, there is something down. I'll show it on my slide. I think Jim should have a set of slides later, Jim Carton, that might bring more to that effect. It is possible that you see exactly the same thing in echo, and that would contradict my hypothesis.
Unfortunately, I don't really have the ideal picture. I can try and get it, but I don't actually have it right now.
I think there was also a picture in the talk from Donata where she was showing that it was not, let's say, adding up. But I mean, that's a good example to come back to the discussion. So also with linking to real physical signals, but leveraging also the point of limitations, maybe the product or the way the product works. Because, for example, if we would figure out that this is an issue of sampling because we do not balance, let's say, the positive and negative signal in the Pacific, and then we induce, because of this, a kind of sampling peak somehow in the time series, but that would be very, very important information, because that we could also reflect back to the historical time series and maybe take out some of the peaks which had been induced from this kind of sampling bias or something like this. So as I said, in any way, this exploring, linking with the physics and the budget and with the focus on the uncertainties will help us for a lot of improvements. And that in turn, if we then be able to re-improve, for example, the historical time series with this kind of information, we will then also improve then the estimate on long-term trend, etc. So it's a kind of loop which will be activated. It would be nice.
Yeah. So do we come to a conclusion on that discussion point? I guess.
You had other questions. There's a whole list. I think we only got through the first question out of many.
Right, but on that topic, so what is there a conclusion there that yes, we should go forward with the ensemble in a coordinated manner, as well as look at the physical? And what about the question of what goes into the ensemble? So
we can do both, because we are going to move forward to assemble anyway. And the assemble method is another way to understand the error sources. But we also need to look into the physical background of all these kind of signals. So I think we need to do both in parallel.
Okay. Oh, yes, Donata?
Just wanted to mention that, yeah, I agree with many of the things that have been said, and that I think it is important to investigate how independent or dependent the members of the ensemble are, and to have a parallel effort, as also Matt introduced today, where we can put forward a framework that lets us evaluate independently, like the uncertainties and the different estimates, so that we can have more guidance, I think, going forward on best practices. Some of the things when we do the comparisons are low-hanging fruit for maybe converging or at least accounting for. For instance, like if we are doing an ensemble and we compare different products and want to look at that spread, it would be good that as a one simple thing, like the ocean mask is the same across products, or at least have a comparison with that case and what the spread would look like if we look at the spread as is, as the products come in, and there's and instead if we account for having a common ocean mask across products. Like some of the things I think can be accounted for, or at least be part of that best practices for comparisons. This said, I think that there is a lot of work to be done before being able to restrict the ensemble. I think there is value in keeping the ensemble and gathering all this information, as Matt said. Like if anything, like we would have all the information in one place, and then we can do a better evaluation and gather a better understanding of the positive and the negative of having the ensemble as is. But at least we would be able to understand better if, for one thing, that ensemble represents the PDF we are after to estimate the uncertainties.
Plus also having the same input data, like having the same mask and having the same input data. If we actually did that comparison with all these different mapping methods, then we would know for sure how much of the spread is from the mapping method and how much is from all these choices in the input data.
Yeah, I mean, we did that on a small scale for 2016. We all used the EN4 input, and actually we went a step further, and Katya Dominguez calculated the ocean heat content in 2 different layers and gave that to everybody from the EN4 and gave that to everybody as an input. So So everyone was using the exact same input. So that is something we could do on a larger scale.
Can I clarify something? I think right now you're talking about a multi-product ensemble approach, while you were talking about ensemble method with respect to one product and the uncertainties. Is that not? I misunderstood something.
I don't know that. What we are talking about? I think we're talking about. I'm talking about my ensemble approach for uncertainty estimate. That is no.
Yeah.
Yes.
And that's not. You can use any mapping method in that ensemble. Yeah.
Yes,
it's not. It's not limited to a single.
Yes.
Maybe just one comment to add to that. So there's really kind of fundamentally two different types of ensembles we can talk about in here. So there's like the statistical ensemble. So that's what we talked about. Like basically, we assume we have the mean field correct. We assume we have the covariance premise correct. We assume that that there's no issues with data quality. Once those things are fixed, you still have an ensemble from the statistical answer, and that's what we had in our ensemble. But then there's a separate ensemble which is really about the systematic uncertainty. Which is then XPT corrections and bias corrections and quality control and things like that, and that is not really a statistical ensemble in the same way. I mean, it is still like a spread and it quantifies the answer, but the fundamentally different answer, the systematic uncertainty. We need someone to mute. But yeah, so just for example, the statistical answers you can validate. Like the statistical answers you can validate using, again, cross-validation, for example. So part of this ensemble and part of the answer can be validated. Then there's a whole different answer, part of the ensemble, which I think is more difficult to validate, like XPT corrections and things like that. But again, it's good to keep in mind, really, there's two fundamentally different types of uncertainty in some sense.
Well, thanks. I was just going to comment on Maria's question. I think it's a valid question to ask, but my view is there would be value in having a community multi-center kind of ensemble where we can really capitalize on the wide diversity of products that are out there, and it does need some thinking about, but there are frameworks that we could already use. I mean, I put a paper in the chat and we could use that kind of framework if that that there's still subjectivity in that framework, and there's still the opportunity to make sure that you're not over representing certain products and you've got good product kind of diversity. So I think there is enough flexibility, but it would be something that could be done relatively easily and straightforwardly. I really like Li Jing's work. I think that is the way forward, to go to these big ensembles. But as Li Jing said, within the terminology I would use, the thing that you won't get from that is the structural uncertainty. So that's what I would refer to as all those kind of subjective decisions which are made in other products, might be different vertical coordinate, different grid size, different climatology, all those things that we can do differently. It's obviously hard for Li Jing's framework to sample that part of the uncertainty, but I think it could still be a really useful kind of ingredient within a wider multi-center ensemble framework. And in fact, it'd be really helpful for the parametric uncertainty, because that framework, I think it's really great to isolate these different steps, and to the extent we can understand what the bias what comes out of bias corrections, what comes out of the QC, and even the mapping methods to those things. So I think there's a role for all of these things. But yeah, I would really like to see the community make progress on an ensemble estimate, and starting simple, starting simple with just integrated kind of time series, ocean heat content time series, and maybe potentially using, what I'd advocate is more or less using the approach that was used in AR6, but just broaden it right out to be as inclusive as possible of all the products, and then just carefully select that ensemble method to make sure that there's diversity and that certain methods aren't kind of represented. But I think that's I do consider that kind of a low-hanging fruit activity that we could probably do relatively, on a relatively short time scale. I think that's all I wanted to say. Thank you.
Thanks.
And what about making it bigger by including in the ensemble also synthetic data? So the ensemble could start with real data and also another group of synthetic data for which we know the truth. And the ensemble is run the same way on the real data and the synthetic data. Would that make sense? And that would be a kind of control. It would control some things, because then you can see how the ensemble and what the different part of the ensemble, how they react onto synthetic data. And then you can compare this to what is your result with the real data. It's making the exercise a little bit bigger, but I think it's very interesting to have this kind of, it's not the truth. It won't tell you what is the best in the ensemble, but it tells you a little bit how the ensemble reacts given the combination you have in the ensemble on synthetic data. Would that make sense? And what would be great is that you use synthetic data for which we have also synthetic sea level data and synthetic grace data.
Yeah, I mean, so just to quickly respond, I think that's a great idea. I think it's about partly understanding what the value of the ensemble approaches are. I think that the synthetic data is a really good way of doing that. The only main caveat I think we have to be a bit careful with the synthetic data is when we only have one or two kind of synthetic data sets, we have to be careful that the results we're getting are not kind of peculiar to that kind of specific model simulation that information's come from, because models have biases, they're not perfect. And I think there's been already some comments on that, certainly some kind of caution about the high latitude areas in particular and models' ability to represent those areas. But that said, I think this is a really good path forward. And in the fullness of time, I think we could get a robust set of synthetic profiles. So I think it would be good to pursue both, as you say, Benoit, but I think the synthetic thing is more about trying to understand the quality of the different mapping methods, or rather the strengths and weaknesses, and whether the ensemble methods are in fact kind of better and how they perform. And you might even be able to tune your ensemble methods to some extent based on those synthetic data. I think that's an attractive option. I can see Donata's got a hand up.
Yeah, I just was going to say that, yeah, I think that if, in the framework that Matt presented earlier today, that would be something, completely, I think, very possible to do, to evaluate not only the uncertainty that each product provides, but as we gather an ensemble of products, we could also see how the spread across those products fares in representing the uncertainty. Like if there is, if the ensemble is, under dispersive or over dispersive. So it's definitely possible. And I think it would be a valuable exercise to do once we have enough, products to create that, to evaluate that spread. So yeah, that's a great point. We'll keep it in mind going forward with the synthetic profile conversation.
Can I just add something to this discussion? Something that surprisingly hasn't been mentioned so far is so we talked about the ensemble of different products, but there's also the question that many of these products don't provide uncertainties for that product itself. So we are able to do that now, and there are a few others who provide some measure of uncertainty, but a lot of these products don't come with uncertainties. So I guess that's the zeroth order thing I think we need to require, is that actually these products try to quantify their own uncertainty to start with. And because if you only have the point estimate without the uncertainty, there's very little you should do with that. Even fitting trends and other things, you're going to underestimate the uncertainty if you don't have the uncertainty of the individual data points accounted for. So if hopefully that's one thing we can agree on, is that these products need to provide some estimate of their own uncertainty, and many of them right now do not do that.
Well, that's part of this effort. We provide, the NCI provides an uncertainty, but we know it's an underestimate of the uncertainty, and that's why hopefully this type of ensemble exercise can help us have a more robust uncertainty.
Well, actually, so the issue is that actually no, that's because they are correlated statistically. So like that would, so okay, this I think is a very important point. So this spread gives us an idea of the systematic uncertainty. It does not give us an idea of the statistical uncertainty, because they are using the same input data. So like they're, you know, that spread really is not any measure of the statistical uncertainty. Like they could all be subject to the same statistical fluctuation, and that would be, you know, not accounted for in that spread we are looking at right now.
But I mean, we don't all use the same. We have the same data available, but we don't all use the same subset of the data or the same quality control on it.
Sure.
So yeah, there's correlation there, but there's also big differences. I mean, I believe those are the biggest differences in how the data are used. So, and that is something that the uncertainty due to data distribution or measurement error in the data itself, that's the thing that's really difficult to quantify. I mean, I know you're doing it, but that we don't have. Basically, our uncertainty is an uncertainty on the method, on the objective analysis, going from sparse data to a full grid. But that's only a small part of the overall uncertainty. So, but you say this ensemble exercise couldn't get at the. I mean, one of the ensemble, at least that Li Qing has suggested, is the different quality control. So this would give some measure of the uncertainty due to the quality control each group is using.
Sure. So, yeah, so of course, so there is some amount of uncertainty, or maybe it should be called variation, due to those choices, that's for sure. But like, I mean, just for the kind of the sake of the argument, like let's say that we all use the same input data. So let's remove that sort of variation or uncertainty. So let's say that we had different products using exactly the same input data. So, okay, we would still see a spread, right? So that spread is then reflective of the different modeling choices that are made in the climate lodge and the covariance and so forth. But that spread is not a measure of the statistical uncertainty. And still, I'm talking about the kind of the gap filling uncertainty. That spread would not reflect the statistical uncertainty in those ensembles. So it's really, so again, it's spread into statistical and systematic uncertainty. So this kind of an ensemble between multiple models is a way of measuring the systematic uncertainty, but it would not account for the statistical uncertainty. And you see, like, why is that the case? So imagine that, let's say all of these products made exactly the same choices. So let's say they used the same input data, used exactly the same choices for the covariance and so forth. Well, now you would end up with an ensemble that is at one single point. But of course, that one single point has still an uncertainty due to the gaps that we are filling in. That's the statistical uncertainty. That's, you know, in our language, this is like you have a random field and you're trying to estimate that random field at unobserved locations. So when you, let's say you knew exactly the kind of the statistical model for this random field, used exactly the same input data, you still have an uncertainty because you have clearly not seen this field everywhere. So so that ensemble approach would not account for that uncertainty, which is what each product should report on top of what they're reporting right now.
Okay, just go back to the synthetic profiles Bonova that provided. I think it's a good complement to the current framework to use the synthetic profiles to understand the sampling and mapping issues. But I also say that it is not a simple, easy task. You need to deal with a lot of issues. First, the synthetic method only deal part of the problem. For example, for something biases or Argo salinity drift, that kind of we don't know well issues. We cannot deal with those issues in synthetic profile method. That is the first point. Second point, that you use models, so model have resolutions. So you have to take care of the subgrade variabilities and observation noises to be as close as to the observational profiles. So that needs a huge amount of work to do. So I think for synthetic method, we have, it is good, but we need quite some time to work towards a really useful synthetic profile method. So that's it.
Time check. So we.
Yeah, we should move on.
I was thinking more. We started 2:15, and it's 3:15 now. So should we cut the discussion? Okay. Well, it was a good discussion for me. It was very valuable. Thank you.
Well, I think we move on to session 4. Co-chairs are Gael Forget, Jim Carton, I think you're online, and Seiji Kato.
Yeah, well, so you talk. So yeah. Time. Explain it. Move on to next session. Is a reanalysis technique to measure the EEI and the surface flux component approach. The first speaker is Gail. Well, no, I won't say. Forget. Okay, Gail Forget. The title is Regional Earth Energy Imbalance in the Sunlit Ocean Layer. And soon.
Yeah, and the person from there is in the.
And how do I move forward? Is this with this thing? Oh yeah, there we go. It just stopped. So that's good. Thank you. Great. So hey everybody. Let me start my watch. Well, I'm just doing it. Yeah. So this presentation is going to be about the energy imbalance in the upper ocean layer. And the reason I care for that particularly has been mentioned by others. That's where a lot of the kind of more immediate impacts of global warming and Earth energy imbalance are going to play out in terms of, marine heat waves, marine ecosystems, and so on, climate feedbacks as well. So I'm going to introduce to you the concept of this sunlit ocean layer EI or SOLAE. And to start it simple, we're going to look at the time series of SST. So here is the ensemble that I'm considering, which I think is reflective of sort of the state of the art. So in there is in orange the retrospective temperature analysis from EN4. The green curves that are all sort of hard to distinguish probably are from data assimilative products from the community. And then there is 4 different curves for ECHO, release 2, 3, 4, and 5. Release 5 is the upcoming one. That's the one that goes to 2019. And so the point here, I think, is mostly this pretty coherent across the reanalysis, this whole range. So I think for the global mean SST, I think we have a fairly good handle on that quantity, both in the seasonality, the interannual, and the trends. To my eye, I would go and say the same thing with this one, which is temperature at 300-meter depth. So this is what I'll consider as the bottom of the sunlit ocean layer. It's a bit maybe of an overestimate, but it's a simplification compared to the euphotic depth, if you know what that is. So again, I'd say there is a pretty good agreement across the board. If you look at ECHO specifically, the different curves track each other pretty well. So I think ECHO, if I can comment on that, has been pretty robust across reanalysis, across releases. If I go down to 1,000-meter depth, so ECHO is still fairly well in this ensemble, but you do see that there's more spread, which I think we need to investigate further. There is also a factor that ECHO is maybe a bit on the flatter side here, to my eye, although others might disagree. That's been sort of consistent throughout, so that's something I want to investigate. But for today, we're going to focus on that 0-200-meter layer, where I'm feeling fairly confident that we can proceed with analysis of the physics and of the science. Next step, I'm going to look at this not in terms of the global mean, but in terms of the zonal mean as a representation of spatial variability. Here is the record from NCEI of the product called OISST. This is 1982 to 2023. So you see a very clear kind of widely distributed heating, which you would kind of expect from global warming redistributing in the atmosphere the heat coming down into the ocean, and a lot of signals. So this is latitude and time. You see ENSO signals and interannual variability and so on. If I look at the same thing in ECHO, this is the top panel here. Looks pretty similar to me, qualitatively, and it doesn't start quite at the same point, but otherwise, like I said before, we have a fairly good handle on the SST in general, which is good because that's ultimately the most important quantity probably in terms of feedbacks. At the bottom, you have the 200-meter depth temperature. There is similarity between the two. You also see kind of an increase overall. You can eyeball an increase in average temperature over that depth. But there are also some significant contrast between those two, I would say, qualitatively and quantitatively. You do see the ENSO signals, but maybe the penetration of heat into that depth is already more aligned with patterns of ocean circulation and physics, not globally distributed as much. So now I'm going to do two things. I'm going to take the difference of the two, and I'm going to look at the integral between 0 and 200. The difference between the two in the top right, I'm going to argue resembles quite a bit what you see in SST, right? So my point is that there is a fair amount of SST variability that really reflects a change in stratification. The bottom right panel, that's the 0 to 200-meter integral. And to my eye, that's remarkably similar to the left, to the bottom left. And so my suggestion to you is that temperature at 200-meter depths might actually be a good proxy for the integral 0 to 200, which can be a useful trick to play. Because Argo, for example, samples that depth very well, not the SST. So now I'm going to move on to defining what I will call the energy imbalance in this layer. And I'm going to look at that by differentiating the fluxes across the top boundary condition, the sea surface, and the heat flux at the bottom of that, so at 200-meter depth. Here is the map of the time mean, the climatology of RC heat flux. This is from ECHO. This is pretty robust across estimate, at least the geographic distribution of it. You can find a bunch of papers where we've made that point. One thing that I'd like to draw your attention to, a lot of you know this, but the range is 100 to minus 100 in watt per meter square, right? So this is a huge range compared to the global mean of 1 watt per meter square or a few watt per meter square we've been talking about. So we're ultimately after a signal that is quite small when we talk about the global integral. I should also say that the convention is positive downward. So red means heating the ocean. Typically, you see that the ocean is getting heated up by the atmosphere in the tropics at the equator, which you expect. And you see that there's a lot of cooling when kind of dry, cold air comes from the continent over the Gulf Stream and the Kuroshio and those currents that carry a lot of heat into the mid-latitudes. So this is sort of all fairly well known. Here is the breakdown of what's going on at 200 meter depth. So here you have two panels. The top one is the advective term, and the bottom one is the diffusive term. There is no more downward shortwave because we are at 200. Basically, that's kind of why I'm choosing that, because the penetration of the shortwave stops before that. A lot of features that if you've looked at the ocean circulation and temperature fields, you will sort of identify. In the diffusion, first of all, it's generally positive, which you expect because you have like warm water over colder water, so it diffuses heat down. Advection has contrast as things on both sides. The negative, for example, in the tropics at the equator reflects that there is an upwelling, and so that's also well known. So you end up with a picture where, for example, in the tropics, you're going to have a convergence of heat with heat coming from both sides. So that needs to go, if the system is balanced, this needs to go out. So we're going to talk about lateral transport in a second. And the opposite pattern might happen somewhere else. So the definition of the Sol AI is the difference between the right-hand side and the left-hand side. Might get the sign wrong. So that will be the convergence of heat in this layer, and this is what it looks like. So you'll recognize some patterns we have seen before in talks yesterday and today, with, as I said, a convergence of heat in the tropics near the equator, and instead a divergence of heat in the subtropics that has to do with the advection term for the most part. You also see that if you look at regions of higher latitudes, there's an interplay of advection, mixing, and RC fluxes that's interesting. I'm not going to go in details. There's a bunch of papers that you don't see the reference to, and that I can point you to. And so here's the next component that we need to worry about. This is a bunch of estimates from a paper I wrote in 2019 with David Ferreira, where we did take the heat flux from the surface in echo, and then we got a bunch of other products for that. So we built an ensemble that you're seeing here, where there's maybe four estimates that use a series in combination with an atmospheric model, and there is some estimated kind of corrected flux estimates for the sea surface as well, and echo. Now you take each one of those products and you pass those through what's called the Helmholtz decomposition, which removes, well, first of all, you remove the global mean. You do the Helmholtz decomposition, and that splits up between the divergent component, which you see here, and the rotational component, which is associated, for example, with the ACC carrying water around and around and around. The point of this plot is we kind of know how to get to these quantities. They agree pretty well, ultimately, I would say, in the range of them. The top left is the global mean, and then the others are the ocean basins. So the Atlantic, the Indian, and then the Pacific. The Pacific is the biggest term, and that's what's kind of the main point of this paper. But so we have methods to approach this and analyze it scientifically and make sense of these things. The next step would be to do this not for the vertically integrated water column, meaning not just the RC heat flux, but the convergence of heat in my layer, which you will have to hold your breath until my next presentation. I'm just going to make one more point to finish, and that's there is very different timescales of motions in the ocean that Earth energy imbalance will experience. The part that I'm talking, so this is a schematic from a paper with Ruiz Rousselet and Paula Chessy from 2 years ago. This is the schematic, and then I'll show you some results. For the 0 to 100 meter layer, what matters the most is those subtropical cells that I've been talking about. And so this is the upwelling at the equator and the divergence to the tropics, to the subtropics. But there's also this kind of big global circulation that people refer to as the meridional overturning circulation or the conveyor belt, so on and so forth. And that implies potentially the recirculation, or that's what's going to affect the recirculation of the EI in the abyss. The only point I want to make is once you analyze this and you look at how much time it takes to go from point A back to point A, and in our case, point A was the section in the South Atlantic. So we tracked the water until it came back along the ocean circulation. You get distribution of how long it takes, and that's what's on the right-hand side. And so you see that these timescales go from, if you take a somewhat short route, maybe a couple hundred years, to like 2,000 and even 8,000 to some degree. So the only point about this is when you analyze EEI, you have to account for this complexity of the system, and it's not going to be a direct route and a simple answer in terms of, EEI resurfacing to the surface of the ocean or something. So I'll finish here. I'll give you my conclusions, my takeaway messages. So I found that the global mean SST and temperature at 200 meter depth are pretty robust across your analysis. I've given you a definition of sol EI as the heat convergence between 0 and 200 meter depth. And my argument is that that's a good way to look at this problem for several reasons. Maybe most importantly to you, it's the conduit of the Earth energy imbalance into the deeper ocean. But for me, it's also where the processes and the feedbacks and the impacts that I'm looking for are. Next bullet. The SST, in terms of the zonal mean, seems to reflect stratification changes. Temperature at 200 meter depth may be a better proxy for heat storage in this layer. ECHO and other estimates provides lateral transports and ways to analyze the pathways of Earth energy imbalance that I think will be useful. There's one thing I mentioned here. You don't see it, but I'm looking for a postdoc to hire a postdoc to work with me on these problems at MIT. A few more that are maybe a bit more questions to address in the future and things that tend to worry me a bit. By 1,000 meter depth, it seems that when I look at my ensemble, the spread increases. So there's, in my eye, more structural uncertainty there. The echo trend for temperature at those depths maybe is a little weak. I'm not sure. It remains to be proven, and Ian will talk more about this, I believe. The deep EI recirculation timescales will be taking forever. And we will get back to the question from before on the dip. I'll show you what I had. In case you didn't see it. All right, so at 200, you do have at 1,000 you don't. And in my eye, that's kind of consistent with this kind of advective scenario. You have to reckon that the thermocline actually crosses this 200 meter depth in the tropics. And so the shifting of the thermocline under the winds that are responsible associated with ENSO might in fact explain what you see in 2016. With this, thank you for your attention, and I'll take any questions. Hopefully I still have time. Oops, sorry. Do you have time for questions?
So, I mean, first, why did you choose 200 meters as the sunlit layer?
That's so the more maybe mechanistic definition, or the one people like, is to look at the depth at which you get to 1% of the shortwave. That's so-called the euphotic depth. That's the practical definition of it. It's around 100, maybe a bit deeper. Basically, I kind of rounded it up to 200 to make my life simple. I didn't want to go deeper. Could have probably taken 150, but I feel 200 is good enough.
Okay, thanks. And you said, so you see at 200 meters, the big drop in heat that's seen in the in situ, but you don't see that at 1,000 meters?
Right.
But in all the in situ, you see that.
I mean, it's not a big dip to start with, right? It's something that, is like the other dips.
Yeah. But that in the in situ, you see that in the whole, integrating over the whole 2,000 meter layer. You're saying here you don't see it at 1,000 meters?
Yeah, it's not in these guys. I mean, it's not just me, right? So if you look at EN4, it doesn't have that either. I think, if you integrate from that to below, you must still see the same thing, right? If it's a lateral displacement, right?
Okay. So
if you're here and you just shift the thermocline like that, you will see the heat anomaly here, but in the integral, just set up. I think, Ian was going to go back to this in a minute, right?
Thanks.
Yeah, no worries.
Yeah. Just to clarify, for your recommended depth, is it 200 meters? Is it the integral of heat in the upper 200 meters, or is it temperature at 200 meters? I think it was your penultimate takeaway.
So what I'm saying is, what I'm after ultimately is the storage of heat in this layer. So that would be the integral. But I'm also after changes in stratification and heat that accumulates near the surface, because that also has very different set of impacts that are also quite crucial. Now, my point about the temperature at 200 is that it's a good proxy for what's on the right-hand side on the bottom. So if you don't have, which is not necessarily easy to get, a proper integral to the surface to 200, at least we can use temperature at 200 as a proxy. Any other questions?
Could I ask a quick question online?
Yeah, please.
Can you hear me? Hi. Great talk. Thanks.
Thank
In the plot you were just showing about the 1,000 meter depth, the Echo, the latest, not yet released Echo version seems to set apart from the other lines, the other versions of Echo, especially like towards the beginning of the time series. Any idea why?
I have not diagnosed that yet. I'm not sure.
Okay. Thank you. Yeah, look forward to this version to be released.
Yeah, hopefully it's out soon.
Gail, this is the,
Awesome.
you remove the time mean from all of these, right?
Oh, yes.
I think that's what it is. I don't think it's the early period that's different. I think it's the later period that's different, but Gail removed the time mean from all of the curves.
Yeah, and now that you say it, that's probably true. Cool. Thank you for that.
Thanks for the clarification.
Oh, maybe one more?
Yeah. To which extent are you confident in your fluxes at high latitude? And if you're not very confident, what can you say about the deep circulation? Because it's mainly driven by fluxes at high latitudes, isn't it?
So what fluctuations are driven by the high latitudes?
The deep circulation.
Ah, okay. Yeah. Well, so there's different places where we have different level of confidence. So the Atlantic, we are sort of comfortable with that. The place where I'm most doubtful is the Arctic. We do have a fairly good match to the sea ice cover and the way it fluctuates over seasons there, as well as in near Antarctica. So we are relatively confident with that. We also don't have a huge trend in the AMOC or anything like that. Right? That would be a signal of something, an imbalance in fresh water or something. So these are, terms that I think is really what we need to clarify. So I think it's a very good question. I think the geography is, we are fairly confident. The way that we calibrate the global mean heat uptake, relies on other products. So we know that it's kind of aligned with the others, but it's possible that, we're not doing that quite right. So I think, it's part of why I'm sort of pushing this idea is, we're thinking of RC heat flux, which is uncertain in itself, available from a bunch of products. But in a way, I'd be interested in focusing more on what's going on through 200. Because it's a little simpler. Mechanistically, at least, on the physics side, for the ocean part, we kind of understand the processes. The parameterization of RC fluxes, as I'm sure you know, is very parameterized. It's quite uncertain, and if you play with it enough, you can create whatever heat flux you want. So on some level, I think the 200-meter depth flux is a good indicator, something that could be diagnosed a little bit like what people do with the Earth energy imbalance by taking a map of, RC heat flux and subtracting some ocean heat content trend, which I think would be an interesting thing to intercompare across estimates. I'm not sure if I fully answered, but that's my take on it. Good? Thank you all.
The next talk is online. Oh, sorry. Next talk by Andrea Storto. The title is Assessing Ocean Heat Content and its Uncertainty from Ensemble Ocean Reanalysis.
Okay. Okay, so I'll be talking about temporal extension of reanalysis, and well, as we know, as we have seen these days, there are many ways to estimate ocean heat content, from statistical mapping, simulation reanalysis, indirect method. We talk about geodetic approach. There are also acoustic measurements that provide complementary information, plus IE reconstruction. I will focus on reanalysis, and I just want to stress that reanalysis do not only provide, of course, a reconstruction of the ocean heat content, but as we have seen this morning, they may be used for, they provide a multivariate reconstruction, so they may be used for a number of applications much broader than the ocean heat content reconstruction, from downscaling, downstreaming, initialization of prediction, plus process-oriented studies. We have seen this morning analysis of advective and diffusive fluxes, for instance. Just as a, let's say, motivation, a few years ago we ran ocean reanalysis intercomparison, and I think one nice outcome, if you look at this picture, this is the difference of the correlation between an ensemble mean of ocean reanalysis against static sea level data estimated from altimetry minus gravimetry, minus the correlation of an ensemble mean of objective analysis. So we found that basically in the Southern Ocean, reanalysis outperform on the 93 2015, if I remember well, objective analysis. The speculation is that in areas with poor observational sampling, we still ingest information from the atmospheric force. So for instance, ventilation in Southern Ocean can really shape the interannual variability. However, of course, we know we do have, especially in the vintage of 10 years ago, we have a large spread in the global signal. You see the thermosteric and allosteric on the right. I think, as I mentioned before, reanalysis can also be good for combining different sources of information. In this example, for instance, we tried to assimilate series data in ocean reanalysis, and this turned out to rectifying the red line compared to the gray line, the deep ocean warming. Of course, this is somehow by construction, because we are trying to combine all together, optimizing the different information. And this can be done also in a more recent study through variational minimization of static sea level data, series data, oceanic content from in situ, each one with its own level of uncertainty. So the minimization by construction will combine all the data. We see, for instance, the 2016, by the way, there is an increase in the deep ocean content, and this is by construction again, so we cannot be sure it's for real. The other point is that if you compare the uncertainty level of the observational data set in black with the one coming from the optimization procedure, we also have a higher level of accuracy coming from the interaction between the different observing networks. And also for historical analysis, for historical investigation, I believe reanalysis, when they are used in an ensemble context, can provide interesting information. In particular, here we use 4 different families of reanalysis with 4 members each, and we compared the 1900 to 2010 oceanic content with CMIP6 simulation in red, and another reconstruction from Zanna through Green's function. And basically what we found is that the interannual, the subdecadal variability in reanalysis as a signal that is filtered out in model-only reconstruction. So this is something interesting to investigate further. So we recently set up an ensemble reanalysis system at moderate resolution, 1 to 1/3 degree, but focusing on the extension of the temporal dimension and ensemble dimension. So 32 members and as I said, 1 degree of resolution. Just to keep in mind that going to this is basically computationally half of increasing the resolution to a 1/4 resolution. So of course we will miss, for instance, the contribution of eddies to the meridional transport, which is an important component, but here we really focus on trying to estimate the uncertainty, as was discussed before. And with this system, we try to have 1 stream of production, which we call contemporary, forced by ERA 5, and 1 other stream that now is only preliminary historical period, going back to the mid of 1900 using the 20 CR atmospheric reanalysis. And we also run what I call an objective analysis system, where basically we use the same data simulation but without model integration. And I will explain you why we also have this system. So it's important in this context to characterize the sources of uncertainty. And in this ensemble, we try to do so by allowing different realization of the atmospheric forcing, of the SST dataset, of the in situ observation dataset, also different initial condition for the reanalysis period, and different bulk formulas, for a total of combining all these sources of uncertainty for a total of 32 members. Plus we have stochastic modulation of the model, ocean model parameters, which is one of the latest release of NEMO, and also stochastic perturbation of the observation. So focusing on the contemporary period, 1 result, it's our analysis in black compared to the in red, the recent oceanic content ensemble from the GCOS assessment. What we found is that there is a larger acceleration in the ensemble analysis and a more pronounced interannual variability. There are some statistics here in the table in terms of trend, interannual variability, and acceleration for our ensemble analysis and for the GCOS assessment. So the main question here is if whether this enhanced variability is somehow an artifact of the reanalysis system or not. To do so, we try to reproduce the same, maybe it's not so visible from the audience, but the bottom left panel, on top of the ensemble analysis, there is in blue, there is the objective analysis, which is using exactly the same data assimilation system, but doesn't have the model integrations. Basically, climatology as a background, we use a climatology to which is added the persistent anomaly. And basically, if you compare the ensemble analysis with the objective analysis, we do have very close values for interannual variability, acceleration, and trend. From this objective analysis system, we made some small changes. For instance, we decreased the correlation length scale in the yellow experiment. We use a monthly frequency of update instead of 10 days. In orange or in green, we use a background, so a first guess for the analysis coming from a model simulation. In all these examples, we have really attenuated the interannual variability and attenuated the acceleration. This, I think, is an indication that that value of acceleration is not an artifact of the reanalysis system, but it comes with the specific setup that we use. And for let's say more recent period, probably these values are not up to date compared to yesterday's talks, but the acceleration for the entire 61-2022 period is estimated equal to 0.15 watt per square meter per decade, and on the shorter 2006-2018 period to 0.20, which is only partly in agreement with different estimate, but probably the one from 2019 has a large uncertainty. Okay, with this ensemble, we can have a different statistics using, again, the ensemble as a measure of statistical significance. As an example here is the areas, statistically significant areas where 2022 is warmer than 2021, meaning that there is no obvious area of warming at global scale. And another statistics is to identify the year, the warmest year per, in this case, model reanalysis grid point. So we found that 2022 was as more than 11% of the global ocean having 2022, sorry, as the warmest year. So almost doubling any previous year. So it's another indication of warming acceleration. So in terms of uncertainty, this plot shows the oceanid content normalized uncertainty, where normalized is basically the ensemble spread normalized by the natural variability of the oceanid content. And we see that before the Argo period, our in black is the global ocean uncertainty. We are around 40%, decreasing to 15%. Now the gray is instead the GCOS assessment, meaning that the uncertainty is much more, is probably smaller on the average, but much more variable along years. And also this calls probably, as we discussed before, to also validate the uncertainty that is coming from our product. While for analysis, quite more steady, let's say. The last diagnostics is about regional trend. In particular, as also Li Xing showed earlier, we can cluster the ensemble member to identify the most important sources of uncertainty depending on the study region. In this map is basically shown the statistically significant prevailing source of uncertainty among the one spanned by the ensemble, and as a interesting summary, although I mean the plot is a bit scattered, but we found that at high latitude there is the dark blue identifies in particular the bias correction method of MBT and XBT as a prevailing source of uncertainty, while at mid-latitude the SST dataset in general seems to prevail. Okay, the last point is some preliminary result from the historical analysis. Here you see the red line showing the historical control run, which means without data assimilation, and in green the historical reanalysis. In orange the contemporary control run, and in blue the reanalysis. While in gray it's just as a reference the EN4 objective analysis. Couple of comments is that there is very strong consistency in the overlapping period, although the two systems use very different atmospheric forcing, meaning that even in the 60s there is robust information coming from the observation. Another point is about the warming that we see in the 30s that we need, of course, to investigate more. Although, for instance, if you look at sea level tide gauge based reconstruction, there is a multi-decadal variability that generally shows a warming period in the 30s. So I cannot say this is for real. We need to investigate clearly more in depth about that, but the main message is that even sparse observations are able to shape the oceanite content variability. And this can be seen also in terms of standard deviation of yearly tendency of oceanite content, that in the here is reported the standard deviation during the first half of the 20th century, meaning that the analysis has almost more than double content tendency variability and the control simulation, and a bit less than double other objective analysis. Okay, so just to summarize, I mean, I presented some preliminary results about an historical analysis system, some more robust about contemporary period. I think, I mean, of course, going back in the last 150 years is extremely challenging for any data simulation system, but what I want to stress that still sparse observation can provide non-negligible tendencies and statistically significant tendencies. So, of course, from a physical point of view, this needs to be investigated a bit more in details. While in the contemporary data set, a large ensemble really allow to rank the sources of uncertainty. So, of course, the design is different from what we saw before, in the sense that for analysis there are a number of input data set larger than an objective analysis. So it's not only, for instance, bias correction of the in situ profiles, but also the atmospheric forcing, the model physics. We try to account for all the sources of uncertainty, but of course the ensemble limited. But I think this is, however, an interesting way to extend their analysis instead of going really towards high resolution, but extending the ensemble dimension. Thank you.
Thank you, Andrea. I have a question because my recollection from Matt Palmer's paper on an ensemble of free analysis and also the community paper we wrote in 2019 is that there was much larger spread across free analysis, and it was mostly because of divergence in reanalysis in the deep ocean warming. And it doesn't seem to happen in your ensemble. Can you comment on that and explain why?
Well, there are a few reasons. I think the main reason is that those family of most of their analysis joining that intercomparison were designed for initializing seasonal prediction, for instance, which means in practice, most of them, they started in 93 with some climatological initial condition. This system, I'm not saying is better. I'm saying it's more designed for this kind of study. So we try to have a very long spin up in order to balance the ocean state with the atmospheric fluxes. And the spin up is different between the, of course, contemporary and historical period, because the fluxes between the 20 CRV3 atmospheric analysis in the era 5 are quite different. So doing that, I think we can reach a convergence between the ocean state and atmospheric fluxes, which avoids the issue. We do have also large-scale bias correction, but I didn't show you. It's more to avoid that salinity may drift, since in most of this period we have temperature measurement, not salinity, and the system is multivariate. However, comparing the impact of the deep ocean relaxation is quite negligible. Indeed, it's very different from EN4, which is a data set that is relaxed 2 at depth. The trends are very different, and also the control run is quite different without the relaxation. So I think the key is mostly the spin up rather than other technicalities.
That means that next time, if we use them to evaluate the ocean heat uptake, we should take reanalyses that have a spin up sufficiently long. That's what you recommend, right?
Yes. I mean, there may be different ways to spin up in a general sense. Could be a bit constrained with future data. There may be different technique, but this could be a possibility, yes.
So if I understood correctly, diagnostic. Have you looked at some big of a spread you can?
Not the RC fluxes. It's not necessarily a diagnostics, in the sense that the ensemble use two different atmospheric forcing realization and two different bulk formulas. So this will create a spread. Of course, the bulk formulas tend to balance again the fluxes. But I didn't look much. Maybe there will be some material in the Jim's presentation about that. But yeah, thanks.
Oh, there's a lag. Okay, thank you.
Talk is by Ian Fenty, and the title is Ocean Heat, OHU, 1992 to 2022, from the latest ECHO Global Ocean State Estimate and implication of outstanding observational data misfits.
Okay, thank you. Oh, hello everybody. I'm new to this community. It's been really interesting, and forgive any major lapses. Understanding of what I'm going to present today. The work that I'm doing, I'm representing ECHO at JPL. I work with Ichiro Fukumori and O Wang. Patrick Heimbach contributed to this talk, and of course Gael. So for those of you who don't know, the goal of ECHO is the 20-year goal of ECHO is to understand, describe, and forecast the global ocean and understand its role in climate change. And the motivation really is that despite global coverage, ocean observations are sparse in time and space and sparse relative to many dynamical scales of interest. And the idea is that when we combine ocean observations and physical models, we get estimates of the time-varying ocean that are better or / more complete than the data or the models alone. And here, this community is well aware of the sparsity and types of data. This has been the topic of many talks. And I'll skip this because you guys are all well aware of it. And this. A distinction of ECHO versus other ocean reanalysis systems is that the ECHO reanalyses are they do not use sequential assimilation. And here the way that we put it, one term that the community uses is continuous assimilation. And the idea is that over ECHO's 30-year time period, we do not adjust the ocean state at all. The solution is a free-running ocean model. The only thing we adjust are the initial conditions, the atmospheric state, and a set of time invariant mixing parameters, and those are essentially parameterizing unresolved mixing. So the final solution is well represented by this blue curve that shows that we fit through time observations, which are indicated here by red X's. We fit observations in a least squares sense. We generally fit them worse than an objective mapping or a sequential filtering type of system. But the benefit is that we can trace the origin and evolution and fate of anomalies of heat and salt and so on and so forth. So we think this is a valuable feature that makes ECHO solutions useful for studying the mechanisms of ocean variability. There have been a couple talks already today that utilize this aspect of the ECHO solutions, most recently from Gael 2 talks ago. So some ocean reanalysis systems that were discussed today use Argo data, some use Argo plus CTDs. For ECHO, we really endeavor to use all available observations. So I want to mention that we do use ice-tethered profilers. We use instrumented pinnipeds, Argo, of course, CTDs from WOS and Ghost Ship, as well as GRACE follow-on, all ocean altimeters, sea surface temperature, sea surface salinity, a huge suite of observations to the best of our ability. And these observations are used to constrain the solution of a 1 degree global ocean model, the details of which I'm available to discuss if anyone would like to. Okay, so I include, this is a little bit of a lag, I include this animation, this beautiful, smooth animation, to not to convey to you that the solution matches the data, because you can't see that in here, but in the bottom right, it's meant to show you, on my screen, I assure you it's very nice, a smoothly varying vertical velocity field. And this vertical velocity field is super important for us because this is a big part of what moves heat through the ocean, this vertical transport. And the movie is available for anyone who wants to see it. But this, Gail and I didn't coordinate this, but this exact field is what Gail was just exploiting for his analysis, and Donato was using earlier. Okay, so now it's time to convince you that the ECHO solution is useful for this community for EEI. Okay, so what I'm plotting here are global mean sea level, that's in the top, and global mean ocean bottom or ocean mass as represented by sea level. And the most important point here is that a solution to the global ocean circulation exists that matches altimetry data and GRACE data, at least in a global mean sense. So the question of, can GRACE data and altimetry data live together to help us understand what EEI is? Provisionally, the answer is yes. The GRACE data is not without error. I exclude a period at the end of GRACE where we know the satellite had trouble and the data is less certain. And of course, altimetry data is sparse in some sense, but to first approximation, the ECHO can reproduce those data. This next plot is just to give a sense that the match to the data is more than just in the global mean, that if you look generally around the planet, we can reproduce the time variable sea level, which of course has a huge steric component. So this really is meant to convey that ECHO matches on the global sense time variable steric variability of the ocean. I'll skip this one for the interest of time. Now, as people are well aware, and as I've mentioned, we constrain the solution to Argo data, okay? And we don't constrain the solution to a gridded Argo product. We constrain it to the individual Argo profiles. But on the aggregate, what I want to show here is the reproduction of the time mean heat and salt trends. This is between 0 and 2,000 meters. I apologize that the caption is a little truncated. The point here is that on a global scale over the Argo period and over the Argo depths, that we can reproduce at least the linear trends. The patterns are there. There are differences in the magnitudes if you look at any one place. We have looked at the places where the trends look the most off. Those tend to be places where the Argo data is itself sparse or odd at the beginning or end of the period. In general, we match the Argo data quite well. Okay, now I'm going to do a little foray into this Argo question because I know some of the community here does not work with the Argo data, but I think this will be super instructive for those. So I'm going to just go from like the coarsest to the finest of looking at Argo, and I picked a point here in the north central Pacific. Okay, and on top, this is a time and depth plot of temperature. Excuse me, I didn't label it, of temperature. The top is from the ECHO solution, and the bottom is from Remick and Gilson, which is a gridded Argo product. And quickly by eye, you can see where there are anomalies that they are broadly reflective in both ECHO and in the Remick and Gilson product. Now I'm going to focus at two different depths. At 100 meters, which is within Gael's sunlit layer, and at 1,000 meters, which is right in the middle of the Argo. So now I'm plotting time series at the 100. First, we'll start at 100 meters. And what I want you to notice is that in the sunlit layer, a place that is within the seasonal mixed layer in this part of the world, that ECHO reproduces reasonably well the seasonal and interannual variations. There are differences with Remick and Gilson, as to be expected. Why? Because Argo is sparse, and Remick and Gilson, in fact, all ocean reanalysis products that map the data have to make choices, and some of these data are filled in. So right at this level, one can't tell which differences reflect a shortcoming of echoes matching the data, and which reflect something about the mapping methods used in the Argo data. So at 1,000 meters, the seasonal variability is much smaller, and I've removed the time mean because indeed ECHO has like a half a degree or a third of a degree, I can't remember what it is, offset compared to the Argo data. But the point is that now we see that in the most of the differences, the low frequency differences, are also match pretty well ECHO and Argo. Okay, now this is the most important plot. This next one. This shows you the Argo data in a 3-degree radius around this point at 1,000 meters. Okay, so the Argo data, the blue X's. Okay, this is at 1,000 meters. The blue X's. To some, this may be really surprising, right? Because the spread of this Argo data, it super exceeds anything you see in the Remick and Gilson product, and it'll exceed anything you find in any mapped ocean product. So, and then you see just see that the black line, the Remick and Gilson mapped product, its spikiness through time is not driven from one moment to moment from the observations, right? Not at this point, not within 3 degrees of this point, right? These at this depth, much of the spikiness in the Argo product of this ocean map product is from the mapping method itself. So to the extent that ECHO reproduces the low frequency, or disagrees with the Remick and Gilson product, or disagrees with the Argo data itself, is in some sense a feature, because we're smoothing the solution in a way that's dynamically consistent against this background of noise. Okay, so now get into the solution with respect to EEI and ocean heat content. First thing I wanted to point out, because it came up a few times in the most recent discussions, is that we do not see a cooling in 2016. Although I did plot it earlier, we do see a cooling from 200 to 400 meters. There's a very clear signal of cooling 200 to 400 meters, and a little bit below, but that's offset by a warming above 200 meters. We can show, and if anyone cares, I can show you more detail what the ECHO solution looks like. I think we disagree with a time series of ocean heat content from Remick and Gilson or NCEI, because we have more of an acceleration after 2017 than is seen in just in the mapped products alone. I did my best to kind of reproduce the EEI implied from ECHO and superimpose it in this plot, which was shown on day 1, using the same approach, to the best of my ability. And I thought I was heartened that in general the ECHO solution falls within the generous uncertainties of this solution, that there's a kind of a dip in 2010 and it goes up again in 2019. The details of the wiggles are different, but maybe that doesn't mean that it's wrong per se. It's another solution that falls broadly within these uncertainties. Okay, the envelope. Okay, last thing I wanted, the last cannibalization of a nice plot. I took this 2022 Shukman plot that compiles different ocean heat content trends from different reanalyses, from different methods, and I superimposed these yellow stars that show where our latest solution is. So, at some depths for some time periods, we fall within the fairly generous spread of other solutions. Okay, and this plot, I thought it was helpful. It was helpful for me to understand the kind of the scale of the problem that this community is facing. The large amplitude oscillations on this plot are the net ocean heat flux for the whole ECHO solution. So it's dominated by a huge seasonal cycle, right? Dominated by a huge seasonal cycle of 30 watts per square meter amplitude, right? And the difference between the median solution, the median of all the solutions that Shukman considered, and the ECHO solution is the difference between the red line and the blue line. So lines that are so close together that they're almost indistinguishable compared to the amplitude of the seasonal cycle. So, the ECHO state estimation system wasn't designed to solve the EEI problem, but it seems like it could be useful for helping understand why there are anomalies from one year to the next, and it seems like it's a respectable contender in the family of solutions. This other feature of ECHO, Gael talked about, and others talked about the fact that we can close the budgets and trace the fate of anomalies. It's already been discussed, but it's a nice feature and worth exploiting if it's of interest. So I showed in the beginning that ECHO matched pretty well the global mean altimetry, global mean GRACE. Felix mentioned on the first day that GRACE solutions are undergoing, continual revision. He showed a nice, what seemed like a large-scale anomaly that can be traced to GIA, for example. Altimetry data, JSON3, wet troposphere, these kinds of corrections are continually being made. So the ECHO solution is only as good as the data to which we're constraining it. If there's a sudden revision of GRACE or of the altimetry, or someone finds another huge issue with Argo, we only use delayed mode, by the way. If someone finds a big issue, then when we reconstrain the model to those data, we will get a slightly different solution. So we can report that given the altimetry and GRACE and Argo data that exist today, we get about 0.79 watts per square meter over the altimetric period. We would love to be able to provide our own envelope of uncertainty for these estimates. It's a work in progress / it'll come when Fusion also becomes available. No, but it would be nice if we could work with some folks here, other folks, to maybe figure out methods to put uncertainties on our estimates, because I think that would be of interest. And I didn't really have time to go into it, but our deep ocean and our polar seas, the solution is constrained to observations where there are no or almost no observations. We can't expect the solution to do very well, or to be necessarily considered better than other estimates. William Lovell recapitulated a nice papers result from on a day one about the abyssal ocean steric trends. I wouldn't give too much credibility to the echo deep abyssal steric trends because the model down there is not constrained. But when deep Argo comes, then it'll be a new day. Okay, thank you very much.
Sorry about that. Maybe I'm talking too much. Just one comment and one question. So you said ECHO is not designed to do this ocean heat content globally, but I would say ECHO is doing very much as what it's designed to fit to altimetry grace and Argo, and it is adjusting the fluxes at the surface. So it is doing somehow, I would say, a little bit like Lehman and Johnson, which is using altimetry and Argo to get the ocean heat content. So that's a natural product, I would say, I would expect from ECHO. So it's not designed for, but it's very well designed to do it, even if it wasn't your objective at the beginning.
Yeah, I think it's convenient.
Yeah.
that this tool, that this approach seems to be useful for this community.
And so my question is, why not using it the other way around? Do you have, for example, you have what ECHO is refusing as data when you have data which is not consistent, and so at the end of the record, when sea level is not closing, ECHO is probably refusing some data, either from Argo, either from Grace, or from sea level. Well, most probably from between sea level and Argo. Do you have some hints on which data it is refusing, sea level or Argo?
Grace.
Grace.
I'm biased towards altimetry, but I can give you a very brief anecdote. I don't know if Felix is online, but there was one of my colleagues identified a misfit, a persistent misfit in the Grace, and he pointed out it seems to map pretty well mid-ocean ridges. So it was, the way Ichiro put it, it probably isn't ocean dynamics. It's probably something related to a change in the crustal mass along the mid-ocean ridge that Grace, through its processing, projects that misfit into the ocean. So it seems to happen on it. We can see some discrepancies. I'm picking on Grace in this example, but we can find some discrepancies that we can then trace back to some issue with the data.
Have you published that have you published that?
Oh, that's a discussion between Ichiro and Felix. Yeah.
So how sensitive are you to the surface fluxes? Have you looked at different sources of surface flux?
Well, I can tell you what we do, and maybe that'll help contextualize. We start with a first guess atmospheric state. Through bulk formula, it provides us a first gas flux. What we then do is adjust the first gas atmospheric state in such a way that the resultant fluxes give us an ocean solution that matches the data. So if we were to just take a different first gas, a different reanalysis atmospheric flux product and rerun the model, based on my experience, we would not, in no reasonable way, would we fit the global ocean heat content trend as well as we seem to, because these atmospheric reanalyses are designed for a different purpose. They're not designed to help ocean models exactly match ocean observations. It's the same thing. It's more severe with precipitation. Pick any atmospheric reanalysis precipitation, drive the ocean model with it. Sea level will do insane things because those products are not designed for the ocean modeling universe. They're designed for forecasting or another community.
Yeah, comment more than a question about the data gaps on the polar oceans, at least from the altimetry perspective. So there's been a huge effort by the Copernicus sea level TAC to produce polar ocean data sets that cover even the ice covered areas of the polar oceans. So this is only available from 2013 online at the moment, but we're currently reprocessing back to the start of CrowdSat 2. And maybe that can help bridge some gaps in this.
Well, thank you so much. Is it a long track data or is it gridded data?
Both are available.
Oh, thank you very much. Yeah, great. Thank you.
What we said that we're going to start, but we are starting in a few minutes. Zhang Kun-wan, is he here? Online. Oh, so
yes, I'm here
Zhang-kun?
online.
Oh, I'm sorry. Okay, now can you share your screen?
Yes.
Okay.
Can you see my screen?
Yeah, we can see. And we can hear you.
Okay. I just put it in the presentation mode.
Yeah. Everything good. Go ahead.
Okay. Hello, everyone. Today I'm going to talk about the warming trend and the ocean heat balance in the Gulf of Mexico between 1970s and 2020. My co-authors are Jim Boyer, Jim Regan, and Pat Hogan. We are all from NOAA National Centers for Environmental Information. So the motivations for us to conduct this study is, although Gulf of Mexico is one of the most ecologically and economically important marginal sea, but there were few studies specifically on the warming trend in the Gulf of Mexico. Some limited studies either focus on the sea surface using satellite observations or study the deep water warming using mode observations. The warming between 0 and 2,000 meters in the Gulf of Mexico is still not quite clear. Studies already found that warming can affect many aspects of the natural environment in the Gulf of Mexico. This includes ecosystem change, intensified hurricanes in recent years, and formation of marine heat waves and cold spells, and also accelerated sea level rise. So in this study, we will first quantify the warming trend in the upper 2,000 meters in the Gulf of Mexico, and then examine the heat budget closure to improve our understanding of what controls the warming in the Gulf of Mexico. The data we used are all from the World Ocean database. This plot shows the temperature profiles at sea surface for every 5 years. As you can see in most of the 5-year period, the data has good coverage of most regions of the Gulf of Mexico. The color change, you can see the evolution of the instrument. In total, we used more than 192,000 profiles in this study. The methods we use is running pentadal objective analysis following Levitas et al. 2012 paper. We calculate the graded temperature anomaly by removing the monthly climatology value. And then we use the equation on the right to calculate the ocean heat content for each grade. Then the warming and cooling trend can be determined by the ocean heat content change over time. Now let's look at the sea surface warming trend. This plot shows the average sea surface temperature anomaly. The Gulf of Mexico line is shown by the red lines. As you can see, the warming roughly started around the 1970s, and there's a continuous increase trend. The temperature on average has increased about 1 degree over the past 50 years. So the average temperature increase is about 0.19 degree per decade. This is comparable to the previous estimate based on satellite publications based on these papers. It is about twice that for the warming rate of the global ocean, which is shown by this black line. So the warming at surface in the Gulf of Mexico is much faster than the global ocean. For the subsurface warming, in this plot, we show the integrated ocean heat content as a function of time and depth. And on the right, the black profile shows the ocean heat content change with the time as a function of depth. The largest warming occurs at the surface in the upper 50 meters and then decline with depth. But all the values in the upper 2,000 meters are greater than 0, so which means that warming can be detected at any depth in the upper 2,000 meters in the Gulf of Mexico. There are also warming cooling oscillations, like cooling, warming, then slightly cooling. So, and the oscillation can be seen better by the bar plot. The overall Gulf of Mexico warming is about 8.86 watts per meter square, which is comparable to the rate for the global warming. There are also spatial variations of the warming cooling trend. In the upper 50 meter, it seems like the western Gulf of Mexico and the eastern Gulf of Mexico has a larger warming trend than the western and the south has a warmer trend than the northeast. Between 50 and 600 meters, we even see a slightly cooling trend in the northeast Gulf. Below 600, warming occurred everywhere and becomes more uniform. To understand what controls the warming, we conduct a simple ocean heat budget analysis. The heat storage rate is balanced by the net surface heat flux at sea surface and the advective heat flux through the two narrow strait. Gulf of Mexico is a semi-enclosure basin. It has only two narrow straits, Yucatan, China, and Florida. Strait of Florida connecting to the surrounding oceans. So for the advective heat flux, we can estimate the advective heat flux in and out at the two narrow strait to estimate the advective heat flux. For the heat storage rate of the entire Gulf of Mexico, it can be estimated using the integrated ocean heat content we estimate from the World Ocean Database, which is about 1.38 terawatts between 1970 and 2020, or 1.76 terawatts between 1992 and 2017. The periods of echo, which I'm going to discuss more in my next several slides. In this estimate, we also consider the heat storage rate below 2,000 meters, estimated by Otto et al. 2021 paper. The net advective heat flux is estimated using this equation. In this equation, V is the loop current transport, which is measured to be about 27.6 severe drop on average. Delta T is the climatological temperature difference between the Yucatan channel and the Strait of Florida. We estimated from the climatological temperature profiles averaged over many years. And then we estimated the net advective heat flux is about 40.7 terawatts. The advective heat flux is much larger than the heat storage rate or the warming rate. It indicating that the Gulf of Mexico needs to lose heat to the atmosphere at a rate about minus 38.9 terawatts. So the next step is we estimate the annual net surface heat flux. We examined 4 data products: soda, OA flux, ERI-5, and ECHO. And the plot on the right shows the annual average net surface heat flux. 4 products showed similar spatial patterns. In the northern and eastern Gulf, the ocean loses heat to the atmosphere, and ocean can get heat from the atmosphere annually in the southern Gulf. The average value for the net surface heat flux annually is positive for soda and OA flux, which means gaining heat from atmosphere. The ERI-5 and ECHO are losing heat to the atmosphere. ECHO has a much larger area of losing heat to the atmosphere. Further analysis showed that the annual net surface heat flux is the only one that can roughly close the heat budget. So the net surface heat flux from ECHO is about minus 37.9 terawatts, which is very close to the value that we needed to close this simple heat budget. As Gil and In presented just 2 presentations before me, ECHO data is based on a nonlinear inverse modeling framework that satisfies both ocean dynamics and data constraints. That might be the reason. The warming can cause a number of consequences in the Gulf of Mexico. It can cause thermospheric sea level rise. It may also change the stratification at the mixed layer depth, might change the circulation, also can change the deoxygenation and warming may also related to the recently intensive hurricanes in the Gulf of Mexico, and studies has already found some ecosystem change. There are 2 recent papers, both published about a month ago, showed there are accelerated sea level rise in the Gulf of Mexico after 2010. The sea level rise in the Gulf of Mexico and the southeast U.S. coast can reach about more than 10 millimeter per year, which is about 3 times larger than the global average. During the same period, our sea surface temperature from World Ocean Database also showed a significant temperature increase after 2010. So we further investigated the steric sea level rise. We can see that after 2010, there's a huge temperature increase, about 0.5 degree in the upper to 2,000 meter, and there's also an obvious salinity increase. The calculated sea level, steric sea level rise is roughly about 5 micromil per year. This is still smaller than the total sea level rise found from the tidal gauge, but is account about 50% of the total sea level rise. And in the Gulf of Mexico, we can also see that the halosteric sea level rise might have a significant contribution to the steric sea level rise. There are other factors like vertical land motion, coastal wind, water mass increase, and fresh water input. Those can also contribute to the sea level rise. We just started this analysis, so this is just some rough result. In summary, prominent warming trend can be found between 1970s and 2020 in the Gulf of Mexico in the upper 2,000 meter. At the surface, Gulf of Mexico warms at a rate approximately twice that for the global ocean. But when integrated over the entire water column, the warming rate is comparable to the global ocean. We also found there are subsurface cooling trend in the northeast Gulf of Mexico. Warming can be roughly explained by the balance between the low current advective heat flux and the annual net surface heat flux from echo in the Gulf of Mexico. Most of the results are presented here has been published in this paper, Journal of Climate. You can find more information there. Thank you. That's all my presentation. Is there any questions?
Just it's not the comment, but just the question. But it's shocking that the only QNet flux you can make, agree with your ocean heating is that from echo, and most of the atmospheric centric QNet is not agreeing with your ocean heat. Is that kind of, I think it's surprising.
Yeah. Yeah. We carefully examine the different products and based on the advective heat flux. So at least in the Gulf of Mexico, ECHO is the only one that can close the heat budget.
Thank you. I mean, it's more of a comment. I mean, San-Kun showed the distribution of the surface flux in the Gulf of Mexico. I mean, all the models showed the same distribution of cooling over the north and the east, and then when I say cooling, out of the ocean and into the ocean in the south, the difference was just the magnitude of that flux into the ocean in the south. So this is something very regional, and so maybe some of the models aren't as good at the very regional resolution of the heat flux.
Yeah, thank you, Tim. Yeah, this slide shows the annual cycle of the four products and the average value, which is shown by the orange line. So I think the other three products tend to average to zero annually, but Echo seems like has a negative annual average. But the magnitude of annual cycle is similar. It's just offset is different.
Zhenghui, that question for
Yes.
you.
I cannot hear you. If there's a question.
Can you hear me?
Yes, I can hear you now.
I found the button. Sorry. I was wondering whether you would want to comment on the role that loop current eddies may play in this problem in terms of feeding heat back to the atmosphere. And as you know, they are parameterized in ECHO. So I was wondering whether you wanted to comment on that.
Yeah. In our simple budget model, we didn't consider loop current eddy because that's a process of inside. So we only look at the boundary advective heat flux. But yeah, I think there are other studies shows that loop current eddy plays an important role to transfer the heat from the east to the west, because most of the loop current eddies disappears in the Western Gulf.
Okay.
Yeah, thank you. Any more questions? Yes, please, Donald.
Oh, a quick question, like on the lines of what Gail was asking, have you considered looking at a model, a free running model, a high resolution free running regional model of the Atlantic or some domain in the Atlantic and look at these processes?
Yeah, I think that this is a good suggestion to using models to quantify or determine the controlling factors of the warming. Yeah, model might give us more information about what really drives the warming in the Gulf of Mexico.
Yeah, if you're interested, we could chat offline more. There are a couple of efforts, configurations of MOM6 in the Atlantic at high resolution that are being set up at the moment, and they could be maybe helpful to look at that.
Oh yeah, thank you. Yeah, I'm sure. Yeah, I will reach to you offline, and we can discuss more about that.
Thank you. Great presentation.
Yeah, thank you.
Excellent. Thank you again. And so we're moving on to the next presenter.
So I will speak about some aspects of what you can do with reanalysis in the context of global and regional EEI. And my starting point is similar to that of Norman from yesterday. So the net DOA flux anomalies from series are in reasonable agreement with observation-based ocean heat content variations after about 2005. But what we can additionally bring in is other storage terms of the climate system based on reanalysis. So that's atmosphere, land, and sea ice storage terms. And you can obtain them from atmospheric, land, and ocean reanalysis. And what is maybe important to stress here is that I will rely mostly on ERA5 or ERA5 derived products. And ERA5 doesn't assimilate series data, and it doesn't see any data that is going into the observation-based ocean heat content product. So in that sense, ERA5 is really an additional extra data set that we can bring in. And for regional aspects of EEI, you need to look into lateral transports, and that's really an important application of reanalysis, since in the atmosphere there's no observations of transports, and there's only very few observations of transports in the ocean. So today I will cover two topics basically. So I will assess global energy budget closure with two approaches. One is a global inventory approach, and the other is a regional budget approach. And then I will basically, as an example of application, I will discuss some aspects of regional EEI in the Arctic. So I'm starting with global inventory methods to look at global EEI variations. And that figure is showing what Norman showed yesterday. It's global anomalies of net DOA radiation from series and the time derivative of ocean heat content from Lyman and Johnson's recently released ocean heat content data. And if you compute the correlation, as others have shown before, you get a correlation coefficient of 0.64. And what is interesting here is that the maximum correlation occurs at 3 months lag. So when the radiation is lagging heat content, basically. And this lag seems to be robust. So if you do it with an ocean reanalysis, you get a similar result. So now I'm bringing in storage terms for atmosphere, land, and sea ice, and that's shown in the second panel now. And what is interesting here, so it's plotted on the same scale as above. The variance of the heat content variations in sea ice and land is fairly small. But what is maybe surprising, the variance of the atmospheric energy variations is quite high, especially if you compare to atmospheric heat uptake, which is 1% or 2% compared to ocean heat uptake. But the variance here is, in the atmosphere is really sizable. And so what we can do now is add these, let's call it them secondary storage terms, atmosphere, land, and sea ice to the ocean heat content variations, and do again the correlations. And what you get is you get an increased correlation, so the correlation goes up to 0.7. And what is also interesting is it brings the DOA fluxes and the storage terms into phase. And you can actually see it from the time series of the atmospheric energy content variations in orange. So it's really out of phase with to the DOA fluxes. That's quite interesting. So it's related to ENSO events, and I think nobody has looked at this, and I think that would be an interesting study on its own. So what is the timing of atmospheric warming during ENSO and post ENSO and so on? So if you do this global inventory, it's apparent that if we bring in extra data for the secondary storage terms, we get better agreement on the global scale, which is quite nice, I think. And next, I will talk about the regional energy budget approach. And so what we do here, I've been talking about this in previous meetings, so I will keep it rather short. So the idea is that we infer the net surface energy flux into the ocean as a residual from the atmospheric energy budget. And we do this by combining observed TOA fluxes from series and the divergence of atmospheric energy transport and atmospheric energy variations based on ERA 5. And I have to stress that the divergence and the storage in the atmosphere is based on analysis. So these are fields that are strongly constrained by observations, and that's really different from fluxes that you can also get from ERA 5, but those are based on short-term forecasts and are less strongly constrained by observations. And it's not straightforward to compute those divergences, and the good news is that you can actually obtain them from the Copernicus Climate Data Store, so I put the DOI here. So moving to the results for the inferred net surface energy flux, on the left you see the climatology over 16 years. You get a reasonable spatial structure, and one metric to assess its quality is the global ocean average of this field, and it's 2 watts per square meter. And that suggests that the bias is fairly small because ocean heat uptake is order 1 watt per square meter, so we are only 1 watt off for the global ocean average. And this small bias indicates that there is a slightly too weak ocean-to-land energy transport in ERA 5, but well, it's quite good compared to earlier attempts using other reanalysis. On the right, you see with a different scale the net surface energy flux over land, and you see some noisy patterns that's related to numerical noise, which is stronger over land. And the net surface flux over land should be fairly small everywhere. And you see those patterns, and the spatial RMS value is approximately 14 watts per square meter. So that's probably an upper error bound of the grid point uncertainty of this inferred surface flux estimate. But I presume it's smaller over ocean because there you don't have the numerical noise issue. So doing a similar exercise as I did in the beginning, but now for global ocean averages. So I plotted here net TOA flux over the ocean and the inferred surface energy flux. And so the difference between the red and the orange curve is now coming from atmospheric storage and the ocean to land energy transports within the atmosphere. And you again see this phase shift between the red and orange curve. And on the right, you see the correlations. And again, if you only correlate TOA flux with ocean heat content variations, you get 0.6 at leg 3. And if you correlate the surface flux with the ocean heat content variations, you get a higher correlation at 0 months lag. So that's quite nice. So bringing in atmospheric observations to the budget improves correlation and also makes the phasing correct. We can also extend these inferred fluxes backward in time by combining them with reconstructed TOA fluxes that have been developed at the University of Reading. And you can see this here in the orange curve. So it's fairly stable net surface energy input to the ocean. So you see maybe some drift, but for comparison, I also put the vertical fluxes as output from ERA 5. And this is what I said before. That's really the parameterized fluxes from ERA 5. And they show a strong bias and a strong drift. And this is much, much smaller if you use this budget approach, which is shown in orange. Good. So since we've seen that the net surface energy flux is fairly stable in the 2000s and onwards, we tried to look into trends. So similarly as what Norman showed yesterday, and I reproduced it on the right. It's the net TOA flux trend over the past 2000 to 2020. And on the left, I did the same, but for the inferred net surface energy flux. So, and note there's a different scaling. So the magnitudes on the left are much bigger. And you see, obviously, some noise over land, but in general, the magnitude of trends over ocean is larger, which is, I think, a good sign. And there's, and in general, it's important to note that the left and right patterns are very different. So this tells us that the changes in atmospheric circulation are the main driver of the spatial structure of net surface flux trends. And well, one might argue which signals are true and which not, but we see increased ocean heat uptake in the Indian Ocean, and especially in almost the whole North Atlantic, north of the equator. Good. Next topic, regional EEI in the Arctic. How many minutes? Ah, very good. Great. So what I'm showing here is Arctic ocean warming 93 to 2019. And these maps are for upper 700 meters heat content and the heat content below 700 meters. And this result is based on an ensemble of 4 ocean reanalysis. And first, what you can see is quite rich spatial structure. There's very strong ocean warming in the Nordic seas and apparently little warming under sea ice. And if you average over all the ocean area north of 60 north, you get a long-term ocean warming of 0.8 watts per square meter. And if you add energy going into sea ice melt, you end up with about 1 watt per square meter north of 60 north. And interestingly, this is quite similar to global average ocean heat uptake. And one might ask how this can be reconciled with Arctic amplification, since surface temperatures are increasing much stronger compared to the global average. And just very quickly before I answer this question, since there's many observationalists here, so we also tried to validate the reanalysis with Argo data where we had some available. And this one example is shown on the right. This is for the Norwegian basin in the Nordic seas. So you can see the heat content evolution from the ocean reanalysis in blue. And in red, you see Argo ocean heat content. And you can see that the Argo data is noisier than the reanalysis, as we've seen in the previous talk. But in general, the long-term variations agree fairly well. So that adds confidence in the ocean reanalysis, also in this rather data sparse region. So for the question about Arctic amplification, if we stratify ocean warming according to surface conditions, so what I'm showing here is ocean warming in ice-covered, ice-free, and total ocean north of 60 north. And what you get is very little ocean warming under sea ice. It's only 0.2 watts per square meter, maybe. But in the ice-free Arctic Ocean, you get warming. If you look at the full depth ocean heat increase, up to 1.7, 1.8 watts per square meter. So this is where you really see Arctic amplification. But if you average over the whole Arctic, you basically, this is canceling. So because underneath sea ice, heat uptake is still fairly small. And if you do the numbers, 83% of the ocean heat uptake north of 60 north is happening in ice-free areas, which only make 37% of the total area. So it's really, there is a lot going on in the Nordic seas. And so another crucial application of ocean reanalysis is looking into transports. So what I'm showing here in the upper panel is ocean heat content evolution in the Arctic Mediterranean. So that's the Arctic Ocean bounded by Greenland, Scotland Ridge, Davis Strait and Bering Strait. And the red curve is full depth ocean heat content, and we can concentrate on this for now. So you see the long-term heat increase, and what you see as well is periods of rather low warming or no warming, then rapid warming, and then stagnation again. And it's quite interesting if you look at the lower panel, which is showing ocean heat transport into the Arctic Mediterranean. And this is based on ocean reanalysis. And we are lucky at these sections, we also have observations. And you can see time series of observations and reanalysis. And what you can see is that the period of enhanced heat uptake or heat content increase coincides with the period of enhanced ocean heat transport. And you can see this both in reanalysis and observations, which is quite nice, I think. And in general, you get good agreement between observational and reanalysis-based heat transport. But it's what is interesting is only one advantage of having reanalysis is that they are produced near real time. And only with reanalysis data, we could show that, in fact, the ocean heat transport decreased in recent years. And it took us a long time to get updated observations that confirmed this. So this shift backward to lower transports and this stagnation of heat content that seems to be consistent both in reanalysis and observations. And yeah, another plot I added just today since the discussion about the 2016 ocean heat content dip. And so if you look up here in the heat content, so you seem to have a very strong pulse of heat increase in 2016. And this coincides with, so what I put here is net surface energy flux over that region, over the Arctic Mediterranean. You also have a pulse of net surface energy input from the atmosphere. So that to me suggests that during that time there was a redistribution of heat from lower latitudes to the Arctic Ocean. It probably doesn't explain all the signal, but some of the heat ended up in the polar regions. So to summarize, so if we add reanalysis information for other components of the climate system than the ocean, we get better agreement between TOA fluxes and variations in heat content in the climate system. And the other point I tried to make is that if we combine TOA fluxes from series with divergence and storage from era 5, we get fairly stable estimates of net surface energy flux, especially after 2000. And this provides really critical information for regional EEI assessment, I believe. Then for the Arctic, we find a similar regional EEI compared to the global EEI, and this is because sea ice covered regions still exist and they have fairly small heat uptake. And what I hope was also able to show is that Arctic heat uptake is governed by changes in ocean heat transport. And ocean reanalysis are in quite good agreement with observation-based transports. And that would suggest that we can use ocean reanalysis also in regions where we don't have observed sections. So that's a nice property of those products. Thank you very much.
So we have plenty of time for questions, I think. Who wants to get us started?
Very, very interesting talk. Thanks. So two questions. You show the heat in 2016 or in an ENSO period, at least temporarily, increasing in the atmosphere, but well, quite a bit, like 0.4 watts, right?
Yeah, it's a huge signal. Yeah.
So at least in those instances, at least on a monthly time scale, at least during ENSO, the Earth's energy balance, it's not 90% ocean, right? It's much more towards, I mean, we assuming constant, pretty much 90% goes into the ocean, but at least in some periods, that percentage is not even close. At that point, it would be about half.
Yeah. So yeah, exactly. That's the point I wanted to make. So if you go to shorter time scales, the decomposition of heat uptake or variation between ocean and atmosphere is very different compared to longer time scales, I think. Yeah.
Yeah. But at the longer time scale, at the year time scale, that then, well, either leaves the Earth system or goes back into the ocean.
Yeah. But well, what is impressive is that this is a smooth time series. So I applied a 12-month smoother. So these anomalies persist over long time scale. So it's not monthly time scale. So it's quite big and sustained signals. Although I have to say I didn't check the decomposition into sensible and latent heat. So I assume there's a lot coming from latent heat in the atmosphere.
And one other somewhat related, in the Arctic, you calculate 0.8 watts per meter squared, and then 0.2 watts per meter squared for cryosphere, and that's scaled over the entire Earth. So
that's the average over the ocean area north of 60 north.
Oh, just over the ocean area, not.
Yeah.
Okay.
Yeah. So it's if you would scale it to match or to make it comparable to the full surface, it's very, so basically this area is 4% of the global area, and the heat uptake is about 4% of the total EI. So yeah.
Thank you.
Thank you. I have a quick question in terms of, I mean, you use ocean reanalysis and atmospheric reanalysis, but one is used for forcing the other. So how independent are those estimates, and or how much they might have been affected by any constraints to bring the model in any balance?
Yeah, that's a good question. So I would say of the 3 time series I'm showing here on the left, on the bottom left, the orange one is truly independent. So if you start from that, it's ERA 5. But then the land heat content it's basically a land model driven by ERA 5. And also the ocean reanalysis is driven by ERA 5. So the 3 curves on the left, bottom left, are not independent of each other, but they are independent of the top left curves. So I hope that makes sense. So it's all based on ERA 5, but these terms are independent of series, and they are independent of the in situ based ocean heat content that you see up there. Well, it would be interesting to have a more observation-based estimate of land heat content variations. Maybe ERA 5 land, which I used here, is underestimating variability, and in reality, the variance of that curve would be higher. I don't know.
I was astonished by your curve where the global ocean heat content is ahead of by 6 months of the top of the atmosphere flux. And so what does it mean according to you? Is that like the coupled ocean atmosphere system is changing winds and revealing some, and so it makes the ocean give some heat or suck some heat from the atmosphere, and then it goes through the atmosphere and we find the solution, and we have as a consequence the top of the atmosphere. That's the way it should be read.
Yeah, that's why I said it would be a study on its own right. So So the TOA fluxes are lagging the heat content variations, and one interpretation might be that you have a warm SST anomaly releasing extra moisture from the ocean, and that's an extra heat flux into the atmosphere, and then this changes circulation and clouds, and that takes some time, and it's only when the clouds have changed that really you see a global signal in the TOA flux. That might be one suggestion, but Norman might have another one.
Well, before we get too creative with our explanations, I think we should compare notes on how you did the comparison, because I don't get that lag, or not nowhere near as pronounced as what you're showing here with Greg Johnson and Lyman's previous analysis, not this particular 2023 paper, but the stuff that we published doesn't have this lag. And so you have to be careful on how you compare those, how you calculate the mean from series versus the tendency in ocean heat content. And that could, when I first did this, I got totally confused, and one of my co-authors pointed out that I had that sort of shift, and one of my co-authors corrected me, and everything fell into place when I did it right. So maybe we should compare.
Yeah, so I think an advantage of this newer product that they released is that it's at fairly high temporal resolution. It's 7 daily averages, and from those you can basically build really clean tendencies. So it's different to what they had before. So what made me really confident about this lag was that if I do the same using ocean reanalysis, where you really have simply the monthly averages, and you can do straightforward center differences, and you can be sure about the phasing, you get the same result. So that made me confident that that's real, kind of. It's in the data at least. I think with the data Greg and John released earlier at like yearly at half-year resolution, I think I'm not sure whether you can see that at all.
Okay, well, we should talk offline.
Yeah.
Just a very quick comment. I think what you did, the series, let's say, born to the surface through the ERA 5 lateral transport could be very useful for many applications, like even validating in ocean model, heat fluxes, things like that. So I don't know if they are available, but I think it's very nice data set to look at more carefully. So.
Yeah, I agree. Yeah, the data are available, and I think it could even built in as a constraint in data assimilation, similar to what you did with series, as a like a 1D constraint. But the advantage of having the net surface flux, it's really maps. So you have spatial structure that you can imply.
Exactly. Yeah, you don't need to apply any to consider any representation error for the ocean heat uptake, but use directly that. Exactly.
That I'm wondering.
Maybe that's a question to Andrea. So in fact, what you get is the flux at the top of the ocean and on top of sea ice. So where you have sea ice, it's top of the sea ice. So it's basically flux out of the lower boundary of the atmosphere.
Thank you.
Just a quick question. So the observations that you use for transport, is that OSNAP or what did you use?
For the ocean transports, it's basically moorings that they have in Greenland, Scotland Ridge. So it's slightly north of OSNAP, so it's slightly north of the eastern OSNAP part. And it has been sustained since 1993, which is quite nice. So I think it's not as densely observed as, for example, Fram Strait, but they believe it's reasonable transport estimates that you get from it.
Thank you.
All right. Shall we?
Escape. Stop. All right. Stop. Next presentation is by me, Seiji Kato. And this talk about the approach of gathering the all the energy fluxes, surface fluxes, and overloaded.
Yeah, it's happening.
So this is forward.
Laser pointer.
This is a laser pointer, and then forward. Here. Okay. So this is the approach that initially when Benoit wrote the white paper a while ago, and we had an approach to infer the EEI from just from the summing up the surface fluxes. But turned out that that approach, the uncertainty or bias error is too large, and we didn't even bother to put the uncertainty in that because of the order of magnitude. Uncertainty is order of magnitude larger, and unfortunately, since then we haven't made much progress to reduce that uncertainty. One of the reasons is this approach involves the different communities and the radiation and turbulent flux, and that doesn't get the uncertainty. It's estimating own product is hard enough, and uncertainty is gathering the multiple product, like Tristan explained yesterday, is very hard, and even harder to get the uncertainty and bias in the regional and scale and the temporal varying regional scale. So this to me is that this approach is to the role of this approach. This approach is resolve all energy fluxes, and we're seeing that the Earth energy imbalance, that the TOA net flux is changing with time, especially very rapidly in the last decade or so. And this approach is since given every fluxes, and the role of this approach is to understand what else is changing associated with the EEI change, instead of deriving the EEI from this approach. And so just to show, just to show to show the current status of this bias I'm talking about. I use the series product, top of that surface irradiances, and the turbulent fluxes from sea flux over ocean and ERA5 over land, and the precipitation and GPCP. And for this case, and dry static energy and the kinetic energy transport from MERA2. And if we do that, the current status of this approach is about regional residual, energy balance residual of this atmosphere. We do that energy balance in the atmosphere so that we don't have to consider the ocean heat transport in the ocean. So if you do that energy balance in the atmosphere, the regional residual is, that's 10 and 30 or 40 watts per square meter. And it's that this the color scale, ugliness of color scale is represents the ugliness of this work. And one of the problem of this, like I said, is lots of flux involved, and its own component has its own uncertainties and time varying uncertainties. And an even harder part is that pointed out Michael Mayer in 2017 and discussed by Peter Loritzen yesterday, that this flux, the last two terms, the flux associated with the water mass transport. So the precipitation falls to the ocean, and that precipitation, the temperature, and the precipitation carry the enthalpy, and in the both way, and coming down, and the water vapor carry the enthalpy too. That has to go into the surface energy balance equation. So this is the hard. But so this role is to, I think, understand what is happening associated with the increasing EEI. So we start looking at that approach, and so understand the surface energy associated with EI. So before we try to do what's happening in the radiation, we have to clean some of the artifacts in the previous series surface data set, and it's called EBAF. So we essentially cleaned a lot of artifacts, and essentially changing the reanalysis from older reanalysis to MERA2 to better water vapor temperature, and we clean the clouds to compute the surface flux. We now use the only MODIS and VIIRS, and we don't use the geostationary satellites, and so on and so forth. That's own decision has a science to it, because we are essentially saying that we don't need to observe the diurnal cycle of the clouds, but that's another topic for another time. And if you clean that, and if you look at the trend of surface radiation, so that what I plot here is a trend over 2000, March 2000 to December 2022. It's a net surface trend. This is a net shortwave trend, and this is a net long wave. This is a total, the sum of those two. So what we are hearing from yesterday is that the cloud change happening over, especially Eastern Pacific, that increase the shortwave radiation over ocean. There is a clear contrast between Northern Hemisphere and Southern Hemisphere. Or more interesting is that there's a clear contrast over ocean for short wave and over land and long wave. And long wave, the over land, it appeared to be cooling in this plot, but that is due to the more upward long wave radiation over land. And if we plot that global time series of this is downward long wave radiation and upward long wave radiation, and for averaged over entire over land and ocean for the global and the anomaly time series going from 2000 and 2023 to end of the 22. And downward is about increasing gradually, and ocean and land at about the same rate. And upward radiation, which is primarily the function of the surface temperature, gradually increasing both at the land and ocean about the same rate. And about 2019, and land is increasing faster than the ocean. This might tell us that the land is warming faster than ocean in the last 4 or 5 years. But do we believe this? And that's I don't know. I don't know whether I believe this or not. So Gail said that this morning that the physical constraint to evaluate this, whether this is true or not. But this is a very subtle change and very difficult to say that whether this is a real or artifact in our data set. And then what we have to do is to go into the regional and unscramble and all artifact and look at that kind of quality control and whether this is real or not. Or not. If this is real, this is an interesting result. But before we go exciting about this, but we have to make sure this is right. And so far, we evaluated the uncertainty of the mean, absolute mean, the monthly mean, and global mean so far. The uncertainty of this time series. What's the uncertainty of time series is even harder. Attaching uncertainty to this time series is very difficult. And but for now, I don't have the answer to that. And so that I started with the we haven't much progress made to closing the surface energy budget, but I have a proposal to close the budget. And so in the workshop we had at ISSI, we discussed about that extending the constraint from TOA to surface and so forth, and to extend the constraint to other data product. So yesterday we explained that the series using ocean heat and content constrain the TOA net, and we use in the series project itself that use the TOA shortwave long waves to constrain the surface radiation. So we do that in a series project, and then Michael Mayer just explained to that and use the moisture static energy and the kinetic energy transport in the atmosphere, and he is inferring surface net flux. And then if we can use the same temperature field and the wind field, instead of using the moisture static energy, we can use a dry static energy. And we have to add the surface sensible heat, and we can infer the diabatic heating of precipitation. And if we do that, think it's try to move. Can we do this? Okay. So if we do that, so what we do is that moving in the energy balance equation, moving any dry term on the one side, any wet term on the other side, and using the wet the diabatic heating from the dry. So inferring the precipitation without measuring any raindrop at all. And so this is what we get, and this is energy balanced. And but this is more like a toothpaste approach, and all bias error is built into this. But the good part of this is that I said that all energy bias error is scattered around all products initially, and now we have a way to gather all bias error in one product, and that our role is now to evaluate that the diabatic heating field is physically reasonable. And if we this is done by the MERA 2, but we can do it. This is the ERA5. So we took Michael's dry static energy field, and the rest of the product is the same, the series and ERA5 sensible heat and C flux. And this is noise is gone, and precipitation fields to me is very reasonable. And again, that this depends on the product we gather, but that's the same for any product, right? The error is depending on the products, and even though we can make it the different, I wouldn't call it ensemble, but we can make it the different sets of this diabatic heating and evaluate the spread. So it's now that the variation is in our hand, and so this is kind of exciting product, and we can even have a monthly and grid diabatic heating by precipitation. And next. So one thing that this product can do is there is a big question is that the missing the absolute energy to close the surface energy budget whether that affect the anomaly time series trend of a precipitation or anything else that's going into that to balance the budget. So now we can plot this. So the blue line, this is the red line is the energy balanced diabatic heating by using a MERA 2, and the orange line is the energy balanced diabatic heating with using the ERA5, and the blue line is a precipitation from GPCP. And the global anomaly time series agree relatively well. And even we can do it regionally. And at top is the time series from the Northern Hemisphere, and bottom is from Southern Hemisphere. So with that, we can do that. So it's not replacing the precipitation data set. We can testing the whether missing the energy affect the anomaly time series. And this is not perfect, the energy balanced product, but at least we can test our the concern, evaluated our concern that the missing energy affect the time series, anomaly time series. So I believe that a lot more we can do with this data set, and this will now this data set is developed under the news product that Tristan explained yesterday. So summary and conclusions. Regional atmospheric energy balance residual computed with the observational based data product remains to be large. So instead of this approach is not getting deriving EEI, but to learn what is changing with changing the EEI. Understand how? Yeah. So and revision of series EBAC product going from edition 4.1 to 4.2 significantly reduce the energy uncertainty in the regional surface irradiance trends. And to extend the constraint, a monthly product of diabatic heating due to the precipitations proposed, and the future work is to analyze this data set to whether this is physically plausible. Thank you. I take a question.
So I think we have a couple more minutes for questions. Anybody? Tim?
Just a question about, so diabatic heating due to precipitation is going to be dependent on how good your precipitation data is, right?
No, there's no precipitation data is going into that. There's everything is inferred from dry. So the radiation, the sensible heat, and the dry static energy transport.
Oh, I missed that. Sorry.
Inferring it wet from the dry.
Okay. Thanks.
So can you use it to correct GPCP, which have
well, that's not the purpose of that, but
or even over the ocean.
But
yeah, because you've got this global mean, and we know that there are issues in GPCP.
Right. Well, we can. Yeah, that's comparison. Is may point out the issue in GPCP maybe, or issue in, or find out where the energy is missing or something like that.
Thanks a lot for this nice talk. I'm curious about this result for the recent years on the difference on the heating and on land and the ocean. So what is your explanation, like steps you want to look at, and what could be the role of resurfacing of heat from the deeper ocean layers, which had been discussed under the post-hiatus redistribution, planetary redistribution of heat?
So why that ocean is heating? That's so. Well, the Norman explained that some of the not all, some of the heating is caused by the ocean or the sea surface increasing sea surface temperature that is affecting the clouds and reducing the cloud fraction. At least that's happening in the Eastern Pacific, and the Southern Ocean might be a different. And so it's not everywhere. It's not one. I don't think it's, I can explain in one sentence, but at least the clouds are one reason.
I think you're asking about the skin temperature, the upward flux where it just shot up at the end. That was land. That was over land.
Oh, land.
Yeah,
land faster.
I kind of wonder though.
That could be the issue in the reanalysis, but that could be real. I don't have an explanation right now.
Yeah, so the skin temperature is the one over skin temperature over land is what I would look at first to see if
that skin temperature of land and the mix of derived from MODIS and the reanalysis.
And reanalysis. So the MERA 2 and
well, MERA 2.
You could look, I guess, at compare MODIS and MERA 2 and see if they diverge.
Yeah, so that's what we do. We have to compare with the various different products to understand that the difference, and it's not so much physical constraint of you said that 300 watts difference in this month and that month. We don't see that large difference. These subtle differences have to be going through the comparison and understand it whether this is real or not.
Absolutely. Do we have time? Not sure. I think we are a bit out of time. Unless somebody else has a question right now.
Good? Okay,
All
so
right,
let's
so
go on. Thank you so
I'm
much.
done. I'm done.
Right, so the next speaker is Johannes Meyer.
Ah. Is there a presentation? Sorry, I don't get it. How can I make it full screen? Control.
This is the laser pointer. Yeah.
How do we get back and forth?
Oh,
Slides.
sorry.
First,
Yeah.
okay.
Yeah.
Okay. Okay. Thank you for having me. It's a pleasure for me to be here. I'm going to show you some results of the paper that we have recently published in the ESD journal. And if you're interested, the title of this presentation is actually the same as the title of this paper. So the motivation behind this study was to better understand long-term changes of air-sea heat fluxes over the North Atlantic Ocean as derived from the ERA5 reanalysis. And in particular, we wanted to understand the driving forces of the trends, the impact of the North Atlantic oscillation and also of the Atlantic multidecadal oscillation. And we wanted to find a link between the flux trends and AMOC weakening. So why using ERA5? Simply because it provides globally gridded data for more than 8 decades, whereas, for instance, observation-based estimates, so like from buoys, these flux estimates are quite sparse and also very limited in time. The problem with these ERA5 fluxes, however, is that they suffer from spurious trends, as shown here, and we already saw this plot in Michael Meyer's presentation, so at least the second half. So you see these spurious trends in the 90s, and these generally large spires, what difference to the ocean heating rate shown here in black. So this is actually the ocean heat content density derived from this IRP dataset. And so to get rid of this discrepancy, we actually apply an adjustment based on the difference between these two lines. So to say, at least to get rid of these discrepancies in the fluxes over the North Atlantic Ocean. So what we actually do is we really subtract the differences in the global ocean means from each grid point in the North Atlantic Ocean. And then we have to explore the reliability of these trends by comparing them with the inferred surface fluxes. And Michael already introduced these fluxes. So here's again shown the atmospheric energy budget. So we take the the radiative fluxes at the top of the atmosphere from this deep sea product as developed by the University of Reading. So it's available from 1985 onwards, and we subtract the energy transports and the storage that we have computed with Aero 5 analyzed fields to obtain these indirect fluxes. And as you can see, and we'll repeat it again, they perform much better than the model-based fluxes in terms of the temporal stability, and also in terms of the global ocean mean. So we have an ocean mean of about 1.6 watts per square meter, and therefore this is, in our opinion, a quite good reference. So the outcome of this adjustment is shown here. So we have, on the left, we have the DGF trends for 1985 to 2019 of these model-based fluxes where we have applied this adjustment. And on the right, we have the trend of the inferred surface fluxes. And as you can see from this generally good agreement in terms of spatial pattern, but also in terms of the basin-wide mean trend, this suggests that the trends in these globally adjusted model-based fluxes are reliable. And I should emphasize this again at this point. Although these model-based fluxes perform, the performance is quite terrible on global ocean scales, they are still useful on regional scales, on smaller scales in general. And as you can see, the trends agree quite well with other products. And just to understand the design of these trends, the fluxes in winter are in general from the ocean to the atmosphere. And according to our definition, these are negative fluxes, which means that if we have negative trends, as shown here in blue, these fluxes increase over time. And this is the case, for instance, along the Gulf Stream, and also in regions of strong sea ice retreat, like for instance in the Labrador Sea and also in the Nordic seas. So in the next step, we wanted to explore the driving forces of these trends, and for that we focus on turbulent heat fluxes only, because the trends in the radiative surface fluxes are usually an order of magnitude smaller. And according to this commonly used bulk formula, which has also been used in Aero 5 to compute the surface fluxes, the trends in the latent heat fluxes, as shown here, can be attributed to changes in the wind speed, shown in the middle panel, and changes in the moisture difference. So the difference between the model level, and this is usually at 10-meter height in Aero 5, and surface saturation humidity, which is derived from the skin temperature. Just remember this number. So this is the pattern correlation between the difference trend, the moisture difference trend, and the flux trend. It's 0.8. We can do that the same with sensible heat fluxes, but they depend on the temperature difference and not on the moisture difference. And here we have a pattern correlation 0.9. So what we can see from these plots is that, first of all, the trends in the moisture and temperature difference are more important for the spatial pattern of the flux trend than changes in the wind speed. As you can see, we have a quite large pattern correlation. And the second point is that the trends in the net surface heat fluxes at low latitudes are dominated by changes in the latent heat flux, as shown before, and at high latitudes by changes in the sensible heat fluxes. And this is also true for trends before 1985, but they are usually weaker and more positive, which is related to the ocean cooling during that time. So shown here again are the trends in the moisture difference, which are largely negative, and the trends in the temperature difference, which are widely positive. So this means that the latent heat fluxes increase over time and the sensible heat fluxes decrease. And here I want to highlight a few features of this trend. So probably the most dominant feature are these negative trends in the temperature difference in the moisture difference at low latitudes, and this can be attributed to an intensification of the Hartley cell, and therefore an subsidence of drier air masses, which basically reduces the moisture in the model level, and that's why we see these negative trends. And similar to that, so also consistent with trends in the circulation are these trends in the Norwegian Sea. So here we see a trend towards more southerly winds that attract warmer air masses, and therefore you have very strong trends at the model level, whereas at the surface, yeah, they're weaker. Along the Gulf Stream, it's actually the other way around. Here we see strong surface trends because the Gulf Stream is getting warmer, whereas the trends at the model level, so the trends at the model level are quite small and much smoother than what you can see here. And the last and probably the most interesting feature are these compensating trends along the prevailing wind direction in the Labrador Sea and to some degree also in the Irminger Sea. And one explanation of that could be that the sensible heat fluxes that emerge in this region of strong sea ice retreat warms the attracted air masses and then as further consequence damp the sensible heat fluxes downwind, so that you have like an increase of sensible heat fluxes in the north and then decrease of sensible heat fluxes sort of further south. And now we wanted to understand, or we wanted to find out if this trend in the net surface heat fluxes, and this is the 70-year TGF trend, can be explained by changes in the NAO or the EMO forcing. And for that, we have regressed our fluxes on the NAO index and multiplied the trend in the index. And this is then subtracted from it, and we call this impartial trend. And the result is shown here. And in a further step, we also subtracted the MAO, so that the EMO signal. And yeah, I mean, you see the differences are quite small. So this means that the EMO forcing is quite small. But what you can see from these plots is that the trends, first of all, cannot be explained by changes in the NAO or EMO forcing. And more interestingly is the fact that these more frequent positive NAO phases that occurred during the last 30 to 40 years favor ocean cooling in the Labrador Sea and also in the Irminger Sea. And you can see this statistically insignificant positive trends, which means that the ocean cooling is reduced. And if you subtract the NAO forcing, this reduction is even stronger. So which means that if you consider this, the NAO forcing, this favors ocean cooling in that region. And in the last step, we wanted to find a link between the surface flux trends in the North Atlantic Ocean. A link from that to the AMOC weakening. And for that, we use the ocean heat budget, which tells us that the ocean heat transport at a certain latitude phi can be estimated from ocean heat transport further north. And in that case, we use transport estimates through the Arctic gateways provided by Tsubuchi et al. So this includes transport through the Davis Strait, the Fram Strait, and the Barents Sea opening. So then you have basically a closed volume for which you can compute the budget. And from this, we subtract the difference between our globally adjusted model-based fluxes and the ocean heating rate, again provided by the ARP or derived from the IRP dataset, integrated over that area between the Arctic gateways and the desired latitude. And the result is shown here for two different trend estimates. So the blue one is based on 5-year means, and the black one is based on monthly means. And you can see that there is a clear negative trend at all latitudes, which suggests that the weakening of these surface fluxes in the North Atlantic Ocean is associated with a weakening of the AMOC. And we also removed the ocean heating rate from this equation. And what you can see is that the trends are quite similar. Actually, they are more negative, which means that the ocean is getting warmer or as warmed, whereas the northward transport of heat declined over that 70-year period. And yeah, that's a summary, and that's from my side. Thank you.
A question: how do you get the AMOC weakening in last 70 years? The AMOC, you said the AMOC is awakening in the last 70 years from 1950 to 2019. What kind of data have you used to have this conclusion?
It's basically the ocean heating rate from Li-Xing Cheng. The model-based fluxes from ERA5. So these are based on forecasts. And for the Arctic gateway, we haven't said that, but this is actually the climatology from these transport estimates, because they are available for 2005 to 2013, I guess, or 16 or so. So we just take the climatology of this transports, which is a valid assumption, because it is assumed that the ocean heat, that the trends in the ocean heat transport at that latitude is quite small, and also the models show that. And that's it, yeah.
So basically, if I understand, you have used the heat transport to represent the strength of the MOC in these 3 streets.
Yes.
Okay, thank you.
I mean, we also removed it, so, and we still see this decrease. But the important point is, and that's why I've showed this adjustment, you really need to adjust these model-based fluxes to get something like this.
Because my how to say feeling is that it's a little bit too big words to say AMOC is weakening based on the the transport in the Davis and the Fram Strait. It's a little bit very far from it's very north, I would say, the heat transport over there to represent the AMOC strength. Just personal feeling.
Mm-hmm.
Other components to the ocean heat transport than the AMOC, right? They can be horizontal recirculations, and maybe that's what you're pointing to. That tying up the heat transport directly to the AMOC may be a bit too quick. Does that make sense?
Yeah, I mean, as I understood, there is like a linear relation to the ocean heat transport and the AMOC weakening. So like really the decrease of the volume transport. And if you assume that, then I mean, then this agrees quite well with the AMOC weakening, right? And even if you look at the numbers, if you take like the weakening at 2060 degrees north, where we have this rapid array, right? Yeah. We have a weakening of 0.2 petawatts per decade, so 20 terawatts. So over 7 decades, this is a decrease of 140 terawatts, and this is relative to the observed heat transport from rapid. This is about 14 or 13%. Like the transport is 1.2 petawatts at 26 degrees north. I mean, yeah, it could be by chance, yeah, but it agrees quite well.
Yeah, no, that's fair enough.
Hello. Is the weakening of the AMOC expected and consistent with the polar amplification, so temperature at the poles rising faster than at the equator?
That's a good point. I mean, I guess so. I mean, the first point is that you have not only in the ocean and heat transport, but most of them happens in the or takes place in the atmosphere. So, yeah, I guess. Yeah.
All right. Thank you again. Anything else?
Jim, are you there?
Yeah.
Oh, okay. Well, how do I do? Just stop sharing, maybe? Yes? Oh, all right, okay. Okay, could you share the screen, Jim? Yeah. Okay.
Look
all
okay?
right. Yeah, looks good. I can
Okay.
hear you too.
Great. So I'll try and be quick. I know you guys are probably hungry. So this is a study which is an early report on a collaboration between myself, Gail Forget, Andrea Storto, and Hao Zhu. And motivation for this really comes from a paper that Matt Palmer published in 2017, which compared a lot of ocean reanalyses that were available at the time. And one of the results was that if you looked at the deeper ocean, there wasn't a whole lot of agreement among these different ocean reanalyses, and that was a little bit discouraging. And so this is an attempt to take a look at some more recent generations of reanalyses and take a look at a more recent time period and see if we can see better agreement among these reanalyses to convince the EEI audience that these really can be useful for you. So I'm going to show you results from just 4 reanalysis state estimates. The first we've heard a couple of talks on earlier. It's the ECHO 4. This is the latest generation. And as pointed out before, this has the wonderful advantage that it maintains consistency with the equations of motion as expressed on the numerical grid. And it simulates most available data, and it you could think of the bias correction in this model as it modifies the surface forcing and initial conditions and some mixing parameters. The other three analyses I'll take a look at are all sequential analyses. So they follow the kind of methodology in the lower right there, where you have a model forecast and you have some update cycle, and then the analysis is used to create another model forecast and so forth. And so all three of these are sequential analyses of that type. It's SOTA, the Andrea's ensemble reanalysis, and ORS5. And of course, just to remind you, Andre's reanalysis actually has this very large ensemble set, which can be used to define uncertainties. So just to get you starting to think about these, I wanted to show you what net surface flux looks like for ECHO 4. This is averaged between 60 south and 60 north. And the period of interest, the longest period we'll be interested in is 1992 through 2019. And you can see that in the warm latitudes, this warm latitude band, ECHO 4 has quite a consistent net downwelling surface flux of about 3 watts per meter squared, and it doesn't change so much throughout the record. Whereas if you take a look at the sequential analyses, in fact, the net surface flux may change quite a bit. In fact, we were just hearing about ERA 5 having long-term changes in the global net surface flux being somewhat high in the 80s and 90s, and then getting lower, and then maybe rising up again. And so I've got ERA 5 in black here, and MERA 2 turns out in this latitude band to be a little bit lower, so MERA 2 is in green. And we've used one of these ocean reanalyses, in this case SOTA, to modify the net surface fluxes to be consistent with the ocean temperature record. And so this is the result of a couple of separate ocean reanalysis experiments, one driven by ERA 5 and one driven by MERA 2. And when you do that correction, in fact, you can get those net surface, the implied net surface fluxes to come into agreement. So that's encouraging. So let me just show you what the results look like from these 4 reanalyses. In each case, I'll show you the average temperature as a function of time, either on the left-hand side for the layer from the surface down to 1,000 meters, or on the right-hand side from the surface down to 2,000 meters. The upper row is ECHO 4. Second row is SOTA 3, third row is the ensemble reanalysis, and at the bottom is ORS5. And as you go from the top down to the bottom, if you can read those numbers, you'll see that the slope of that line is getting steeper and steeper as you go from the top to the bottom, indicating that the rate of heat uptake is lowest for ECHO 4. Actually, that was mentioned earlier, and it's highest in the set for ORS5. Let's see. So let me now show you what the spatial patterns of this heat uptake look like. I also wanted to point out, it was mentioned earlier, this whole issue of the XBT bias problem, and possibly one of the reasons why the analyses sort out this way is I know that ECHO 4 and SOTA are both using the Levitus XBT correction, which tends to give you somewhat warmer temperatures in the 1990s because of the number of XBTs. So anyhow, so this is what the spatial pattern looks like of heat uptake for 0 to 1,000 meters on the left, 0 to 2,000 meters on the right. And this top row again is for Echo 4. You can see that the patterns are pretty similar between 0 to 1,000 and 0 to 2,000. You get this warming in the eastern tropical Pacific and western subtropical Atlantic, and cooling in the subpolar gyre, and cooling in the western Pacific. And so now we want to compare those to the other three analyses. And I think if you look down the page there, if you take a look at those same features that I pointed out in the upper row, you'll see them in the other analyses as well. So that kind of checks our first box. In other words, you can certainly qualitatively see the same patterns in each of these reanalyses. So that's very encouraging. And the next thing I'd like to do is point out a couple of the small year-to-year anomalies. Oh, by the way, I've annually averaged everything, so just to make my life easier. And so if you take a look between year 2000 and 2005, of course, we have this dramatic increase in heat uptake in the ocean in at least a couple of the reanalyses. It's very evident. You can see in this red dashed circle in SOTA 3. It's very evident in the ensemble reanalysis here as well. By the way, in the ensemble reanalysis, the gray bars indicate one standard deviation of this ensemble set of reanalyses. And it's even evident in ORAS-5, although not quite so evident in ORAS-5. By the way, if you look at 2016, you can see a little bit of a change in the average temperature. This again is 0 to 2,000 meter average temperature, but it's not very prominent. And that's also consistent with a couple of the earlier comments. And so to try and figure out what was going on between 2000 and 2005, I show you on the right the same picture I showed you before, which is the heating rate between 2005 and 2019. That's what I showed you before. And on the left, I've added the heating rate over a somewhat extended period starting in 2000 to 2019. And in fact, you can see that the heating rate, a lot of these basin regional anomalies disappear when you look at this longer period. That dramatic heat uptake in the eastern tropical Pacific, the western subtropical Atlantic, even the cool anomaly in the western tropical Pacific are all somewhat weaker. And that's true consistently for all of the analyses that we're looking at here. So there you go. And so now I'd like to take these analyses and try and come up with basin average estimates of net surface heat flux. There are only 4 reanalyses going into these estimates. The values themselves are just the median that I get from these 4 analyses, and the uncertainties here are simply the standard deviation of the estimates from the 4 analyses. And this is all for the period 2005 to 2019, in other words, the Argo period. And I just wanted to spend a little bit of time talking about the different ocean basins. So you can see, oh, and the upper number is the number for between 0 and 1,000 meters. The lower number is between 0 and 2,000 meters. And so you can see in the Atlantic, there's quite good agreement. In other words, the uncertainty is small in the upper 1,000 meters. It's a bit larger in the upper 2,000 meters. But the number's large. The Indian Ocean has larger uncertainty in both the upper layer and the lower layer, and also is quite high heat uptake. The agreement in the Pacific is quite good already, and the agreement in the Southern Ocean is not so good in the below 1,000 meters. There seems to be some disagreement. And if you look at the individual analyses, it turns out that the 3 sequential analyses are in pretty consistent agreement. It's not to say they're right, but they're in pretty consistent agreement for the Atlantic. So ECHO4 is a little bit different there. In the Indian Ocean, it's the ensemble reanalysis and ORS5 that have the highest heating rate. In the Southern Ocean, it's ECHO4 and ORS5 that have the higher heating rate. And I wanted to take just a moment to look in a little bit more detail at this heat uptake in the Indian Ocean. So the just the rest of the slides I'll show you are just for the Indian Ocean. So let's average horizontally over the surface of the Indian Ocean from the surface down to 2,000 meters. So get the average temperature anomaly as a function of depth and plot it as a function of time. And I'll show you that plot in the upper panel for one of the analyses which have a somewhat lower heat uptake. I picked soda. And in the lower panel, one of the analyses which has a higher heat uptake, which is ORS5. And it's also kind of encouraging, at least to me, if you look as a function of time along the horizontal axis, the anomalies look pretty similar. You see this warming in the surface layer. And the big difference between the upper panel and the lower panel really has to do with a relatively weak but a vertically extensive warming, which occurs between about 500 meters depth and 1,500 meters depth in ORS5. And I think that warming is responsible for the greater heat uptake in ORS5. And we can kind of track down the origin of that heat uptake by looking horizontally at where the temperature anomalies are distributed in that 500 meter to 1,500 meter layer. Oh, by the way, that's what EN4 looks like for the same section. So this is what the spatial pattern is of the heat uptake in that layer, 500 meters to 1,500 meters, where ORS5 is getting somewhat more heat than for example, SOTA 3 and ECHO4. And it's interesting to look at the patterns of heat uptake geographically as well. And for observational oceanographers, they'll probably take a look at this picture and recognize that that whole layer extending from about 50 south to about 30 or even 25 south, that's all Antarctic intermediate water. It's Antarctic intermediate water. So you're really seeing the warming of Antarctic intermediate water, and it just turns out that ORS5 is warming that water just a little bit more than, for example, SOTA 3. And you see the same patterns, though. And then there's also a little bit of warming north of something like 10 south. So again, the patterns are very similar, but of course, when you average over the whole basin, the positives and negatives cancel and you get these slight differences. So that's pretty much my story. I began by having concerns, having read Palmer et al. 2017, that these different reanalyses were just too different to be useful for EEI calculations. And I come away already with considerable encouragement. In fact, I believe that these reanalyses are sufficiently similar that we can really start to diagnose exactly where the heat is going in and use them to try and track down this, where there's agreement and why there are sources of error. And so that's pretty much my story. Thanks.
Great. Thank you for staying on time also. And my apologies for the delay. It's my fault. Do you have questions? Okay. I think
they're hungry. I'm really sorry I'm not there to be with you guys. It's been wonderful listening to all of this.
Excellent. Well, thank you for presenting remotely. Have a good night. You have one more?
We just told the earlier poster session that there's 2 more presentations at posters. Is that what, 3 minutes each? Is that what it is? So I start from the top. So Mikos, are you there?
Yes, I am here.
So that you have a 3 minutes presentation about your poster, and then we go Sean, and 3 minutes. And can you share your poster, Nicholas?
I start, all right.
3 minutes.
Right, okay. Can you see that? Thank you. So, Saluti Frascati, Budapest speaking. Here is my availability and email. So, Benoit mentioned in a recent presentation that Arrhenius was one of the founding father of climate science. Now, Schwarzschild is certainly another. So I got in mind an idea that what if I would control his very simple, very original radiative transfer equations on annual global mean data, on fluxes. So I was looking his original equation 1, which is actually contains 3 terms, one for the emission of a layer, A for the upward beam, B for the downward beam as a function of the optical depth, and the emerging flux at the TOA. 3 very easy terms. It is very well known in the literature. It's reproduced everywhere, in Houghton, in Liu, in Goody, and Pierre Humbert, and Hartmann, and everywhere. So I create here first equations from this one, from these terms. The first equation is very well known in the literature. Again, it's the difference of the second and the first terms, given in Houghton books, Physics of Atmospheres, for example, in equation 2.13 is equivalent. The difference of A and E at the surface for the Earth's atmosphere, for example, that surface, it gives the net flux, the net radiation, which is in radiative equilibrium, which is in radiative convective equilibrium is the turbulent flux that is balanced by the sensible and latent heat. This for clear sky. So my equation 1, which is the difference of A and E, says that in the clear sky, the net radiation at the surface, that is in radiative convective equilibrium, the sensible plus latent heat, equals half of OLR. Unequivocally. This is my first equation. True or not, who knows? My second equation will be using a special case of the second term, using the tau equals 2 case. I do not speculate about why, but actually I realize that in that case, when tau equals 2, then A equals twice A0, What does it mean? That the total energy, the total short wave plus long wave energy absorbed by the surface equals twice the OLR in the clear sky. Sounds completely crazy. Why would it be? So, okay, let's try it. This is my second equation in the clear sky. The third equation, I create the all sky versions of these two very easily by connecting the clear sky and the all sky through the long wave cloud radiative effect, which is set as L. So if I separate the long wave cloud radiative effect of the atmospheric radiation transfer, then my third equation will be the same as the first one, but with all sky data in the left-hand side, all sky data in the OLR minus long wave cloud effect, then divided by 2, and the same for the fourth equation.
Okay, because
yes, okay, I think
time's up.
That's very easy. All right, very easy. I checked the 4 equations on your series EBF edition 4.1 data, and what I found that all the differences are less than 2 less than 3 watts per square meter minus first, and the 4 equations all together has a mean bias of actually 0. And then I projected it on the new GVAX diagram. Sensible heat and latent heat plus latent heat. Left-hand side, all are minus.
Could you just stop or wrap up?
Perfect. The difference is perfect. There is a geometric solution of that, and the geometric solution can be realized. Observed.
Sean, could you share screen there?
Okay, that's okay. Thank you. If you have anything to ask, here is my availability. Down there. Stop sharing. Okay. Thank you.
Sean, Sean, can we? How do I take a control?
Can you hear me now?
Oh yes, but
is that good?
I can. Oh, this is. Oh, this is yours. Okay, go ahead, Sean. 3 minutes.
Okay. All right. I will try to be very brief. I can see that my contribution is a little different from your main focus of the meeting, but I wanted to remind people that there is a very old approach which works amazingly well, actually, the Bedico-Sellers energy balance approach. And what I want to discuss very, very briefly is the fact that you can upgrade it and make a big improvement by properly taking into account radiative conductive boundary conditions, and that this gives much more interesting results, much closer to the data. So the idea is that here I'm showing how temperature varies from weather scales, very short times to much longer times. But the point is that after about 10 days or so in the weather, in the atmosphere, we have essentially air doubling time is something of the order of 10 days. And so everything becomes essentially stochastic. The GCMs become stochastic. The ocean component is more like maybe 6 months. But the point is that we have an opportunity here to come up with a model that should work over these longer timescales here, macro weather and climate timescales. Okay, so this is the idea. We're trying to come up with energy balance equations which operate over this longer timescales. And you could think of this as an update of Bedico-Sellers or Hasselmann theory, all of it based on the classical heat equation. And what Bedico-Sellers does is essentially it just redirects. You have some energy imbalance at some point on the Earth's surface, radiative imbalance, and the radiative imbalance is redirected away from the equator to the poles. And if you just do the global model, you get a box model like this. But if you, in fact, take into account the radiative conductive boundary conditions instead, so some of the heating goes in, some of the imbalance goes into subsurface sensible heat, and some of it goes into increased anomalous black body radiation, then the interesting thing is that you get the half-order equation. So there's a half-order derivative here. This is completely classical, right? So instead of the Bedico-Sellers with this h equals 1, you get h equals a half. And the significance is that essentially fractional derivative is a convolution with a power law, or say in Fourier space, it's just a power law filter. And the point is that essentially you get very long memory. So you have storage automatically, there's very long memory, whereas in the classical Bedico-Sellers, it's just exponential memory. And so that's the key value, the key thing. You could make regional models, and just again, you can compare Bedico-Sellers. Well, the latitudinal model, the Bedico-Sellers is here with h equals 1, the classical value, and okay, the updated Hebe is a half, and you have this horizontal divergence that comes in, and so you have this interesting, in fact, half-order operator. You can work out the spectra very easily from this. Phase shifts that are quite realistic, and especially over land, between the maximum forcing, say, per year and the lags. But the spectra looks like this. So omega is the frequency, so it's high frequencies, it's omega minus 1, low frequencies, it's closer to white noise. But these fits very well to say annually. These are globally averaged reanalyses temperatures here. And the right-hand side, these are paleo temperatures over the last millennium. And the relaxation time is something like 70 years. The interesting thing is you can do this on a regional basis, and you find that you get these relaxation times. Remember, so the relaxation time is a quantification of how long it would take the temperature to rebalance, re-equilibrate, if you had, say, a step function increase in forcing. And the interesting thing is that most of the places over land, it's something like a month, which is what everybody has been using as sort of assumed over land. But over ocean, there are some cases where it's literally millennia. And you know, this plot is based on NCEP reanalyses over 70 years. But the key point is that there are mechanisms then, essentially in this case to do with deep ocean currents, that can give you enormous memories. And these memories are not exponential memories, they're power law memories, which means that we have mechanisms now that could explain, you know, really long-term variations. So one application you could do is to make projections to 2100, and these can be made with significantly reduced uncertainty. So the blue is is based on this this fractional energy balance model. The gray is the CMIP5. I have other plots for CMIP6, but these are the multi-model ensemble and 90% confidence interval. So you can see that you get, in fact, perfect agreement, but you get much lower uncertainties with the Phoebe. And so, okay, so anyway, that's basically where I stop. I've probably already gone over my 3 minutes, but the idea is that there's an opportunity here to have a kind of an effective medium type of model at long timescales, which is essentially what Bedico and Sellers were doing based on the classical heat equation, but just by changing the boundary conditions to make them more correct, with, in other words, radiative conductive, you get these long memory phenomenon, and you get many much better agreement than you would without that. But anyway, okay, I better stop there.
Thank you very much to both speakers, and well, make sure that you send it, your poster to us so that the people have a question and ask a question later on. We don't have much time. Any questions? Or okay, well, thank you very much.
Apparently, the poster has been put up at your end. That's what I was told, so people can see it there. Anyway.
Okay.
Okay, thank you.
All right, bus to the dinner, or no? Or Jeremy? Oh, no.
It would be great.
Well, thank you. We have to go. The people online, and we're gonna start tomorrow 9 o'clock again. Thank you very much for all speakers today.